and welcome to the second day of first symposium on secondary aerosol formation and growth, NANO 2023. Today we have total 4 sessions. The first session is on chemical transformation of aerosol, and I request Dr. Pandit Roy to please chair the session.
Very good morning to all of you, and good morning to those who joined online also. So we have one keynote lecture and 3 invited lectures. First, I invite Dr. Manish Shri. He'll be talking on the recent advances in understanding secondary organic aerosols, implications for climate forcing. Dr. Manish, you have 30 minutes. Maybe in 25 minutes I'll give a signal. Okay, thank you.
Thank you, Vijay, and thanks for all the organizers for giving me an opportunity to present. Before I start this talk, I want to thank all my collaborators, my students, postdocs over the many years who have contributed to this work. I also want to thank the United States Department of Energy's Office of Science, Biological and Environmental Research Early Career Award, and the Atmospheric System Research Program for funding. So as we all know, secondary organic aerosols are formed by chemical reactions of volatile organic compounds. So they begin their life cycle as gases, but then due to many reactions in the atmosphere, they are transformed to lower volatility products which can condense to form secondary organic aerosols. And that is in sharp contrast to primary organic aerosol, which is directly emitted. And so if we think about what is a particle of SOA or secondary organic aerosol, this class of particles is made of thousands of organic compounds. So compared to a particle which is made of just sulfate or black carbon, it's one chemical component, but SOA is a class of thousands of organic compounds which changes dynamically in the atmosphere as a function of oxidation and many other processes. And the reason it is really important is, as we saw from previous talks in this symposium, that once we have nucleation, which forms the initial clusters, it can consist of sulfuric acid, amines, and other molecules. But then its growth from this ultrafine particle sizes to CCN relevant sizes is facilitated by SOA. So SOA has a critical role to play, not just in the size of the particles which contribute to cloud condensation nuclei, but then also hygroscopicity and then its impacts on clouds and radiation reaching the Earth. So this is a classic figure from our review paper, which we published in Reviews of Geophysics. Now it's almost 5 years or more. But the main idea behind this is one of the most important but unknown processes or uncertainties related to SOA formation is regarding anthropogenic biogenic interactions. And by that we mean, like many places in the world, like India, China, and many other places we know, have a mix of emissions. It's emissions from natural biogenic sources, example, isoprene and monoterpenes coming out from trees, but then also they mix in a typical urban environment with several different molecules, sulfate, oxides of nitrogen, other organic molecules like polycyclic aromatic hydrocarbons. But then this mixture then interacts in the atmosphere, and that interaction causes formation of SOA. And its SOA is dynamic both by composition but then also by its phase state. So it could exist in a liquid-like phase, a semi-solid phase, or a solid phase as a function of its composition, but ambient temperature and relative humidity. And this SOA mixture of thousands of organic compounds is classified into different classes, ranging all the way from intermediate volatility organic compounds, semi-volatile organic compounds, or SVOCs. But then also what we know pretty well is the highly oxygenated organic molecules and the extremely low volatility organic species. So this whole spectrum of volatility of SOA is what governs its new particle formation, the multi-phase chemistry related, which affects its growth and evaporation kinetics. And so this complex chemistry and this complex mixture then undergoes, it can seed clouds, so it affects the CCN, the optical properties and hygroscopicity of these particles, which then interact with aerosols and clouds, and then they feed back to biogenic emissions by aerosol radiation interactions and aerosol cloud interactions. And so the main idea behind this work is anthropogenic and biogenic emissions and their interactions, which form SOA, are still unknown, although we have made a lot of progress over the last decade or so with the advent of many new instruments. But many of these interactions are still unknown, and they are not included in climate models. And that could severely bias the radiative forcing of aerosols. So the main themes of secondary organic aerosols, which I'm going to touch in this talk, are highlighted here, and I will go over them one by one. The whole topic of SOA is so vast that it would be very difficult or almost impossible to cover it in one talk, but I will try to give some key highlights from different works from my group and other people's work. So let's start with some of the pathways to formation of low volatility organics. So as I mentioned, that low volatility organics are extremely important for the growth of ultrafine particles to CCN sizes. And so the first pathway is that when you have a gas phase like a VOC, which undergoes multiple generations of chemistry in the atmosphere, and by that I mean multiple steps of oxidation with OH radicals, ozone or nitrate radicals, it forms low volatility organic vapors, which can then undergo reversible gas to particle partitioning to form semi-volatile SOA. And then in the second pathway, the semi-volatile SOA, once formed, can then make bonds or polymers within the SOA matrix, and that this is called oligomerization or accretion reactions, which can make almost non-volatile SOA. So this process can happen on a time scale of minutes. The reversible gas particle partitioning and multi-generational chemistry happens on the time scale of hours. But then there is also another class which is called the extremely low volatility organics, and these are formed by isomerization of peroxy radical intermediates and rapid addition of oxygen. So this auto-oxidation adds many functional groups to the carbon chain very fast, on the order of seconds, and that can produce ELVOC vapors. And these vapors could be so low volatile that they could themselves nucleate, but then also help into the growth of other species. So why is the low volatility organics important? So as we know from the initial clusters like sulfuric acid, low volatility organics, ammonia and amines below 1 nanometer, when they are growing, their growth is enhanced by organics. So once they grow to sub 3 nanometer sizes, so when they are less than 3 nanometer sizes, there is also a strong loss by coagulation. And for them to get over this coagulation barrier, if you have a lot of low volatility organics that can act as a competing pathway, which can then grow them very fast to CCN sizes. So therefore, this low volatility organics helps them to get over the coagulation barrier. And volatility of these organics is a fundamental property that can enhance or increase the CCN number concentrations by a factor of 2 to 9. And so there is a very critical role of low volatility organics, which we need to understand, and we have been studying, as has been highlighted by many talks before me, including Professor Pulmala's and other talks. So before I go further, I wanted to give a perspective of what happens when the SOA formation interacts with clouds. So this is a typical figure from the representing a work in the Amazon rainforest from Andy Andrea's group. So what happens is that near the surface, the forest emits biogenic volatile organic compounds. These oxidize to form semi-volatile organics, and these semi-volatile organics can be rapidly lifted up by deep convective outflow all the way to the upper troposphere, which could be 10 to 14 kilometer altitude. And there the temperatures are so low, like 250 Kelvin, that these organics these are semi-volatile near the surface, because of warm temperatures, but here at really cold temperatures, their volatility decreases substantially, and then they can rapidly condense to form new particles and then grow. And these particles can then be slowly moved down by cloud downdrafts and also contribute to boundary layer aerosols. So it is important to keep this perspective as I discuss some of our other results in this talk. So this is a figure from Bin Zhao's work in PNAS, which we all contributed to. And what it shows is that in the regional model WRF-Chem, we included a two-dimensional volatility basis set, which includes temperature-dependent auto-oxidation and dimerization of ELVOCs and ULVOCs. So this is over the Amazon rainforest. The aircraft was sampling the entire atmospheric column here. You could see the black line represents actual measurements from the aircraft. Near the surface of the Amazon, there were about 200 to 500 particles per centimeter cube. But as the aircraft flew to high altitudes, between 10 to 14 kilometers, it sees up to 20,000 particles per centimeter cube. So these are actual measurements here in black. And then different model simulations. So when we just had an inorganic nucleation mechanism without the role of organics, it could not explain this high particle number concentrations in the upper troposphere. And similarly, when there was a scheme which has inorganics but a simple organics treatment that produced too much particles near the surface, too few particles in the upper troposphere. And so this complex treatment of 2D VBS, volatility basis set, which includes the temperature-dependent formation and NOx-dependent formation of these extremely low volatile organic compounds, shown in cyan line, best reproduce the measurements because these ELVOCs can be transported by cloud convective updraft to high altitudes. They can efficiently condense their nucleate and form new particles. So this is an example of how some of the most advanced measurements we have done in the recent decade has helped to close the gap between model and measurements of new particle formation, not just near the surface, but over the upper troposphere. Moving further, I want to say that the yields of SOA have a complex dependence on oxides of nitrogen. So here this is a schematic figure which shows that up to a certain value of NOx, the isoprene SOA yields increased, but then after that, as NOx is increasing further, the yields of SOA decreases. And one of the explanation for this is that if you see here, the different dots here represent different lumped component volatilities, and when they react with multiple generations, there can be functionalization reactions which decrease their volatility, but also fragmentation reactions which increase their volatility. So increasing NOx could increase the breaking of carbon-carbon bonds or fragmentation reactions, and that could reduce the formation of SOA. But there is this complex role of radicals and NOx in multi-generational chemistry, model parameterizations of functionalization and fragmentation as a function of NOx is challenging and is not adequately represented in most models so far. So just a brief idea of what functionalization and fragmentation is. So you have a carbon backbone here, and when it is reacted with OH or ozone or other radicals, it could add the functional groups to the carbon chain. And so what happens by addition of functional groups is the molecule becomes heavier, its volatility decreases, and so it can form more SOA. But on the other hand, when you are also oxidizing this carbon chain, you could also break the carbon-carbon bond. So in this case, you end up with two smaller molecules, and each of them would have higher volatility because they are smaller. And so this fragmentation reactions would increase the SOA yield, and would decrease the SOA formation in this case. And so there is this competition between functionalization reactions and fragmentation reactions and how it varies with oxidation and as a function of NOx, and that can change the formation of SOA in the atmosphere. So I wanted to present some real measurements which actually show that this functionalization and fragmentation happens in the real atmosphere. And this is work from Alan Goldstein's group. This was published in PNAS. This is measurements over the Southeast United States, and it shows that when you have a monoterpene, which is a carbon-10 compound, this is measured with two advanced instruments, the GC by GC instrument and the chemical ionization mass spectrometer, SIMS. And you would see that these monoterpenes can functionalize, but then also fragment. So you see a host of different compounds, so C10s, which with more oxygens here, but then also C9s and C6s here, which represent C6, C7, C8, which represent the fragmented carbon backbone. And in that paper, it was shown that the fragmentation products actually increased in the real atmosphere with aging in the presence of NOx. So these are some advanced measurements with advanced instrumentations which have shown that functionalization and fragmentation happens, and NOx has a critical role to play in this multi-generational chemistry and fragmentation and functionalization of these molecules. Now I would like to present a much more cleaner example of how anthropogenic activities have changed biogenic SOA formation. And in reality, if we want to look at how much have anthropogenic activity changed biogenic SOA, we want to go in a region which has which does not have any influence of anthropogenic activities. And so that kind of pristine baseline is very hard to find nowadays, because most regions in the world, including some of the forested regions, have already been perturbed or influenced by anthropogenic activities or inflow or transport of anthropogenic emissions. And so the pristine baseline of natural biogenic SOA is really hard to find. And so ideally, we need to go back in time under pre-industrial conditions if we want to fully unravel how anthropogenic activities have influenced biogenic SOA formation. But there was a field campaign which was designed in the Amazon rainforest. This is just a snapshot during the Go Amazon 2014-15 field campaign, where showing the measurements with the DOE G1 aircraft. So here you could see the vast green area of the Amazon. If you look from outside, it looks like a green ocean, especially in the wet season. And then over this ocean, this is the cleanest you could get to a terrestrial region which approaches pre-industrial times. Because if we are measuring the NOx concentrations, they are at levels of parts per trillion in the wet season in the pre-industrial background in the Amazon. And this has a lone source here, the urban emissions from the Manaus urban city, which is in the center of this region here. And so ideally, if we were to fly an aircraft which goes into the plume and comes out, we will be between present day times and pre-industrial times at the same time. And so exactly that was how the Go Amazon field campaign was designed. So you see the G1 aircraft, which is flying outside the plume and inside the plume. And as it is going in the plume, you see this periodic increase in particles and gases and other things. And when it comes out in the terrestrial region, in the pre-industrial region outside of the rainforest, you see a sharp drop in gases and particles and everything else which it was measuring. And so this was a very nice opportunity to study SOA formation and anthropogenically influenced biogenic SOA. And so here we are showing measurements using the aerosol mass spectrometer, which was mounted on board the same aircraft. And the orange is measurements of organic aerosol with the AMS. And you see as the aircraft goes between pre-industrial baseline, which is around 0.5 microgram per meter cube. And once it goes into the plume, you see about a factor of 3 increase in organic aerosols here. And then we were trying to model this with WRF-Chem at high spatial resolution and with all the mechanisms we know about anthropogenic biogenic interactions of SOA. And the model predictions are shown in blue. And you could see that the model here was able to reproduce this periodic rise and fall of the aircraft as it goes out of the plume and then into the plume. And then the other thing we could do in the model is we could just turn off the Manaus urban emissions. And that is the baseline in the model with this green. So you could see if the urban emissions were not there, you would not see this increase in SOA formation in the plume. The model is predicting that about 80% of this increase, even in the plume, in the anthropogenic plume, is natural biogenic SOA. And this is because the anthropogenic emissions of oxides of nitrogen substantially increase OH radical concentrations inside the plume, and that causes much more conversion of isoprene and monoterpenes to SOA. So 80% of this is biogenic SOA even inside the plume, but this enhancement could be achieved because of anthropogenic oxides of nitrogen. And so you see that in plume, the natural biogenic SOA was enhanced up to 300%. So this is just a summary of this finding. This was published in Nature Communications. What we see is that in the pristine wet season Amazonian rainforest background, the NOx is 20 to 50 parts per trillion, which is really, really low. But then inside the plume, the NOx is increased by a factor of 10 to 50. And so that causes increase in OH radical concentrations, and then that causes much more formation of biogenic SOA inside the plume compared to outside the plume. And you see this large increase, up to 400% increase in aerosol mass concentrations and SOA, organic aerosol mass concentrations, compared to the background, which can be explained by increased biogenic SOA, but that increase is possible only by the anthropogenic emissions of oxides of nitrogen. So I want to present another example of multi-phase chemistry and organic-inorganic interactions. So one of the most important studied pathways of aqueous chemistry and multi-phase chemistry relates to isoprene epoxydiol, SOA. So once isoprene is oxidized by OH, it forms ipox gas, and this ipox gas undergoes acid catalyzed ring opening reactions to form with, when the particles have inorganic sulfates, they have water, they have acidity, then this ipox can, from the gas phase, can react with these particles and forms ipox SOA, which comprises organosulfates and methyl tetrals. But there are, even though this is one of the well-recognized pathways and studied pathways in the last decade or so, there are still many, many unknowns to this ipox SOA formation. And some of the key challenges is that the particle phase acidity changes as organosulfates are being formed, and also as we are forming this ipox SOA, this coating is highly viscous, and this can reduce additional uptake of ipox gases. Isoprene epoxydiol has been measured, SOA has been measured in many locations globally, and some of the hotspots from the measurements are over the Southeast US, over the Amazon, and some of the other regions here. But then the key so it could contribute up to 30% to SOA formation in the Southeast US and over the Amazon. But here I want to say that key ipox SOA processes are either not represented in many of the SOA models or are not well understood. And so this is a schematic figure from our recent paper, which shows that there are key process level uncertainties like diffusion limitations in organic shell. The chemical kinetics of ipox SOA are not well understood. And then also this kind of ipox SOA formation can happen in the clouds, which have large volume, ample aerosol water. It could form ipox SOA, but then when the cloud evaporates, there is cycling between clouds and aerosols. And so that is another uncertainty in terms of understanding this multi-phase chemistry of ipox SOA and similar compounds in the real atmosphere. So how do we reduce these uncertainties? One of the ways is to use very carefully designed laboratory measurements. And here I am showing you a schematic from some measurements we did here at Pacific Northwest National Laboratory. And what was done here by my collaborators is that in a 1 meter cube Teflon chamber, ammonium bisulfate and other seeds, acidic and non-acidic seeds were injected, and then ipox gas was injected. And once the particles are being formed, the measurements were made, not just of the size distribution, but also several other properties like the composition, the density of ipox of the aerosol, and the volatility and evaporation kinetics as they were being formed. And so all these measurements together, the size, composition, density, and volatility, were really important to constrain the model to understand the processes happening. And measurements were made both at dry conditions and also medium relative humidity conditions. And so one of the findings from this is that a lot of the models, when IPOX SOA is getting formed, then it consumes the sulfate, the inorganic sulfate, and converts it to organosulfates. And once we are converting the inorganic sulfate to organosulfate, that causes a sharp drop in the acidity of the particle. Here it's more than two units of pH drop in acidity. And so if the models, many of the models, they don't account for this drop in acidity due to organosulfate formation. And what that does is that it could greatly overpredict the formation of IPOX SOA, because if you keep the particles acidic, even when organosulfates are getting formed, then the model will predict that you would make much more IPOX SOA compared to what actually happens here. So here you would see the black is observations, and then the red and the green are our revised model predictions, which account for this drop in particle acidity. And compared to that, this blue is a model which does not account for drop in particle acidity. So without dropping particle acidity, you could greatly overpredict IPOX SOA formation. And diffusion limitations are another aspect to this, which many models don't consider. So coming back to the part of diffusion limitations, so viscosity of organic aerosols could change in the real atmosphere. So it could vary from liquid-like, which is like water, which is free-flowing, to olive oil, honey, ketchup, peanut butter. This is viscosity is increasing in this direction, and glass marble is solid. So what that does is that if you can think of something which is liquid-like and it's taking up an organic gas, there are not much limitations, diffusion limitations for the organics to enter the particle phase and react there. But in a glass or a peanut butter, it would be much more diffusion limited. So if we can think in a semi-solid regime, in addition to diffusion limitations, the particle length scales matter. So if you have a 1 nanometer particle, an organic gas can easily reach equilibrium within a second or so, even for a semi-solid, because the diffusion length scale is very small for a 1 nanometer particle. But if you think of a 100 nanometer particle, the diffusion time scales could be a day or longer with a semi-solid. And this has implications to the uptake of organic vapors on these particles, because diffusion limitations can reduce SOA formation in this case. One of the approaches to studying these diffusion limitations is taking an aqueous inorganic core which is surrounded by organic material. And so this is, we solve for diffusion and reaction within both the organic coating and the aqueous core, and solve for flux balance across the interfaces. And that way we can solve for the reactive uptake of, say, IPOX gases within a coated particle. How do we predict the viscosity and diffusion limitations of SOA? So we have a framework here which was developed by Manabu and other groups, which quantify the viscosity as a function of volatility, composition, ambient temperature, and RH of the particles. So in the Amazon, for example, in the tropics, where it is warm and humid, SOA particles will be liquid-like near the surface, but as you are going higher up in the atmosphere, as the temperature is dropping and relative humidity is dropping, these particles become solid and viscosity becomes...
Dr. Manish, you have 3 more minutes.
Okay. So the viscosity has an important impact on SOA, and one of the implications of this is that when you look near the surface, there is aqueous chemistry, but when you look in the upper troposphere, what we found is that aqueous chemistry cannot happen because there is no water in the particle phase. It's the coating is solid, so the direct emissions of semi-volatile gases to the upper troposphere and their condensation in this case could explain IPOX SOA formation. So in the interest of time, I would not go further. This is another example from one of our studies where polycyclic aromatic hydrocarbons, which are cancer-causing, can be coated by viscous SOA and transport them to long distances. This is an example from cloud chemistry from one of our recent studies. And so with that, I will just leave with key takeaways that organic SOA are complex systems, and the interactions with anthropogenic NOx and sulfate can modulate them. And there are several unknown processes, for example, related to surface and in-plant biochemistry, which are unaccounted sources of SOA. And then the size, number, mass, composition, optical properties, and chemistry of SOA vary around the globe, but there are critical insights to be gained from different regions, which can be brought together when we are applying it to a new region. Thank you.
Excellent talk, Dr. Manish. So we have a couple of questions. Yeah, first, Neeraj.
Hello, Dr. Manish. I am Neeraj Rastogi. First of all, thank you so much for such an interesting and informative talk. My question is related to, one of the slides you were showing that isoprene SOA yield as a function of NOx. And you showed that initially it increases and after some time it decreases. So what decides that threshold that, okay, up to this point it will increase and then it will decrease? You said something that NOx is causing, carbon bond breaking. So that is why you have fragmentation and it is decreasing. But initially it is showing the increase. So that means same NOx. Yeah, so can you just explain that part?
Yeah, it's a good question. And that threshold could vary for different SOA systems. But the main idea is, like I showed an example for the Amazon rainforest, when you go from very, very small levels of NOx, like parts per trillion levels, to 1 or 2 parts per billion levels, initially the NOx will increase the OH radicals. And that could cause an increase in SOA formation. But then at some point, as you keep increasing the NOx, it will cause breaking of carbon-carbon bonds. So these are peroxy radical reactions with each other, and it could vary a lot for different SOA systems. So the specific example which I was showing was for isoprene SOA, but that kind of threshold for different like monoterpene SOA and other things still needs to be studied. And we know for Southeast US, I showed another example where monoterpene SOA also was showing fragmentation with increasing NOx. But Southeast US already represents an urban environment where NOx was already high. So yeah, I see your point, and that needs to be studied more. Thank you.
I have a couple of questions. Quickly I'll ask. So in addition to Neeraj Rastogi's question, so you have shown one aircraft observations going out from the plume and going inside to the plume. So in that plume, it is already like highly NOx reached. Like you told that it is increasing like 10 to 50 folds, from 50 ppt to its 10 to 50 folds.
1 ppb.
So why?
To 1 ppb, yeah.
To 1 pp. Okay, 1 ppb. So it is within the threshold limit, right? So my
Yes,
question was
1
that.
ppb for many of the smog chamber measurements, 1 ppb is still classified as low NOx.
Low NOx, okay.
So that was the whole point, that if you look at the baseline of the Amazon rainforest, the real baseline would be much, much lower than what we measure now with smog chambers and what we classify as low NOx. So even in the plume, 1 ppb, in the plume in the Amazon could still be low NOx conditions from today's chamber studies.
Okay. Another question is that in one of your chamber experiments, you have used ammonium bisulfate. So what is the advantage of using ammonium bisulfate instead of ammonium sulfate? Because epox OAs are known to be acidic, and ammonium bisulfate also has acidic like component. It's a like single H plus ion acidic. So why, what is the advantage in that?
Yeah, so the main thing is we wanted to do both dry experiments and wet experiments, and ammonium bisulfate does not have, it doesn't effloresce till very, very low relative humidity. So even at 5% relative humidity, it has some particle water. And so in that case, it is highly acidic though, at that condition. And so we could study the effect of both relative humidity and acidity by using ammonium bisulfate seeds. But there were also experiments with ammonium sulfate, which helps you contrast the role of more acidic to less acidic particles and the role of relative humidity. And so we do find that acidity has a strong impact on, say, oligomer formation of epox SOA. I didn't have time to go into further details, but we have looked at both ammonium bisulfate and ammonium sulfate. And the main advantage of ammonium bisulfate is it can retain particle water up to very, very low relative humidity.
Okay, for heterogeneous phase reactions. Okay.
Yes.
And also, like you have shown one a model estimation of epox SOA. So which model you have utilized for predicting?
We developed this model in-house. It uses the dynamic gas part. It uses the dynamic inorganic aerosol thermodynamics, the mosaic model, and then it has box. And then we developed our own capabilities for formation of epox SOA which includes many, many processes: organosulfate formation, the decrease of acidity with organosulfates, the formation of semi-volatile tetras, in addition to organosulfates, oligomerization of tetras. So we considered many, many processes in that box model which we developed for IPOX SOA, and we were comparing it with laboratory data of many, many things at the same time: volatility, density, size distribution evolution, the volume growth. And when we have so many things measured together, then that really helped to constrain many, many unknown parameters in the model.
Okay. And the input is isoprene and isoprene derived products, or just isoprene?
In the lab experiments, we were directly injecting IPOX in the gas phase to the seeds.
Okay.
Yes.
Okay, sir. Thank you, sir.
Thank you.
In the interest of time, so we can stop here, and let's thank Dr. Manish Joshi for an interesting lecture and interactions. Thank you, Dr. Manish. Thanks.
Thank you.
So next we will move on to the next speaker, Dr. Andrew Lambe. So he'll be talking on the measurements of secondary organic aerosols using an oxidation flow reactor. So it's an invited lecture, and the time is 20 minutes. Dr. Andrew.
Thank you for the introduction. Can you hear me okay?
Yeah, please go ahead. Yeah.
Great. Thank you.
Thank you.
So thank you everyone for coming to listen to my talk today. And I'll be talking about a comparison of SOA generated from the oxidation of laboratory biogenic and anthropogenic precursors by the oxidation of OH, chlorine atoms, and bromine atoms in an OFR. And so I'd like to start by acknowledging my co-authors on this work, as well as funding from the National Science Foundation, the NANO 2023 committee for giving me the opportunity to present today, Tescorn, our distributor in India. I'm a principal research scientist at Aerosol Research Incorporated in the United States. So I'd also like to acknowledge our customers and research collaborators whose measurements with our instruments have provided insight into air quality and source apportionment efforts within India. So in that context, I thought, what better way to introduce my talk than by showing AMS measurements in and around India that are summarized in this recent paper by Gunt et al., shown here. And so this figure shows pie charts of the speciated non-refractory particulate matter measured by the AMS, broken down into its main subspecies, being chloride, sulfate, nitrate, ammonium, and organics. And to me, there are three major take-home points that are apparent from this paper. One is the relatively high loadings of non-refractory particulate matter, measured at almost all of these sites, approaching hundreds of microgram per cubic meter during the winter. The organics are the green fraction of this pie chart in all of these plots, and so there's a high organic content, and depending on the season and the source region, this can be both significant contributions from primary as well as secondary organic aerosol. And then finally, something that as far as I know is relatively unique to India is the high fraction of particulate chloride. So that's the purple slices in these pie charts. And my best guess is that this is likely some indication of an important influence of halogen chemistry in these source regions, right? Because if you have enough gas phase ammonia and gas phase HCl to make ammonium chloride, which is presumably at least some significant fraction of this particular chloride, the presence of those high HCl along with other reactive chlorine species in principle should allow for significant formation of chlorine atoms as well, which are a very reactive oxidant that can compete with OH for the oxidation of many VOCs. And that's a point that I'll get to over the course of the remaining slides in my talk. Here is a summary figure from a modeling study that was recently done by Lee et al., where they investigated the influence of halogens on haze pollution in the wintertime in northern China. And some of the main points that were apparent from this modeling study is one, that both anthropogenic chlorine and bromine emissions in China, when included in this model, enhanced the PM2.5 concentrations on a study average basis by about 20%. And then within that segregation of different compound classes of PM2.5, the enhancement in SOA was even more significant, over 100% enhancement when chlorine and bromine chemistry is included in their model. And both of them were important, as was determined from this sensitivity study when they removed chlorine and removed bromine emissions separately from the model. The SOA concentrations increased from 6 to 15 microgram per cubic meter just by adding that chemistry in. And so that begged the question to me, to what extent is this representative of other source regions? And again, I would argue, looking at those chloride aerosol concentrations in and around India and comparing them to the minuscule fractions of chloride aerosol that were measured and modeled in China, it doesn't seem like that big of a leap of faith to me to imagine that halogen chemistry is probably important in India also. But with that context, I want to introduce the motivating question for this research, which is, how does the chemical composition and the yield of SOA compare when it's initiated by halogen atoms versus OH oxidation, which on a global scale is the most important daytime oxidant in the atmosphere. And so to investigate this question, we conducted a series of laboratory oxidation flow reactor studies in which we continuously input biogenic or anthropogenic VOCs that were oxidized by they were oxidized in the OFR following controlled exposure to OH or chlorine atoms or bromine atoms in separate experiments. And so in this context, an OFR is best thought of as a lower cost, higher oxidation capacity smog chamber that also happens to be field deployable, and so in principle it can be used to investigate the SOA formation potential of ambient air masses in different source regions as well. And that's an active area of research for this method. The fundamental goal of an OFR is to mimic aging timescales in the atmosphere on the order of days within a couple of minutes of residence time in the OFR in real time. And so in these experiments that involved characterizing the number concentration and the size information of the SOA particles that were generated with a scanning mobility particle sizer and our aerosol mass spectrometer to infer the chemical composition of the SOA and calculate hydrogen to carbon ratio and oxygen to carbon ratio as measurable surrogates for the oxidation state of the SOA. So now I'm going to show results for several biogenic and anthropogenic precursors over the next few slides, and I'll start with isoprene SOAs as a canonical example to illustrate you to the type of results that we obtained. And so isoprene is a C5 biogenic VOC with 2 double bonds that happen to make it very reactive to not only OH, but also chlorine and bromine, which can directly add to both of those double bonds. And so this figure shows the SOA mass yield obtained from OH, chlorine, and bromine oxidation of isoprene across separate experiments as a function of the integrated exposure in the OFR. And so to orient you toward these numbers, 10 to the 11 per cubic centimeter of OH exposure, which is about in the mid-range of this plot on the x-axis, is about 1 day of atmospheric aging at a typical OH concentration of 10 to the 6 per cubic centimeter. Chlorine is 10 to 100 times more reactive than OH towards most VOCs. In the case of isoprene, it's about 7 times more reactive towards chlorine than it is OH. So lower exposures are needed in principle to obtain SOA formation. And bromine and OH have similar reactivity towards alkenes. In this case, the bromine reactivity towards isoprene is about 70% of OH. So in principle, the same numerical oxidant exposure when bromine is the oxidant should give a comparable extent of oxidation as does OH. So with that background, some of the results that we observed are as follows. We observe a maximum mass yield with isoprene of about 40% after about 1 day of equivalent atmospheric aging. We see increases in the yield of SOA at low OH exposure, followed by a decrease at higher OH exposure, and in the case of the halogens, chlorine exposure as well. As Manish discussed in his talk, this is our interpretation of this trend is the transition from a functionalization-dominated mechanism at lower exposures towards fragmentation at higher exposures, resulting in carbon loss, even as oxygen-containing functional groups are still added. And so, whereas a maximum mass yield of approaching 40% for isoprene is observed, and again, this is with no added NOx, so this is an upper limit to what the yield would be in ambient conditions. The maximum mass yield obtained with chlorine was about half of that, about 20%. And then with bromine, the yield was on the order of 1 or 2%. And as far as I know, no one has measured yields obtained from bromine oxidation of VOCs before. So while this wasn't necessarily an interesting result, it was a novel result. And then taking the same data and looking at the chemical composition of the SOA and how they evolve with aging, this figure shows the hydrogen to carbon ratio as a function of the oxygen to carbon ratio for these different isoprene SOA types. And what's apparent from this is that there's evidence of significant multi-generational oxidative aging of OH SOA and chlorine SOA, because the oxygen to carbon ratio increases from about 0.3 at the lowest OH and chlorine exposures at which we observed SOA formation, up to about 0.6 for chlorine and almost 1 for OH. Conversely, with bromine, the oxygen to carbon ratio never gets higher than about 0.3. We interpret this to be the case that even though in principle the extent of oxidation is similar, based on the relative reactivity of bromine and OH towards isoprene, the reactivity of bromine towards first or second generation oxidation products must be small, because if it was significant, then you would in principle see an increase in O to C ratio to a much greater extent than what's observed here. So now a similar set of results for alpha-pinene. We see the same qualitative trends in SOA yields as a function of oxygen exposure. The yields increase and then decrease significantly for alpha-pinene chlorine SOA and alpha-pinene OH SOA. But here, again, in the absence of added NOx, the yield is higher when chlorine is the oxidant, with a maximum yield of about 45%, compared to 30% for OH at about a day of equivalent atmospheric aging. And again, bromine doesn't appear to initiate significant SOA formation with this precursor, because following the initial bromine addition to the double bond, its apparent reactivity towards later generation oxidation products seems to be small, because if it were significant, in principle, functionalization would continue when you would have increase in yield and an increase in the oxidation state of the SOA also. But again, as was observed with isoprene, the oxygen to carbon ratio of bromine SOA never gets more than 0.3 or so, whereas the O to C ratio of alpha-pinene OH SOA and chlorine SOA approaches 1, along with a concurrent decrease in the H to C ratio. Toluene was one of 3 anthropogenic precursors that we examined in this study, and so I'm showing that one first. It is not reactive towards bromine on any scale, to any extent that would be applicable to atmospheric chemistry. So here we just looked at OH and chlorine. And so what was most interesting to me about this system was that we observed similar maximum mass yields regardless of whether OH or chlorine was the initiated oxidant, despite radically different changes in the elemental composition between the different oxidants. So within the experimental uncertainty, we observed yields on the order of 0.5 to 0.6, and yet the hydrogen to carbon ratio was systematically much higher in the OH SOA than the chlorine SOA. And we attribute this to just the different initial attack on the aromatic backbone of toluene by OH versus chlorine. OH adds directly to the aromatic ring, so it can create hydroxyl groups. If there's HO2 present, which there is, you could in principle form organic peroxides as well. Whereas chlorine does not add directly to the aromatic backbone. It preferentially reacts with the methyl group that's attached to it. And so we attribute that to the main reason why the H to C ratio is lower, because we're not adding alcohols, which don't result in a net decrease in H to C ratio compared to other functional groups. Contrast that now with another anthropogenic precursor, endodecane, where the elemental composition is almost exactly the same regardless of the oxidant, as you can see from how the H to C and O to C evolve on the same trend line here. The yields are different. Here, when chlorine is the oxidant, the maximum yield was higher than 2, So it's a very efficient SOA precursor. And with OH, which it's still high SOA yields, approaching 1, is significantly lower than when chlorine was the oxidant. So significant dependence of the oxidant on the yield, even though the chemical composition is basically the same, at least as is inferred from the elemental ratios, because hydrogen abstraction is the dominant mechanism, whether OH or chlorine is the oxidant, since dodecane is a saturated molecule without any double bonds to add to. And then finally, this was the most interesting of all the precursors that we studied, to the point that we published a separate paper just on this one, decamethyl cyclopentosiloxane, or D5, which we use as a surrogate precursor for personal care products, was an extremely efficient SOA precursor regardless of oxidant. We saw mass yields approaching 1.5 when OH was the oxidant, similar mass yields when chlorine was the oxidant under humid conditions, where the relative humidity in the OFR is about 40%. And then in the absence of any added humidity, the mass yield under dry conditions approached 3. So a factor of 2 change in the maximum yield was observed depending on the humidity that was used. And then related to that, before I even get into the elemental composition of the SOA, the other point is that whereas with all of the other precursors we saw evidence of fragmentation at the highest oxygen exposures that we used, with D5 we didn't see that. The yield just keeps increasing and then or levels off. Part of that is kinetic limitations with OH, because D5 has an OH lifetime of about 10 days under typical atmospheric conditions. So maybe there just isn't enough exposure. But even when you're approaching 100 days of equivalent OH exposure, you don't see that turnover in the yield curve like you do with the other precursors. So my interpretation of this result is that the siloxane backbone that's present in D5, the silicon atoms bonded to the oxygen atoms, retain low volatility nature of SOA products, even when the methyl groups that are attached to each of the silicon atoms are functionalized or fragmented to reduce the carbon number of average carbon number of the SOA. Okay, and so now just looking at the elemental composition of the SOA and how it evolves with aging, you again see that because hydrogen abstraction is the dominant reaction pathway for D5, whether it's OH or chlorine, the H to C and the O to C ratios evolve in basically an identical fashion in a Van Creveld diagram, whereas the H to C and O to C ratio behaves very differently when there's no humidity added to the OFR. The O to C ratio approaches 2, and the hydrogen to carbon ratio drops significantly. And so we discuss some hypotheses to explain this apparent humidity dependence in the paper in more detail, but basically we think it's related to direct reaction of water vapor with alkoxy radicals that are formed following OH or chlorine attack of the D5. So to close the presentation, over the next couple of slides, I want to use our results to suggest some possible mass spectral markers to look for in ambient data with AMS measurements in terms of fragments chlorine-containing fragments that are present in all of the chlorine SOA types and then the bromine SOA types on the next slide. In the types of chlorine SOA that we sampled with the AMS, these are the chlorine-containing ions that we detected, which range from less than 1% of all of the SOA signal for dodecane to about 11% for isoprene. Cl plus and HCl plus were the dominant ions in all of these SOA systems, but there was also a series of carbon, hydrogen, and oxygen and chlorine-containing ion fragments in each of them as well, some of which were the same across all of the precursors, and others, such as C4H6Cl and C3H2ClO, were unique to toluene SOA. So in principle, these could be used to fingerprint organic chlorides in ambient AMS measurements, given enough signal. And then analogous to that, for the bromine SOA types that we characterized in this work, here are AMS measurements of bromine-containing ions in these experiments. And again, the Br plus and HBr plus ions were the largest fragments in the spectra, but then also an extensive series of carbon, hydrogen, oxygen, and bromine containing ions were detected out to about mass charge 200.
Dr. Andrew, you have 2 minutes more.
Great. And so in these systems, the bromine containing ions fractions contributed about 4% to 12% of the total SOA mass. And so again, in principle, could be used to fingerprint organic bromides in ambient AMS measurements, given enough signal. So in closing, to summarize the main points of this talk, we saw that for each of the 5 SOA precursors we looked at, there were distinct yields, both in their absolute and relative values, whether OH, chlorine, or bromine was the initiating oxidant. With that said, there is much higher similarity when OH and chlorine were the oxidants than when bromine was, because OH and chlorine initiate multiple generations of oxidative aging, whereas bromine appears to be limited to 1 or 2 generations at most. And then finally, our results suggest that in source regions with active halogen chemistry, chlorine may significantly enhance the SOA formation potential in those regions, whereas bromine may not, at least not directly, because it doesn't seem to initiate significant SOA formation by itself. Any influence that it has would probably be to increase SOA formation by increasing concentrations of OH through radical recycling reactions. And so with that, if you're interested in more details from the work that I presented, I'll refer you to these publications from our group. Otherwise, be happy to take any questions. Thank you.
Thank you, Dr. Andrew, for keeping up the time and excellent talk. We can take some few questions. Yeah.
Thank you, Dr. Lambe. I am Neeraj Rastogi. Thank you for the nice talk. In initial slides, you were showing this isoprene SOA and alpha-pinene SOA. Can you go to that slide, if you don't mind?
Yes. Sorry, let me.
So initially, alpha-pinene SOA and isoprene SOA you were showing, right?
Yep. Let me go back to that. Sorry.
Yeah. Yes. Okay. So, yeah. So this right-hand side figure, that's H by C, O by C. So if you have reactant isoprene only, so to start with, how you will have any O by C, and then means for halogen, how this O by C is increasing. Means H by C decreasing, that I understand. You are replacing hydrogen by chlorine, but how O by C is increasing in this? And similar case you have shown in subsequent slides also. So can you just explain this part?
So you're asking how do you start with?
Yeah, one thing is you don't have any O by means O in this, right? If you are taking these only as a reactant, to start with there is no oxygen. Means this your isoprene has no oxygen. You have only H by C. But you are starting somewhere around 0.2, and then it is increasing with the, H by C decrease is understandable, but O by C, why it is increasing for the case of chlorine?
So I think your question is why are there no data with oxygen to carbon ratios between 0 and 0.3?
That is one thing, and other thing is the slope what you are showing here, right? Yep. So that slope means you are replacing H by either O or by Cl, right?
Right.
That is how it is evolving, right?
Mm-hmm. Yes.
But if you are doing this chemistry with halogen, how O by C is increasing? That is what one thing I would like to understand. And other thing, to start with, you are having some O. So this bromine, it is, say, in case of bromine, it is at one place.
Right.
In hydroxylradical, it is again clear that if you are oxidizing, you are putting more and more oxygen, so it is following that slope. That is understandable. I am just not able to follow this chlorine. Right.
So when chlorine or bromine initiates the oxidation of the VOCs, there is, if it for an alkene precursor like isoprene, they add directly to the double bond, and then the oxygen adds quickly as well to make a peroxy radical. So the chlorine or bromine addition does not prevent oxygen addition as well, in the same way that it does OH. So when OH adds the double bond, you have an alkyl radical as well, and then rapid O2 addition to make a peroxy radical, and then the fate of the peroxy radical is what influences the product distribution. Same thing for chlorine and bromine. The chlorine or the bromine itself doesn't have any oxygen, but they add to the double bond to make an alkyl radical, and then with the oxygen that's already present in ambient air or in laboratory air or whatever, that adds to make a peroxy radical, and again, from there, the fate of the peroxy radical governs the composition of the SOA.
That means when you say halogen, you are not talking about pure halogen, it is halogen oxides also.
Even when the halogen initiates the oxidation, as long as there's oxygen present, the oxygen will add to the alkyl radical containing the chlorine or bromine to make a peroxy radical that has two oxygens, at least two oxygens, and then auto-oxidation or multiple generations of oxidation will continue adding oxygen-containing functional groups to the molecule.
Okay, thanks.
Hello. Hi, Andy. This is Subrata. I have one question for you. If whatever oxidations you have shown for isoprene, monoterpene, and other species, so it is mostly homogeneous nucleation and followed by SOS, right? That path.
In these experiments, yes, any SOA formation is achieved from homogeneous nucleation.
Yes. So, my question is, if we want to add some seed particles like ammonium nitrate or something, and do the same experiments, do you have any reference for that, or if you have done that earlier?
In these experiments, we did not add seed particles. In the paper, we compared yield measurements obtained in the University of Texas Environmental Chamber, where they did use seed particles in all of their experiments. And there was not any systematic effect of seed particles for the precursors we compared, but that doesn't mean that it wouldn't have an effect under some of these experimental conditions. My guess, and it's just a guess, mind you, but my guess is that if there was any influence of condensation sink on the yields, it would perhaps be for those species or those oxidants where the yield is relatively small, because that might imply that the oxidation products were semi-volatile and might be more sensitive to changes in the condensation sink from adding seed particles. So isoprene bromine, for example, the yield might increase relatively more when you have seed particles present than when you are using isoprene OH or isoprene chlorine, where you get significant SOA formation even without adding seeds.
Because
that is a hypothesis that could be tested in future work for sure.
Okay, because in real atmosphere you won't have like homogeneous like nucleation very often, so you will be always having some seed particles like black carbon or ammonium sulfate. So where the deposition will happen. So that's why my question is like, and it is doable with PAM, right?
It is, yes.
Okay.
Yeah.
Thank you.
Okay. Thank you, Dr. Andrew, for excellent presentation and interactions. So with this, we'll go to next talk by Professor Neeraj Rastogi. So he'll be talking on the oxidative potential of atmospheric aerosols over India.
Okay. So, good morning everyone. Firstly, I should thank the organizer, Dr. Vijay Ganawade and Dr. Rakesh Huda, for giving me this opportunity to share whatever little bit I know about the topic. Once you see the title, Oxidative Potential of Atmospheric Aerosol over India, many of you, including myself, will think that this belongs to the last session, Aerosol and Health. So why you are presenting it here? Are you leaving early? No, I am not leaving early. So there is some link. Let me show that. Okay. So we are hearing since yesterday. We all know that our atmosphere, it is like a cooking pan, right? It cooks whatever you are putting into it. So means you are putting primary particles directly from different sources. You are putting precursors of secondary aerosols, and all these things from different sources. We understand this part. Secondary particles are found under if your meteorological conditions are favorable, you form secondary particles. That also we are hearing since yesterday. We understand this part. During transport, once, whether it is from primary or secondary, once it is in the atmosphere, during transport, both primary and secondary particles can undergo a variety of physicochemical transformations process, which is called cooking or aging or atmospheric processing, whatever you want to call it, before they get removed from the atmosphere. So some example, for example, suppose you form some acidic species like sulfuric acid, nitric acid, okay? They can react with dust or sea salt, and then their physicochemical properties will change. I will just show you example of this from my earlier studies. Acid titration by mineral dust and sea salts. So suppose you have mineral dust, which is represented as calcium carbonate, and then you have sulfuric acid or nitric acid, and they are reacting. So it will form calcium sulfate or calcium nitrate. We know that mineral dust is coarse particle. We also know that freshly formed sulfuric acid, nitric acid are very fine particle. If they are reacting, they are forming, obviously they will form coarse particle. But what is the implication of this process? You are increasing the solubility. Dust itself is sparingly soluble, less soluble. But if you are doing this kind of processing, you are making it more soluble. Other thing, dust is hydrophobic in nature. It doesn't love water. But if you have this kind of coating at the surface, then it will attract water. So you are making the surface hydrophilic. Then you are decreasing the number concentration of fine particles. So you know, means when you are reacting one dust particle, it will react thousands of small particles. So in a way, you are changing the size distribution of those fine particles into coarse particles. And obviously, it will result in shorter resistance time of those fine particles. So we actually observed this. So this is from my thesis actually. And you see, there is an anti-correlation between EA upon calcium and bicarbonate upon calcium. So what does that mean? So let me first tell what is EA. EA is excess acid, which is Ta minus ammonium plus potassium. And now what is Ta? Is total acid. And SS means non-sea salt sulfate plus nitrate. So we calculated total acid. Now part of it which is already balanced by ammonium potassium, we remove. So that is excess acid. Now if this is reacting with calcium carbonate, you are supposed to get anti-correlation, and that is what we got around the year for 2001 and 2002. So that means we have shown that these reactions are actually happening over Ahmedabad. Same thing if you are going to sea. We have sea salts. They can react with sulfuric acid, they can react with nitric acid also, and they will form sodium sulfate or sodium nitrate, and you will release HCl. But how do you know this reaction is happening? So this is the, from multiple cruises over northern Indian Ocean, I am saying it is really Bay of Bengal. Multiple cruises, you see, from 2000 to 2009, multiple cruises, and the relationship is chloride deficit versus excess sulfate. Now what is chloride deficit? Means we know that chloride by sodium ratio in sea salt is 1.8. So that means expected chloride is 1.8 times sodium concentration. So this is expected chloride, but this is what we measured. So whatever difference is here, that is deficit. So if there is deficit, we have seen that chloride deficit and excess sulfate was correlating very well. That means these reactions were happening over the marine atmospheric boundary layer. And implication of that, just in previous talk we heard, you are releasing the HCl. So okay, let us see what is. So what we told here, that near quantitative chloride depletion was observed. Near quantitative means almost all chloride has gone. Very small amount of chloride we were able to measure. The deficit was very high, which also means that sea salt could serve as a potential sink for anthropogenic SO2 in the dominant polluted marine environment. And this loss of HCl, what was talked in the previous talk also, that it can be large source of reactive chlorine that has implication to oxidant chemistry in the marine atmospheric boundary layer. Okay, so what we understood? Okay, so what we understood so far? That aerosol aging can modify the size, composition, and surface properties of aerosol. What else it can do? So if you have acidic species, they can also affect the abundance of soluble metals. Now what does that mean? Say if you have some dust, it will have some iron also. That iron If you are simply putting in water, that concentration will be very low. But if it is with acidic species, then soluble iron will increase. And what is the implication of that? It will change the bioavailability of micronutrients. So whomsoever is working on surface ocean, you know, iron is a micronutrient. So if it is reacting, dust is reacting with acidic species, for the same amount of mineral dust deposition, you are adding more soluble iron. So that is another thing. Okay. So other than that, redox active metals can generate reactive oxidation species. What is that? That we'll be talking in the next slide. Through Fenton and Haber-Weiss type of reactions. After that, in addition, organics like PHs, they are oxidized to their derivatives like quinones. They are redox active. They can also generate reactive oxidation species. Further, upon deliquescence or during cloud or fog processing of SOA, decomposition of organic hydroperoxide, that can also generate reactive oxidation species. So by any means, if you are generating more ROS in the atmosphere, that would increase the oxidizing capacity of the atmosphere and facilitate the SOA formation or their rapid aging. So in 2 slides, whatever I said, this is the summary. Aerosol aging causes various types of chemical transformation, and presence of organic, inorganic, redox active species can generate ROS and may affect the oxidizing capacity of atmosphere. Okay, now what is ROS and oxidative potential, where we are talking now. So in a sequential univalent reduction process, this oxygen undergoes reduction forming several reactive intermediates. So oxygen, if it is getting electron from somewhere, it will form superoxide anion, then hydrogen peroxide, hydroxyl radical, and ultimately water. From where this electron is coming? This electron is given by the redox active species present in aerosols. This ROS can be radicals like superoxide, hydroxyl, peroxyl, alkoxyl, hydroperoxyl radicals, or they can be non-radicals also like hydrogen peroxide, hypochlorous acid, ozone, singlet oxygen, peroxydated and all. So now what is oxidative potential? Ability of ambient aerosol to generate ROS or deplete antioxidant. Deplete antioxidant is only related to health inside our body. Depleting antioxidant or generating ROS, kind of similar. But when we are talking about atmosphere, capacity of aerosol to generate ROS is called their oxidative potential. Now redox active species, what I am saying, they can, means any species which can give or take electron, they are redox active. In inorganics, we know all transition elements are like that, like iron, manganese, copper, cobalt, chromium, molybdenum, nickel, etc. And in organics, like derivatives of pHs, quinones, they can be this redox active. So ROS present anywhere. If it is in ambient air, they form via photochemistry through multiphase reactions and affect atmospheric oxidizing capacity and secondary organic aerosol formation. In human body, they form via intracellular metabolism and cytosolic enzymes, and they cause oxidative stress, inflammation, cell death, which lead to various cardiopulmonary diseases. In plants, they form due to sunlight intensity, or salinity, drought, nutrient deficiency, pathogen attack, and they affect the productivity of the growth. So in short, ROS, wherever they are affecting inside our body, in plants or atmosphere. Now I will be talking what we have done. So with the thesis of my student Anil Patel, means we were lucky that we started this aerosol oxidative potential work in India. You see these red dots, these are the places from where he collected the samples. Port Blair, Shillong, Patiala, Kanpur, Mount Abu, Ahmedabad, and then there was a cruise over Arabian Sea. So all these places we collected the samples. And then we did variety of chemical speciation like major ions, TOC, acid soluble metals, water soluble metals, brown carbon, this water soluble organic aerosol through offline AMS, and oxidative potential through DTT method. Now let me briefly tell what is DTT method. So aerosol oxidative potential through DTT method. So what you do in this case, you take some thiazolidinol, 100 micromolar you take in different vials. You take, this is very laborious work. You said
5 vials you take. In each case, you are taking 100 micromolar of DTT. Now you are adding soluble PM in all. PM start consuming that DTT. Now in different vials, you are adding this DTMB at different times. So first vial you are putting 10 minutes, second vial you are putting 20 minutes, 30 minutes, 40 minutes like that. And then you are measuring the remaining DTT. Once you put DTMB, it quenches the reaction, so it stops. So whatever remaining DTT is there, that is what you are measuring. So as a function of time, it decreases. So from sample to sample, you will see the slopes are different. Steeper the slope means higher the oxidative potential. Okay, so actually this slope is by micromole per minute. That is oxidative potential, which you call DTT activity also, or oxidative potential, or consumption rate of DTT. Now you have measured this. Now if you normalize it with respect to the volume of air you collected, you call it OPV. If you normalize it with respect to mass of aerosol collected, you call it OPM. So per unit mass is OPM, per unit volume of air is OPV. This is what, okay? Now, this is what we have observed over Patiala. So what do you see here? OPV versus PM2.5 and OPM versus PM2.5. We see there is a significant correlation. There was a scatter, but there was a significant correlation between OPV and PM2.5. But if you see OPM, for similar mass concentration, it is ranging from here to here. Mass concentration is the same, but OPM is varying too much. So what could be the reason for that? So actually, if you see OPV, you can write like this. OPV is equal to OPM into PM. The slope of that line is OPM. If you divide OPV by microgram per meter cube, it will come OP per microgram, right? So what is happening? Why it is showing like this? If that line is very tight correlation, say R square is 1. So here you will see a flat line, because this is per unit mass. Why should vary per unit mass, right? Per unit mass should remain flat. It is independent of mass concentration, but it is varying. So why? Let us try to understand a little bit of that. Say, suppose this red portion is your PM mass, and that black dot what I am showing is redox active species present in that mass. And this arrow is OPM. Huh? Now, if we change that in the same proportion, whether increase or decrease, same proportion. So whatever percentage you are increasing redox active, same amount you are increasing this mass, or reducing the same proportion, OPM will remain same. Okay, but if you increase the mass and your redox active species are similar, OPM will decrease. Right? Again, if you keep the mass same, but redox active species should decrease, OPM will decrease. Again, mass is same, but redox active species are more, OPM will increase. So that is, for example, this case maybe for this kind of sample. This case, you see, high concentration is too high, but OPM is low. So this kind of example. Okay. So in short, what I am saying here, that OPM depends upon the chemical composition, that is relative abundance of redox active species in particulate matter. Okay. Now some results, let us see. So this is the study we did over Delhi. This was online RS measurement, and it was done from post monsoon to winter. And what we saw, that traffic was mostly contributing to OPV. In the valley, obviously, it was fireworks, and during winter, it was biomass burning. But in all the season, secondary aerosols and atmospheric processing, it was affecting OPV. This was another study which was compared Delhi versus Illinois. Mass concentration, you see, mass concentration over Delhi was 13 times higher than Illinois. But once you compared OPV, it was only 5 times. Reason is same what we discussed in previous slide. It is the redox active species which are present in, now irrespective of the total mass concentration. So that means in Illinois, redox active species are higher. That is why you are getting similar OPV compared to mass. Okay. Then some correlation. What we saw, that OPM showed a very significant relationship with envisaged 44, which is a representative of oxidized organic aerosol. And then also with this C2 formaldehyde group greater than 1, and with potassium, which is a proxy of biomass burning, and with sulfate. So simply one would infer that these species are responsible for the observed OPM, or sources emitting these species also emit redox active species responsible for observed OPM. Why I am adding the second line? Because over Patiala, in previous slide I showed there is a good correlation with sulfate. Over Patiala we have shown that with SIA it is negative trend, OP. So we observed the negative correlation between SIA and OPB over Patiala. And to investigate that further, we did some lab experiment and we found a negative correlation. So to investigate, so we found that SIA is DTT inactive. Now again recall that whatever red dot versus black I was showing. So in that case, even if your redox active species is remaining same and inactive species you are adding more, so OPM will decrease. It will appear to decrease. So that is what we observe. So it means that, so now this we understand. So it means that mere correlation between OPM and measured species does not allow one to infer that a species is responsible for OPM. We need to understand the underlying mechanism. And we need more detailed studies with spatio-temporal coverage along with aerosol OP, along with size, composition and meteorological factors to identify the responsible species or processes and which are affecting aerosol OP. Now this is the just almost final slide, and this in the beginning I showed that from where we collected the samples. Now I am showing overall results. So this is the composition over all the sites, and you see this red one is OPM, green is OPB and black is mass concentration. See just few things carefully, you see black versus red and green here, black versus red and green here and here, and means in between. So you are seeing quite a bit, means quite significant differences. Their mass is more compared to the other bars. Here these bars are going much up compared to mass. So why is it so? It is same thing what we were discussing. So this is Shillong or Port Blair. You are getting aged aerosol masses from Indo-Gangetic plain. Aerosol means atmospheric processing are increasing their OP. Arabian Sea, mineral dust was coming. Mineral dust is TTT inactive. So you have more mass, but OPB and OPM were low, and other things were in between. So from our study over urban, semi-urban, mountain and marine regions, this is the major conclusion we draw, that one thing is OP of species coming from biomass burning is much higher than whatever is coming from fossil fuel burning. Other is OP of anthropogenic aerosols are more than natural aerosol, as you can see from here. Aerosol OP is governed by the chemical composition rather than total mass concentration. Oh, I missed that. Atmospheric aging. So this is the reason. Atmospheric aging or fog processing increase the aerosol OP. That is why you are getting this kind of trend. And aerosol OP is governed by chemical composition that we have already discussed rather than total mass concentration. So what overall it says, that mitigation strategies for reducing aerosol concentration alone may not work, and linking aerosol OP with health effect will be more effective. As far as, suppose if you are saying that just reduce the mass concentration of aerosol, that may not help, because fraction of redox active species present in that, if you are reducing that, that only will affect as far as health effects are concerned. So to summarize whatever I said so far, so this I think I have already said, so one can read.
Okay, thank you, Professor Neeraj. We can take few questions.
And I wish to acknowledge my supervisors, actual people who are working, I am just presenting, and my wonderful collaborators. And these are our publications from aerosol OP work. Yeah.
So I don't see any questions. So, oh, okay, Subrata.
One question, actually, in your earlier slides, you have shown one comparison of chlorine deficit with excess sulfate. So all the measurements are from cruise, right?
Yes.
Okay, so whether you have seen any seasonality, because the source of H2SO4 in ocean mostly from DMS, maybe, right?
H2SO4 sulfate.
Sulfate, like it is like it's a exchange reaction,
Okay.
H2SO4
Okay.
with.
So, okay. So season, when you say, all these cruises were taken during January, February.
Okay.
Winter time. So you know that time you get the plume from Indo-Gangetic plain.
Okay. Okay. So it's mostly continental origin.
Yes. Sea salts are obviously from ocean, and other things were coming from. So that is why you have calculated NSS sulfate, non-sea salt sulfate. Yeah.
Okay, let us thank Professor Neeraj. Yeah.
Yes.
So, just sorry, what effect, say, for example, in case of Western IGP, which is dominant by the dust aerosols, and Eastern IGP, which is more dominant by the polluted aerosols. So, how do you think in your theory this will impact the overall process?
It affects almost all the things. Means whatever you say, initially I was talking about the solubility of iron. We have shown that if we are collecting aerosol over Arabian Sea versus aerosol collected over Bay of Bengal, solubility is much different. Here it is 1%, 2%. Here it is going up to 40, 50% because of this kind of reactions. Same thing means I have shown that bar, that red green versus black. You have seen Port Blair and Shillong, that how much different they are compared to whatever you were getting over Arabian Sea. So this processing is
any data from Western IGP like
Patiala, means Western IGP is Patiala, but means during winter we have done. Okay.
Okay, thank you, Professor
Thanks.
Neeraj. So we'll move on to the next talk by Dr. Soumya Singh. She will be talking on atmospheric ammonia measurements, sources, processes, and its impact on air quality. I think we are on time, maybe 2 minutes.
Is it fine if am I audible? Perfect.
Which one?
Yes. Soumya? Yeah.
Next slide, this slide, and this font.
Okay, thank you. So, hello everyone, good morning. My name is Soumya Singh and I am a research scientist at UC Berkeley. I will be taking you from air to soil to vegetation a lot, so just bear with me. And so first of all, I want to thank organizer and Vijay especially, because my talk is I'm not going to talk about the particle a lot, but I still feel like, and you will agree that, ammonia is so relevant. So yeah, thank you all the organizers and thank you University of Hyderabad. So let's start with acknowledging my group so far. So I did my PhD from JNU, and then I went to do my first postdoc in University of Toronto, where I did a lot of ammonia flux measurement and I learned a lot about ammonia exchange from atmosphere. And then I am currently with UC Berkeley, so working on PM 2.5 measurement. Okay. So usually I don't go with the outline, but because it's I figured that this is going to be quite a mixed audience, so I just thought I'll give you an idea how my talk will be going on. So I'll talk about some, first I'll give you the introduction of the ammonia hotspot, why exactly I'm talking about ammonia here, but then we understand, I'll go with from the sources to the sink. So what happens once it's in atmosphere, and then how it impacts the air quality, and then also when we look back a few years back and how we see that trend is going on. So just to I have written this for me, that also to explain that my talk I'll be going from the global, I'll just show the global trend or global chemistry or whatever the deposition or emission I will be, and then I'll be also giving the Indian scenario. I try to patch that with my work, and also brought my other research group study as well. So yeah, so let's look at what is these global ammonia hotspots look like. So basically with the evolution of the satellite data And we can see this beautiful picture when we see that ammonia, this is basically the atmospheric infrared sounder satellite, which actually measured the ammonia concentration. So I think this is a recent development. Recent, when I say, it's like around 2002 or something, the satellite came, and we can actually see that these are the major hotspot, and they identified the major hotspot globally, and IGP and India is one of them. But when you look at the trend of and they looked from 2002 to 2016, and they came up with this the difference of the ammonia rate per year, how that is changing. So the warmer color you see here, it's basically showing it's increasing over the time, and when you see the cooler colors, which is like in blue, it's showing the reduced, because of the reduced agriculture burning, they are seeing the decreasing trend. And of course we are here, we are in the warmer zone. Warmer means the increasing zone basically. So starting with the ammonia pollution, so what is this pollution means? As we all know by now that ammonia is one of the most alkaline basic nitrogenous species in atmosphere. It acts as a precursor and it reacts with the acidic part of the atmosphere, which is like acids, sulfuric acid and nitric acid, and form the PM 2.5. It can actually deposit to and also create the haze in densely populated area. It can also deposit to the sensitive ecosystems. So let's get deeper into the source and sink process. So okay, so now we are talking about the sources. So ammonia agricultural activity has been the largest source, which account around 80% globally. But when I say agriculture activity, it also includes the fertilizer application and the animal farming and all. And then there are biomass burning, vehicles, industry, and natural sources as well. So once the ammonia in atmosphere, of course, anything goes in atmosphere, it will come back. So it has sinks. As sinks can be atmospheric chemistry happening in the atmosphere, reacting with the acids, and then forming the particle, and then and implications on the air quality. But then it can also deposit to the surfaces like water bodies, like soil and forest, and then it has further impacts like soil acidification, agricultural productivity, eutrophication, and climate change. So now, I mean, this arrow was intentional because I'll be talking from one of my measurement we did in Ottawa. So I'll be talking about ammonia exchange with the surface is bidirectional. So this was not by mistake. Just wanted to help. All right. So let's look at what is the atmospheric global budget, because I'm moving towards the sources of ammonia. So it's important to see how this is. When we see different source contribution. So basically, this is not a very recent paper, but ammonia is so difficult to measure because of its, it's a very sticky and volatile gas. So this has been always a challenge, whether you have a very integrated measurement, which can be like 8-hour integrated measurement, or something a fast response measurement. So this paper actually, they took the data, wet deposition data from different measurement monitoring network across North America, Europe, and China. So like NADP and then CapMon from Canada, and they took the ammonium wet deposition data, and they actually derived that to the ammonia emissions using different emission inventory. So you can see that the fertilizer and manure actually contribute a lot, and that's where so my talk will be mainly focusing on how much ammonia agricultural and food system is actually going to contribute to ammonia, and how that is what are the other implications to that. So yeah, these are two major impacts. So let's look at the agriculture and ammonia separately. So once you have fertilizer activity is one of the major, when you think about the agriculture activity, so fertilizer application is one of the major component on that, and urea is one of the dominant fertilizer when we think about fertilizer across globe. And once you apply urea, it get hydrolyzed with the water moisture inside, present in soil, or with the irrigation, And with the help of this urease enzyme, it creates ammonia and CO2. This ammonia can actually escape, but we are putting this urea because we want to give food to the plant. So it can actually, it can do its own work, go to the nitrification and, the nitrate, and then plant can take that. But what happens usually, it actually immediately escapes from the soil. And that's a problem for farmers, because there is a term called nitrogen use efficiency. So basically how much nitrogen you are putting in the soil, it's not going to the plant. So that's also reducing. And then what's happened, if this ammonia is going to the atmosphere, that also creating the PM formation and other implications. So we are basically losing, there are many implications coming from the economic cost, we are from the fertilizer application to the environment as well. All right, so there has been many, attempts, I would say. There have been many effort to really come up with how much actually ammonia is coming from these fertilizer applications. So I put together this chart from this paper, and basically you can see the nitrogen loss in form of ammonia after urea fertilizer application is from 30% to basically 12 to 15% in Europe, and South of Asia is one of the highest contributor. There is no surprise because it's a mainly agriculture dominated area. But why this high variability we see? Because of, there are, as I mentioned, ammonia is really challenging measurement. It's an extremely challenging molecule to measure, and also there is because of the advancement in the instrumentation recently, we are able to actually measure ammonia in a better way nowadays. So I was doing, so as a part of my postdoc in Toronto, we had this motivation, okay, so what happens if we go to the farm with a fast response measurement, and if we really conduct a 2-year experiment in the field, and do we see that high emissions coming from urea application? So we collaborated with the AFC, Canada Food Inspection Agency, and they have like a beautiful experimental farm where they have this flux tower, and they have this sonic anemometer, and they do N2O flux. And so we had our instrument which is called quantum cascade, which is called quantum cascade laser spectroscopy, QCL. You can see the full form here, and it's basically a fast response measurement, and it measures every 10 hertz. So every millisecond you will have a ammonia data. It measures the concentration, but when we actually measure the turbulence, which is the vertical wind, we can see the covariance, and that's how we derive the eddy covariance flux. But I have put this for the simplicity, but it took 1.5 years to really clean the data. So it's not that simple. It's a complex process. But this is our experimental setup. It has the analyzer, basically the QCL, and then you need because it's a laser instrument, you need a chiller to cool that. So I will not go into the detail about the instrumentation here. And just to give the perspective how this data looks like, it's a millisecond data, so this is just the time series to show. This one is the ammonia concentration in ppb, temperature, and the wind speed. So whenever you see there is a spike in the ammonia data, and if it's co-vary with the wind speed, basically that time you understand there is a flux. But this is exactly not the process we compute the flux. There is in background we have to do a lot of computation and a lot of calculation, but this is just to show visually how that time series would look like. Alright, so we got 1 year of data. I am just presenting 1 year of the data, but as I mentioned in the first graph that when I was describing the process, ammonia is actually, it can emit from the soil to atmosphere, but it can also deposit if they depending upon there are different parameters. So we did actually capture emission, deposition, emission, deposition. So this is basically a one full growing season data, and then on y-axis you see the flux that's in the nanogram per meter square per second. So whenever you see a flux value more than 0, then that's emission. Whenever you see value 0 less than 0, that's basically deposition. Sorry. All right. So, thank you. I really need this. Thank you. So to actually estimate how much ammonia is coming from the fertilizer application, we basically look at just a few weeks of the data, because once, think about the crop. You start growing the crop, after a few weeks it will just grow. So then the atmospheric exchange with the soil actually just break, then the coupling start happening with the atmosphere and then the canopy. So we basically, that's the reason we only take the 3 to 4 weeks of the data depending upon the canopy growth. So here you see other parameters which are being measured on the field, and this is the mixing ratio. So we also collect the soil data just to make sure that we have the measurement of the flux, but also we want to model how that actually correlate with the soil data, because it's all happening inside the soil. So what happens that there is an atmospheric concentration, but there is also a term called emission potential. Emission potential is basically the ammonium concentration in soil and then the pH. So you can compute that emission potential, and based on that there is the basic chemistry based on the Henry law constant and acid dissociation constant. We can actually we can actually derive that what would be the direction of the concentration going, if it's going into atmosphere or not. So based on that, we also found that our measured value were very much comparable to the model, and we saw actually very little ammonia emission from our experiment. And this was a very first successful eddy coherence measurement globally, actually covering 2-year season. And we have not. I'm still working on the paper because it's just very challenging. So yeah, hopefully in 2023, yes, we will see the paper coming up. So that was Canada. Now moving back to the India. So I also did, during my PhD, we did not measure the flux, but we I actually measured the ammonia concentration in different, rural and urban region. So rural was UP, there is a village called Mai, that's actually my village, and then Delhi. So we actually saw there was a significant seasonal variability in the ammonia concentration. And we measured concentration, but of course we wanted to trace back what is the underlying cause. So basically you can see that there is in rural area you can see monsoon is always washout, because of the washout effect you can see the lower concentration, but in rural area the seasonal differences are very much clear. And we have these crop season, Rabi and Kharif. So you can, I'm not able to really say that I was not tracking the fertilizer activity, but in a bulk I can say that whenever there is a temperature and that's the atmospheric condition not favoring to the mixing, and also the fertilizer activity combining with that, that's basically increasing the ammonia concentration. But that also, you can argue that PM 2.5 would be also like that. So because it's a concentration, I cannot really go back into the source identification here. But so I talked about agriculture, but there have been actually the non-agriculture sources as well. Traffic emissions have been there have been many studies reporting traffic emission. So this is actually my project. It's I have been doing this, and I love giving name to the project. It's called Analysis of Measured and Modeled Atmospheric Nitrogen, and this I have been doing with my one of my colleague from Netherlands. He is a satellite person, so it's perfect to really collaborate. So just like everybody was doing COVID the data taking from the COVID and understanding how that impacted the air quality, what I thought that this is the perfect setting to see if there is any influence we see when we see the reduction in the transportation or any the industrial activities shutting down. Do we see that data in ammonia concentration? And we have taken this data from CPCB. There are limitations in that data set, but because this data set is available, we will be, and that's why I actually wanted to just look at the data set. So I took the criteria was I will take the 3 year of data, and that's where I got just 7 sites, and 5 sites from Delhi and 2 from the surrounding area. And these green colors is basically showing the shaded color is showing the lockdown period in 2020, then the green is the lockdown period in 2021, and you see this is the hourly concentration basically with a moving average of 2 weeks or something. So when you see, I mean, from this data, I still, trying to interpret, still analyzing this data. So we don't see really a clear difference, a clear, drop when the lockdown started for ammonia. Again, I want to remind about the measurement limitation. Really? Okay. All right. So this. So this is basically, I wanted to show this work I'm doing to understand what are the other sources we have. Then there are zinc, and once this is in atmosphere, it can react with our other, So there has been studies in Salt Lake City. Why I took this example? Because this is showing exactly what kind of level we see in IGP, and that's basically my research group in Toronto. They did this measurement to understand how this is actually ammonia is contributing to the haze formation in Salt Lake City. Again, from that data set, CPCB data set, I'm trying to see how IGP and non-IGP actually reasons are are different in the ammonia concentration, and we are trying to see that from the satellite data, which is the CRIS satellite data, cross-track infrared satellite data, and how that is comparing with our measurement, ground measurement. So there is another thing which is called deposition. Deposition could be basically, it can be dry deposition and wet deposition. So from this satellite, I just want to focus on, from this graph, I just want to focus on the ammonia part, and overall the message is here, the deposition is also increasing as we go, our demand for the food and energy is increasing, the fertilizer overuse is also increasing. Again, actually, basically, I just wanted to talk about the deposition, and we also observed that in Delhi, that in wet deposition in last 2 decades, this was done in my PhD, we also observed that the ammonium deposition increased like 4 times. So clearly from the global satellite data, when we see that very locally from India or US or Canada, we see that similar pattern, but you need to understand the uncertainty with these measurements or these, the graph analysis I'm showing, it's huge. So that's again showing really that what we need more measurement basically, and I want to jump into this summary part. So it's nothing very like I'm not going to talk about anything, just we found something. I just want to highlight one of the goal, or actually the key goal of my talk was I wanted to talk about ammonia, which has been a not overall discussion in Indian scenario, I would say. Like people talk about it, but we need to bring the agriculture, atmospheric and air quality people together to really solve this or to really understand this problem, I would say. So yeah, I mean, we need total NHX measurement, not just the gas measurement or simultaneous measurement. Yeah, I think I talked about it, so I can just, thank you.
Yeah, thank you, Dr. Soumya. We can have a few questions.
Hi, nice and interesting. So how soil moisture and soil acidity will affect this ammonia exchange?
How soil moisture, so its deposition actually create the soil acidification, I would say, because when if it's getting deposited and when it's get the soil moisture, it can go into NH4 plus. So then if you think about the nitrification, that will create actually from ammonium to the nitrate nitrite formation, there will be H plus, and that actually create the soil acidification.
How it will impact that ammonia exchange? Like if it is acidic. Okay.
Yeah. Let's thank Dr. Soumya for interesting talk. And with this, we have come to the end of this session, chemical transformation of aerosols. And I thank all the speakers for sticking to the time. And I thank organizers for giving me this opportunity. Thank you.
Thank you, everyone. Thank you, Dr. Pandit Rai, for chairing the session. And I thank all the speakers. We are running late, 5 minutes. I think that's all right. Jury has given me poster presentation evaluation reports, and they told me that it was very extremely competitive. Very is not probably appropriate word. Extremely competitive, and we had to go 2 rounds, and this is what we got. Yeah, so we have M. Deva Prasad, Arun Nair, Subrata Mukherjee, Pallavi Padwal, and Oishi Chakrabarti. Welcome back. Our next session is aerosol cloud radiation interactions. I request Professor Sagnigde to chair the session.
Yeah, so good afternoon, everyone. So in this session, we have one keynote talk, 2 invited talks, followed by 3 lightning talks. So I request the speakers to keep it in the time, and without much delay, I invite Dr. Pandithurai to deliver his keynote talk.
Yeah, good morning, everybody. So first of all, I thank Professor Vijay and Dr. Rakesh Huda for invitation, and I thank all the organizers for wonderful hospitality for the last 1 day, last 2 days. So with this, I'll start. So I'll be talking on the aerosol cloud precipitation interactions, which is an uncertain component of climate system. So I had to thank many of my colleagues. I have not listed all the names, but some of them are here, Subrata and Pallavi, and there are other colleagues, Leena, Anil Kumar, Abhishek Ray. So I will be presenting some of their PhD thesis work. So if you see this schematic which describes the aerosol cloud precipitation related processes, which occurs in a GCM grid box. So you will see, so there are several processes which interacts with other aerosol cloud precipitation processes, and with a large range of spatial and temporal scales. So here you can see the cloud types, which include low-level stratocumulus and cumulus, where the research focuses on aerosol activation, and there is a mixing and new particle production in the below cloud bases. And when it comes to high clouds like cirrus, so you will see the aerosols act as ice nuclei, and in turn contributes to the ice precipitation processes. So here the primary processes are given in blue color. So whereas the secondary processes that result from and influence aerosol cloud interactions are shown in gray color. And so you all know that in high cloud active aerosols, there will be higher cloud droplet, more cloud droplets gets activated, and for a given liquid water, if there are more number of small droplets, then they cannot grow to larger size. And so for a given volume, if there are more number of smaller droplets, it increases the reflectivity of the cloud. So it's widely known as Tommy effect or cloud albedo effect. When the droplets are small, it will not get collide with the falling drop, and it can bypass the falling drop. Whereas the large droplets which can collide with the falling drop, in turn the collision coalescence of efficiency will be higher. So it's also known as the cloud lifetime effect. So this way, the cloud active aerosols, which could be act as a cloud condensation nuclei or ice nuclei, and it will lead to the cloud radiation interactions and the aerosol cloud precipitation interactions. So in turn, now it can suppress or increase the local precipitation and alter the thermal radiation and latent heat profiles, and in turn it can affect the hydrological cycle and climate. So there are several processes which are listed here, and so IITM took some initiatives for better understanding on these aerosol cloud precipitation interaction processes. The one was in 2009, so it was a project which used instrumented aircraft, cloud aerosol interactions and precipitation enhancement experiment. And after that, subsequently, we also established a cloud physics laboratory in Western Ghats, and currently, so we are also establishing an atmospheric research testbed in core monsoon zone, which is central India. So wherein all the atmospheric processes are could be understood, and in turn it can better represent in models. So that's the idea. So KIPEX, this is led by one of my colleague, Dr. Tara. So it's the major objective is to understand the aerosol cloud interactions, and also to formulate a scientific basis for rain enhancement, because in India there are several state governments, which they used to go for cloud seeding projects for rain enhancement. So the ministry wanted to take a scientific basis seeding and give recommendations to the government. So with that, this project started. We got an opportunity to better understand the cloud processes. So in this project, we used instrumented aircraft, but with aerosol, cloud, and some of the meteorological variables, but not detailed aerosol chemistry because of the limitation of the aircraft, and also due to space. Even though we tried to get some chemistry, but it's not that we could not have aerosol mass spectrometer type of online instruments. So the interesting results, what you can see here is the polluted continental clouds. So this is some vertical profiles of cloud drop size distribution. In one case, continental polluted, which is conducted in 28th May 2009. The other one is near Mangalore coast. It's considered to be a clean marine case. So what you see here is the number what you're seeing. It shows the meter, the altitude in meters. So you'll see from 4.5 kilometer to 7.5 kilometer. So in spite of cloud, sampling the cloud drop size distribution for 3 kilometers, so the drop size distribution did not broaden. Whereas in the clean marine environment, you can see that the droplet size distribution broadened within even 3 kilometers, right? So what it does is that when there are more cloud active aerosols or polluted environment, the droplet size distribution doesn't broaden at certain height. So it takes, it tends to grow to deeper heights for warm rain initiation to occur. So it indicates that the collision coalescence is suppressed here. So whereas here the collision coalescence is active. So that's what we could see how the aerosols can influence the cloud drop size microphysics, and in turn it can affect the precipitation. So in this case, so even though the warm rain did not get initiate, but during the later part, so the ice microphysics also plays a role, because so in this region during May there is a lot of dust aerosols which could act as a potential ice nuclei. So we could see some ice hydrometeors while sampling the clouds at higher heights from 6 to 7.5 kilometers. So there are some studies from IITM giving that how the rain forms at a higher elevation when there is a more pollution. So that's a thing. That's one of the study, and this graph is not coming up. That shows some modeling simulations with different CCNs. So giving a different result, giving similar results what we have seen in the observations. So this is another paper which showed, so when the warm layer depth has to increase when there are more pollution. So to improve our understanding on aerosol cloud precipitation interactions, so we have certain knowledge gaps. So we don't have full understanding on the CCN and ice nucleating particle activation processes, which is representative to our region, so that these observations can help tune the existing parameterization in models, and also what physical and chemical characteristics which control the activation of complex anthropogenic and natural aerosols prevailing over these regions to how it serves as a CCN and ice nuclei. And this is the cloud physics laboratory, which you will see in Western Ghats. So I invite you, all of you, in some occasions whenever you are visiting, you can have some collaborative proposals. So we have several facilities for all these three components: aerosols, cloud, and precipitations. So also you will see that there is a high vegetation, so which you can see there is a potential for biogenic volatile organic compounds, which we recently initiated, so which will act as a potential precursors for secondary organic aerosols. So these are some of the objectives we set, that so how the aerosols influence microphysics, and how we can develop a better parameterization for our relevant to our region, and what is the role of biogenic volatile organic compounds on secondary organic aerosols, and in turn CCN activity. So those of you are not very familiar with the Western Ghats, you can see this color is shown in the altitude, and you have a dense vegetation, and it's a highly very heavy precipitating region. So there is, it's not very clear that the orographic precipitation in this warming scenario also has some climatic signal that there is a decrease in orographic precipitation. So how these the anthropogenic influences are altering, that's a major question here. So with this, I will divide my talk into two parts, like CCN and ice nuclei, depending on the time availability. So these are some CCN supersaturation spectra which we observed over Western Ghats, and also this is near Hyderabad. So we had some campaign to support the aircraft observations over this region. So we have CCN spectra for different regions now. In addition to these, on campaign-based Varanasi and other places. So this is one such result. We could see that how the aerosol and CCN are varying in different season diurnally, and you could see the different diurnal features in different seasons depending on the different sources and the other processes. So what you primarily see in monsoon, you will see a primary peak in the morning, whereas in the pre-monsoon you have the secondary peak is the evening peak is dominant. So the question is that in spite of heavy precipitation, even during these break situations, we have higher aerosols and higher CCN. So we were trying to understand what could be the possible contribution of biogenic VOC emissions from these regions to these organic aerosols. So we tried to look at the chemistry of these aerosols, and this shows for several days. You can see a systematic diurnal variation of high organics during the daytime from the morning to, so the kind of scenario we could see, so which we try to link with aerosol and CCN variability. So this is one day where we could see how the diurnal variation of CCN, and so compared with the chemical composition of aerosols, you can see this. So it closely resembles the organic aerosol variation. Also, we could also see some such a new particle formation events over this place. So using all these, so we try to see the closure between aerosol and CCN, and what is the role of organic aerosols. And so this shows, this graph shows, this is the aerosol concentration, and these other curves are CCN concentration at different supersaturations. So you can see during the late night and early hours, the activation fraction is very close to 70 to 80%, whereas so during the daytime you have the activation fraction reduces considerably due to the complex chemical composition of aerosols. So we try to see, in the absence of the hygroscopicity measurements, we try to see using the ACSM chemical composition, we try to see whether the estimated or modeled cloud condensation nuclei, how better it matches with the measured CCN by having different scenarios of inorganics and combine inorganics and organics. And when the better correlation is seen when you include the inorganics and the oxygenated organic aerosols. So, so that is in the absence of hygroscopicity. Later, we try to augment the hygroscopicity measurements at our lab, and so this is a HDMA setup. So wherein so you have two DMAs. One you see the dry particle radius and send it to another humidified DMA and humidification chamber and see the growth factor of aerosols. And from the growth factor, if you estimate the hygroscopicity, which is commonly called as kappa, and you have for different seasons, so March, April, May, and the monsoon and post-monsoon and winter for different sizes of the particles. So this is a PDF, and we classified these data sets into 3 classes. One is less hygroscopic, below 0.1, and the other one is hygroscopic population between 0.1 and 0.2. The third class is more hygroscopic population. The shaded region is in the hygroscopic population, and you can see different type of size dependence, what you see in different seasons. So when you take a seasonal average hygroscopicity, what you see is different behavior in the Eichen mode size range, and so there is an increase in kappa from in the accumulation mode range particles. Range sizes. So we try to see what could be the possible reasons. So what you see is in pre-monsoon, so the more hygroscopic population tends to get reduced. And the above 100 nanometer, you will see the more hygroscopic population increases. So this is one of the reasons for this such a behavior, that so there is the reverse trend in the size dependent hygroscopicity. So in monsoon, you can see there is a flat variability, and we try to look at the PDF of diurnal variation of hygroscopicity, and the black line shows the average hygroscopicity and for different sizes. So we try to see with the chemical composition. So it clearly shows that during the daytime, in the morning hours, there is an increase in organics, which reduces the hygroscopicity, whereas so whenever you see an increase in inorganics, which leads to higher hygroscopicity, and these are some average so values what we use for. And so if you look at the chemical composition in pre-monsoon, so you have higher ammonia and higher ammonia and chlorides in pre-monsoon, which could be one of the possible reasons for increase in kappa values in pre-monsoon as compared to winter season. So we try to see the closure study between kappa derived from growth factor from HTDMA and the derived from chemical composition, and this chemical composition is derived from AMS. So one thing what you can see is that the AMS only can measure non-refractive species, and also using the ZSR rule for estimating the hygroscopicity. So you need to assume the type of aerosol mixing. Also the transmission efficiency of AMS is also lower at lower diameter. So during measurement, lot of particles could be missed. So if you try to use the chemically derived K in models, could add error in CCN activation processes, and which will in turn affect the cloud lifetime and closure. So we also try to see, even within chemistry, try to see the different mixing scenarios and see which one is closer to the growth factor derived kappa. So this paper so recently come in atmospheric, science of total environment. And we also try to see how whether we can parameterize this hygroscopic growth factor. So for different seasons, we try to see what could be the coefficients. So in the absence of such complex growth factor measurements, so one can use in this region, this kind of chemical composition is there. One can use this parameter, so parameterization to estimate the growth factor for any dry diameter. Now, also we also implemented the volatile organic compound measurements, so which currently Subrata is working on for his PhD thesis. So he looks at the variations in isoprene, monoterpene, and benzene toluene, and so we could see that this isoprene was highest among all the VOCs, so about a factor of 5 during summer. So this could be due to the high temperature, which results in a higher isoprene emission. So when you look at group the data with the temperature, so you can clearly see that there is a good amount of emissions when the temperatures are increased. So here I try to also see that how there is evidence from the VOCs, and how do we see that SOA in the AMS measurements. So you can see that there is a time lag between the VOC measurements isoprene, which is shown in green color, and what you see on the right hand side is from the AMS. So he further he plans to utilize all these data sets to assess the SOA formation using a box model. So to estimate secondary organic aerosols. So this could be so the estimated SOA can be further compared with the oxygenated organic aerosols, which we can estimate from the AMS data. So how I'm doing time? So okay. So now I'll shift slightly from the CCN to the ice nuclei. So aerosol also facilitate the nucleation of cloud droplets and ice crystals in the Earth's atmosphere. So what you can see is that there are more ice nuclei, there is more ice and precipitation, so which leads to shorter life and in the low level. And if very few ice nuclei, then mid-level clouds persist as liquid, so which can lead to a net cooling effect. So here we try to measure the ice nuclei and try to parameterize from based on observations. As you all know, as compared to CCN, the ice nuclei are very few in number. So you can say 1 in million of aerosol particles. So here we used a continuous flow diffusion chamber for online measurements of ice nucleating particle. So very few studies are carried out. We conducted in aircraft collecting samples, and there are other previous studies also offline samples, and do analysis in the ice chamber, and we don't have continuous measurements. And so if we have continuous measurements which could be used to develop a better parameterization to improve our climate prediction. And this is the spectrometer for ice nuclei we use, and it's a CFDC type chamber, and this is a semi-automatic instrument, and so there's a lot of effort is required to conduct one experiment, like almost 8 hours a day one has to work on to collect data. So I think I'll skip these technical specifications. So basically the ice nuclei, so we try to look at different seasons, mainly in these mixed phase temperatures, like below minus 25 degrees onwards up to minus 34 degrees Celsius. But now we are also parallelly collecting some samples on assay and try to go even below this temperature to get ice nuclei concentrations. And as you know that there are the existing ice nucleation parameterizations some are supersaturation dependent, some are temperature dependent, and there are some temperature within aerosol dependent, aerosol concentration dependent. So we also try to put our measurements into the temperature and the aerosol dependent method, and we try to derive similar to the Paul DeMott parameterization, but so this is one of the paper which came out that how even the DeMott equation, which he uses similar parameterization, but it doesn't fit to our region. So we used our observations and tuned it to match better with the observed INP concentrations. So also we tried to test this in the model, and I think I'll skip this, and it is tested in WARF model to see how these different parameterizations fare well with this, and so which shows that we also try to compare with radar reflectivity. So what we see with by implementing our parameterization in the model and see how it compares well with the observed reflectivities. There is a reasonable agreement, but still there are a lot of biases which further need to be tested. So we also try to see how well it simulates the raindrop number concentration or raindrop size, and we see that the IITM the spin developed parameterization matches closely with the observations. I think so. With this, I think I'll summarize in the interest of time, and so to summarize that the aerosol particles are necessary ingredient for cloud droplet formation and ice nucleation process. So how they can modify the cloud microphysics sometimes in subtle ways to generate feedbacks that may amplify or dampen their influences. So aerosol dependent ice nuclei parameterization for our region is developed and tested in models. So cysteine activation process studies are being made using size resolved chemistry and hygroscopicity observations. So these observations are essential for process studies, and also to develop parameterization representative to different climate regions. So with this, I thank you all. And so all these measurements over orographic regions generally represent the orographic convection cloud processes. So we also setting up a atmospheric research testbed site in central India, which is a core monsoon zone. So if we can improve the prediction in core monsoon zone, so core monsoon zone rainfall is highly correlated with all India rainfall. If we can represent the processes in the core monsoon zone, so which will be more realistic representative for the region. So whereas the Western Ghats cannot represent the entire India. So that's the idea that we are also coming up with developing the testbed facility. So I welcome all of you to join in this effort. So maybe in future we will have proposals from MOEs. You can also submit proposals, and it should be like our dream is to have like a DOE arm type of site, which is there in southern Great Plains in Oklahoma. So similar to that. So this is a plan of Ministry of Earth Sciences, and we are trying to implement this project. So we already set up a suite of instruments, but still need to add many more. With this, I think I'll close. Thank you.
Yeah, thank you, Dr. Pandit, right on time. So, questions? Yeah, please.
Yeah, it's nice lecture about aerosol cloud interaction. Just I want to know, how does aerosol layer like vertical distribution of aerosols affect the aerosol direct radiative forcing?
Okay. Yeah. So the direct radiative forcing is like how it influences the radiation budget at the surface and at the top of the atmosphere, and the vertical profiles will give the alter the heating rates in the atmosphere. So the heating rates are changed, then it can affect the stability of the atmosphere. So if there is a highly absorbing type of aerosols, the atmospheric forcing could be on the higher side, so which will lead to the more absorption and more heating rates. Yeah. The vertical profiles are important.
Okay, thanks for the very good talk, and I was especially happy to see the ice nucleation measurement being conducted at your station, and it's impressive that you used the spin as the first time in India. Maybe more of a comment than a question, but these kind of ion measurements, they are really crucial because they basically dictate. You cannot have rain from a cloud without having ice nuclei in that, basically, because that's the only process how you grow the droplet to a large enough size. And it means that these kind of ion measurements are very crucial and understand what the ion is made of and what are their distribution. And I fully can recommend that these kind of measurements are conducted in India in different kind of environments. It doesn't have to necessarily be the spin.
Yeah.
Because what can be done is normal offline filter collection, and those filters are then analyzed for the ion activity. There are quite simple methods for doing that, and we'd be very happy to give pointers and facilitate this work.
Okay, yeah, thank you. I think so. Spin advantage is only the continuous online measurements, but there are problems with the spin that we cannot go to high temperatures, below minus 25 as of now. We also have parallelly started collecting samples in central India and to analyze it in offline. Yeah, so.
No, I think in the interest of time. Okay.
So, see, increased CCN, they reduce the cloud effective radius. That is the normal Tommy effects that you have observed. Have you observed something like anti-Tommy effect in which for some of the particles, the increased CCN is actually increasing the cloud?
Yeah, so that is also there. I think in some cases we also noted there is a paper also by anti-Tommy effect reporting. Even from satellite data, many people are also seeing that there is an increase in aerosol load and increase in effective radius. I think it mainly depends on how we will see the liquid water. Yeah. So even our some aircraft observations were suggesting that there are anti-Tommy effect in some conditions. But it's not very. Still, there are uncertainty in that.
Okay, thank you, Dr. Pandituri, once again.
Thank you.
So our next speaker is Professor Chandan Sarangi.
Hello. I would say I'm waiting for 2 seconds to say good afternoon to all. And thank you very much, Dr. Kanavade and Dr. Huda, for inviting me at this esteemed platform. I have been hearing the entire discussion since yesterday, and it's quite stimulating. And you would see I have twisted my topic also, because I want it to be more relevant about what we are discussing. At the same time, I thank Dr. Pandithurai to set up the platform and the questions from audience also. I see a question about vertical distribution. I will talk about it. I see a question about CCN, anti-Tommy and non-CCN microphysical effect. I will talk about it. So what I want to say is, since yesterday we are talking about measurements at local scale, we are trying to, or we are underlining that there is quite uncertainty or deficiency of our mechanistic understanding of how these nano or questions relevant to nano symposium, how they are changing. I want to bring in another complexity. I think since yesterday we are discussing about complexities also. Every speaker is adding a little bit more complexity into the discussion. I'm saying regional emissions, right? You're measuring at one site. How does the regional emissions play or bring into or come into picture when we are discussing this. What I will do, I will show two case studies from my recent studies. One where regional emissions are actually constraining the air quality pattern understanding, and it's the popular case of Delhi, and I will directly go into it without much introduction because everyone knows about it. Second, I have a relevant question. Does, like, since last 10 to 15 years we are continuously seeing observational evidence that aerosol cloud climate is a thing in India. But does this aerosol, and we also know that aerosol emissions are increasing. So do we see a trend in cloud cover based on this increase in emission? These are the two case studies I will discuss, and towards the end I will bring back the questions to our relevant discussions that we are having. So first about the trends. We all know now that India has or specifically Northwest India has a new season. We call it crop residue burning season. And why it's so distinct? Because people are now actually booking or planning their vacations out of Delhi during November to avoid the hazy environment out of it. We know the very basic cause or the basic discussion that goes on is all about the crop residue burning. We have a source region here, and the meteorology favors advection of aerosols or smoke plumes into Delhi microenvironment, and we believe that Delhi high extreme haze conditions episodes that are somehow linked to it. We see model simulations, quite regional model simulations, which go from 20% to even some cases where 70% of the contribution is being identified to it. But at the same time, recent papers, in which Dr. Kanawade is also the first author, we talk about that meteorology is not insignificant. In fact, meteorology can actually determine if it will be a extreme hazy day in Delhi or not. What I want to highlight is last 5 years we have CPCP measurements now, and if I divide the measurements based on the fire count, right, I get satellite fire count. All these points are CPCP measurement of 4 years, 3 years, 2018 to 2020. I divide the days into high fire days and low fire days, and I put two composites out of it, and what you see is here the difference. It's very evident what we all believe. Delhi is getting the burnt, right? The maximum increase in PM 2.5 is happening over Delhi, while the source region is this, correct? This is 3 years of data. Maybe at the first stage I am surprised seeing this spatial pattern. I know Delhi is highly getting polluted by haze, but why there is less increment of PM 2.5 near the source region? That is one question which came to me in the initial part. But then I thought it might be 3 years of data. Let's do a little more due diligence. We went on with, this is machine learning based PM 2.5 estimations of 1 kilometer MAEC data. And if you use the same to again characterize the same days that the same procedure going for low fire days and high fire days, and this is the difference. You still see the same pattern, right? Over the source region it is less, and over the Delhi region the PM 2.5 values are high. So based on this is the general question I have. So if you have the smoke burning happening, it's like, just imagine like a chimney plume, it might be advecting based on meteorology. However, as we know, as it advects, it gets diluted. So why it is that, if we are saying that it's just dispersion or advection, Delhi is getting this spatial pattern, this proportional increase in Delhi, right? In some papers, people have explained that it might be a chimney effect. Whatever we are releasing, it goes up and then subsides near the Delhi region. But why Delhi region? Why not just before that? Why after that? while 20 years of data clearly shows that distinct air shade over Delhi region, right? And what I will show in next 2 slides based on my analysis is that there is actually a plume behavior movement which is happening, and there is the elevated smoke layer which is closely observed in the distinct Delhi air shade during these high days, and which can affect the temperature and local lapse rate so strongly that Delhi, or this could be a strong contributor to the spatial pattern that I am seeing. Trying slightly touching upon the question asked in the previous lecture about the vertical distribution. So this is, another thing, all the 2 plots I showed before, these are daily measurements. So I wanted to see if it is more in daytime or night time, the increase that we are seeing over Delhi. So I have taken PM 2.5 measurements which are like 30 stations over Delhi, and I have plotted, I have first divided into 2 composites, smoky days and background days, and this is the diurnal plot. And this is the difference, right? Interestingly, you will see that the increase is maximum during noon time. You see, during basic diurnality understanding, the concentrations or dilution should be maximum in daytime, and we are seeing the diurnal pattern correct. But the difference shows that it is quite high during mid-noon time, and then it persists as the boundary layer also subsides. So this is the first point which indicates there is a role of local atmospheric structure or lapse rate and aerosol temperature interaction. Somehow the smoke plumes are affecting it. I then used, I think 15 years of Calypso data to find out the specific days when the high smoke plumes are transporting from the region, source region towards Delhi. So one is smoky days, blue is background, and the difference. And this is at source region, let's say Punjab, Haryana region, and this is downwind means NCR or Delhi microclimate region. What I am clearly seeing is a elevated layer, right? This is average of many profiles which are collected within those 15 years. This elevate means this is the difference, or this is the enhancement of aerosol as a vertical column when smoky days are prevalent over that region, and this is the same enhancement during the same smoky days but at a higher altitude, right? And the last slide that you are seeing here, this is from radiosonde data. So we have taken radiosonde data, we have calculated the VPT based mixing layer understanding. Again, the difference clearly shows that there is a decrease in mixing layer height. Like in the background, it used to be somewhere around 1 kilometer, and during the smoky days, it comes down to around 0.5 kilometer. And this is again like average of many profiles. This is the row. I think the N count for radiosonde is around 100 or 112. Based on this, and this started to, this is also a plot from radiosonde, the same thing, mixing PM 2.5 and mixing height calculated from radiosonde. We clearly see as the mixing height decreases, the PM 2.5 values increase, right? To confirm this, I have also done a WRF-Chem simulation of a very distinct event where actually the elevated layers, Delhi is seeing elevated layers of these plumes, and I will not go into detail, but clearly you just differentiate these red and black line. So red is, green and black line. So without radiation and biomass burning emissions, which means that we are taking away any interaction with the temperature of atmospheric structure, and then the default. And it's so surprising that the values could be around 50% different. And this is a specific case when the plume is actually located 500 meter above Delhi. It's just passing by Delhi, and this could be an effect. So this is the first case study I was talking about, regional emissions, right? We are measuring over Delhi a lot of things, but are we considering the effect of that regional emissions or the regional thing that is coming into picture? And that regional emission is very well coupled with the atmospheric structure there. Yesterday, Dr. Lubna was mentioning about her chamber experiments where temperature is a constraint, right? If you change temperature, your questions, the growth rate, the NPF, everything changes. So in that context, you see a slight or without regional constraint, you can be missing a lot in Indian context, right? Now, I will go to the second case study I want to emphasize. As I mentioned, like we are seeing regional emissions are changing, increasing over India last 20 years. We also know that aerosol cloud climate is evidently seen in last 10 years of studies. The KIPEX experiment was the first to see the instantaneous effects. Satellite data confirms. Dr. Nair is here, who has also been working on it since long, and we know that there is a aerosol cloud climate. Dr. Dey is also has also worked on this extensively. But my question is, are we not seeing the cloud cover trends? Right, it is changing. So if it is so certain, are we trying to see the cloud cover trend? And this talk will be towards the end. I will try to convince you that we are seeing. That's the thing. This is a study again we did with Dr. Kanavade in 2019. And what we tried to show here is that the increase in high AOD or high pollution days in last 2 decades is highest over southern India, right? Peninsular India or eastern India. And we have just divided the days into percentile of AOD, and this is the number of days when in a season of February, March, April, May, the number of days where 66 percentile of AOD is crossed, right, criteria. And we clearly see this, there is a stiff increase. Followed by this, I also worked on another paper where we used high resolution Miser and MAYAC data, and again the same picture is coming out. These are trends or changes. This eastern region, or we can call central India eastern region, there is a lot of, the enhancement is very high, not absolute values, because absolute values obviously IGP is higher, but the net change is higher. And we know by theoretical understanding that change from clean to slight pollution can be more sensitive in terms of climate compared to mid pollution to high pollution. The sensitivity is more when we change the clean environment to polluted environment. Now this and then we also want to know why it's increasing, and this is a old paper where tracer experiments were done using regional model by Kumar et al. And we can clearly see that it's a regional thing, and if you have tracers in this eastern box, most of the pollution over this eastern coast is being governed by it, right? So it's somehow related to the eastern IGP, most of the contribution. So the enhancement could be due to enhancement of regional emissions in eastern IGP. And is it, first of all, like the first thing, is it showing a relation with temperature trends? So we involved in a paper where we tried to took the same box. What we calculated is change in temperature per unit AOD, and for 20 years. And this is a paper from JNU with Amit Mishra, Dr. Amit Mishra, and Dr. Singh is also co-author sitting here in this paper. And what we clearly see is that the cooling trend is available, and in short, this region can be thought that aerosol is trying to affect the temperature trends very clearly. Then does it also affect the cloud trends? This is also the outflow region, and what we have done is the first decade versus the second decade. This is AOD. We have plotted the composite. You see that the values are strictly changing. This is a Calypso analysis of the same composite. You see in the recent time, the enhancement is at an altitude of 1 to 3 kilometers. it's not at surface that much, like not within the boundary layer, but above boundary layer. And what you are seeing here is the values of AOD summed over only this layer for last, I think 7 to 19, and you can see increasing trend in this, that the AOD over that region at a certain elevated height is increasing. And we know, and if we go and see the cloud cover over that region, the same box, this is level 2 data of MODIS, and again composites into first decade and second decade, this is the difference, and this is the trend. We clearly see that low cloud trends have been clearly increasing over this region, and the difference is very, and this is about occurrence, cloud occurrence, and the difference is very clear. We used temperature profiles from ARIES, and we found that a very clear increase of temperature. This is the difference between those two composites, while the difference of RS shows moisture increase at a lower surface. And so what I am trying to say here, the elevated layer of aerosol, the increase in trend can have a trend in temperature, atmospheric temperature, can increase the stability, can actually enhance the moisture in the boundary layer and affect the marine clouds, and we are seeing a trend in it, right? This trend is strong enough to also be visualized in SST trends. So generally everywhere it's increasing because of our global climate change, but over this box it is actually decreasing. I'm also trying to simulate this, however capturing those trends and also the shallow clouds is a challenge, but I want to believe that this could be a location where constant emission enhancement is being seen. This is a pre-monsoonal time where, as Dr. Pandithorai told, our kappa is too high, hygroscopicity. Measurement shows around 0.2, 0.3. So this can be linked with aerosols and could be a potential region where you see trend associations with it. Just to summarize, we have papers coming out. In the entire discussion, we are seeing that temperature and the composition of VOCs, amines, sulfuric, these are the things which have the drivers for aerosol NPF as well as growth, right? These are actually, you see, people are putting papers where temperature, monsoon driven organics are being accounted or driver for new particle formation. In this context, the two examples we talked about, and if you link it back to your measurements, you will see that there could be a strong connection or driver contributions in it, and to address that we need to have regional model simulations. So at this platform I would also like to encourage, I'm in trying to do some regional simulation at this scale, but I also feel that we should acknowledge the importance of regional models here, and by the next time we should have more. I believe people can have more into this. Thank you.
Thank you, Dr. Sanjeev. So, any quick question?
Very nice talk. I have a few things. See, this burning, I think it's not new. Since 40, 50 years, burning is happening. But why only the recent decade it has been highlighted? If the downward is the, means what you are telling is the right, it should be like 40 to 50 years back also it should be happening. I think that anthropogenic activity and the boundary layer dynamics, it is the what it has to explain, but not only the burning activity. That is first thing. Second thing is you mentioned that trend. You see, the trend is not linear, and that depends upon starting point and ending point. If it is a linear trend, if you put it, I suggest to have the multi-regression analysis, because sometimes it's decreasing, increasing, decreasing. You should remove the background oscillations, natural oscillations, before getting one, before putting any trend in that.
Yes, I agree. Thank you. Like, I also totally believe that the condition has exaggerated because of wind stagnation also in the burning scale. Like every 10 years, our wind is getting calmer over that region. Future 30 years, it will be even more calmer. So the meteorology is a key player, and if we change the meteorology in our models, everything changes if you just tweak it a little bit. So emissions are there, but the transport and the mechanism of transport, these understandings are very essential for the mitigation, definitely. And yes, obviously observations are showing a net relation, but the exact answer will come out of more mechanistic studies only. Without that, we can.
First of all, let me correct it. This phenomena is not 40, 50 year old. It's rather last 15, 20 years that this problem has come up. And why this problem has come up? Because of the government policies that they have restricted the use of groundwater and shifted the date in such a manner that now this the period of wheat to rice to wheat shifting is only 1 month. So the people have to prepare for the land, and there is no other option but to burn it and all that. Added to that, because the sowing season has shifted, and of course the meteorology is there, which is playing a role. So these two have made it complex. So this is a recent phenomena, 2025. But my question is that because you are looking at the changes, with respect to say only the temperature, so and boundary layer, of course. So have you included wind speed and to see that if the ventilation coefficient has a bigger role to play in that, rather than just the boundary layer? That's number one. And the other is that is there some kind of wind shear being generated because of that your temperature change that you have seen?
No, definitely I have looked at it. First thing is we have handpicked the events, high fire and low fire, and we had radio sounds where wind velocities are there. They are not very distinct over that time, and it's stagnant. Like it's not very high. The wind speed is also not high, and also the difference of wind speed is not that much significant. Second, ventilation coefficient itself has the PBL height merged inherent into that formula. So yes, the net in a nutshell, ventilation coefficient is decreasing because our mixing height is decreasing, so ventilation coefficient is decreasing. And wind shear, obviously I have not seen, because this is just what we are talking is 1.5 kilometer, and what is changing is 500 meters. So without this high resolution LIDAR observation, we might not see it, and having more LIDAR observations like over that region might also confirm and give us more events to compare and understand.
About this interesting discussion and move ahead. Thank you again, Dr. Sharan.
Thank you.
So next speaker is Dr. Andy.
Okay, so thank you. I'd like to comment earlier that each presentation is making our life more complicated, or our seminar more complicated, and maybe I will try to simplify then a bit. So I will show something that we are doing at Pallastuntuри in Finland, and for us the process studies basically were made years ago. And I remember when I was a PhD student, and there was always some old professor who said that, but we did this 20 years ago. And now I noticed that I'm one of those, which is not a good thing, because we need to keep up with the development. But yes, so not only my study, of course, there are plenty of collaborators and people in our unit, in our group, who are making these measurements. And let's sit back and relax and see what we have there. First, I'd like to introduce the Global Atmosphere Watch concept, which is from WMO. Those who don't know, basically there are global stations around the world who are mandated to monitor the state of our atmosphere. So to say that, how is our planet's atmosphere doing? Is everything going well, or is something going the way it should not go? And our Pallas Tunturi station is one of those global atmospheric watch stations, and it's one of only the 4 stations that are above the Arctic Circle. And we started measurements in '95 and aerosol measurements in '96. And nowadays you cannot discuss global and European measurements without mentioning 2 research infrastructures, which is the ICOS, that is for greenhouse gases, and ACTRIS, which is for aerosols and trace gases. And really the idea behind these infrastructures is that we do quality assured measurements and in the same manner at all the stations where we are. This is a wintertime picture from Pallas Tunturi. You can see that there is basically nothing around here, only snow. It's an ideal background location inside a national park, which is quite large, and in such it represents a larger subarctic area. And what is important here to understand that we have a unique opportunity to also study aerosol cloud interactions, because the station, which is on a hill about 560 meters above the sea level, is occasionally inside low-level clouds. These kind of stratocumulus clouds, and I will show a bit later how they look like. About the history of in situ measurements that we have done at Pallas, and also for aerosols and clouds. So, like I said, in '96 we started. That was the basic aerosol number concentration that we measured then. And then also at the same time we were measuring the visibility with basically a Vaisala present weather sensor. In 2000 we added aerosol number size distribution measurements and a nephelometer. So now already 23 years of data series is available there. And then in 2002 we actually took into use this fact that we are inside low-level clouds, and we made a new station inlet so that we can study the clouds. Previously we had a PM cutoff, but with this inlet we were measuring, collecting the total aerosol and then gently evaporating the water so that we could also collect the cloud droplets. Soon after we started biannual campaigns of cloud droplet size distribution and other cloud properties. And 2005 added black carbon measurements. And then of course plenty of stuff happened in between here, but I'm just adding some of the most important additions. And now in 2022 these sort of campaign-based measurements of the cloud droplet size distribution were made continuous. To have an idea what kind of aerosol we have there at the site, here you can see long-term particle number concentration evolution. First, in a linear scale, you can see that the maximum concentrations are around some thousands, maybe 10,000 maximum. But what's important to understand in Pallas is that if you look at that from a log scale, then you actually have these, let's see, maybe I'll point this one. You actually see that there are plenty of low concentrations. What happens here at Pallas is that we have the low concentrations in the winter time, because really we don't have any local sources. And then in the summertime what we have is biogenic organic compounds. So that's mostly what is doing that. It's nothing to do with anthropogenic stuff. It's natural aerosol that is increasing the particle number concentration. So secondary aerosol formation, basically. And like I said, that we've sort of done most of our process studies, and now where the focus at the moment really is to take these long-term time series data into use. And this is to support IPCC assessment as an example. And this is just provides now an overview of the particle number concentration in different sites around the world, where Pallas, you can see, is, okay, now it's a part of it. I'll show here. It's one of the lowest stations. But what you can see here is there's this large variability in the Pallas data, which is the natural variability in aerosol concentration. And at polar sites, the yearly median concentrations are in the order of some hundreds of particles per cubic centimeter. So you can understand that it's pretty low. Of course, IPCC is interested in optical properties. You remember we have long-term optical properties of both scattering and absorption. If you look at the scattering, again, Pallas is very low compared to the other stations. And this is now a so-called base year 2017 that has been picked for the latest IPCC evaluation work from these kind of network stations. For absorption, actually, sorry, that was the absorption, and this is the scattering. For the scattering, Pallas is not there for the year 2017, and the reason is that even for the long-term studies that you do, sometimes you have break in the instruments and break in the date. And when IPCC report assessment studies are collected, they are very, very rigorous in what kind of data they accept. So Pallas unfortunately did not make that comparison, but in another study we compared against some Arctic stations that you can see here for the scattering, and Pallas is around the same level concentration as Barrow. If we take Barrow over here, here would be Barrow, so roughly again at the same levels. The long-term trends in aerosol optical properties. At many stations around the world, they have been decreasing because of the decreasing emissions. At Pallas, we don't really see from our data series any trend. This is no significant trend, but for scattering, we actually see a slight increase for the long term. And it's the same as in Svalbard. And basically this has to do with air masses distribution being different with the evolution of time. But most of the stations around the world, they show decreasing trend also for the scattering. Which makes, if we turn it into single scattering albedo, we can see that at Pallas we have a slightly increasing single scattering albedo, so sort of a brightening the aerosol at the station. Okay, now I get into the cloud business a little bit more, and I will tell about these measurements that we do. So what most of us well know here is that when you have a cesium particle with a typical size of between 50 to 400 nanometers, then you have a situation where you have supersaturation, you get condensation, and a cloud droplet forms that is between 5 and 50 micrometers in size. And that's exactly now what we have basically utilized in our the size difference in our approach, how we want to study this. So basically, we build, like I said, we build an inlet that takes in all the particles, including the cloud droplets, evaporates them slightly, so we can see what was the so-called total aerosol. And in this graph, total aerosol size distribution would be something like this. And then we take another inlet where we have outside ambient air, we have let's say PM 2.5 cutoff. So we cut here, which means that we don't collect these guys at all. And that would be your size distribution then looking something like this. So in principle, from that you miss all the activated particles, and now if you subtract interstitial from the total aerosol size distribution, you get a size distribution of the activated particles. So basically these vary your CCN, right? What you can also do is you can, for those particles, you can deduct a so-called D50 diameter, so the diameter at which 50% of the particles were activated. In this case, it would be around 50 nanometers. So you can see the 8 mode particles get activated at pulse. What we then did was that we took this information and we calculated from this D50 diameter, basically the CCN concentrations for a certain period of time. I won't go into details because we want to make a little bit more studies out of that. But what we get is CCN concentration, long-term data set, not in some artificial supersaturation, but actually in the supersaturation of the actual clouds. It also equals that this is basically the cloud droplet number size distributions, number concentrations, sorry. And you can see that they go from one particle, roughly 1 particle per cubic centimeter, up to about 1,000 particles, 1,000 cloud droplets per cubic centimeter. And you can see a trend. There's been a trend of about a little bit less than 20% decrease during this time. To get an idea what the clouds look like, this is a typical situation. So this is an image taken from a drone, and our station where we make the measurements is here. So you can really see that we are not measuring something local orographic cloud, but we are measuring this kind of a large scale, mesosynoptic scale stratocumulus clouds. Of course, we want to look into more detail. So, like I said, that we made these biannual campaigns. Since 2004 we started, and we have made 9 campaigns in total. We always hit our campaign times in the autumn, because that's when you have the maximum clouds present. About 30 to 40% of the time you are in cloud. And we measure all of these parameters that you can imagine a little bit more. And we always have international collaborators with us who are interested in these kind of studies, and they come with their own research plan, and they measure, for example, they can measure with aerosol lidars or cloud radars, or make ice nuclei measurement with spin, and so on. And by the way, this guy over here now is this continuous cloud droplet measurement sensor nowadays that we are using. It's from German Pallas company. Also balloon measurements with tethered balloon, but nothing as fancy as ISRO. And now, based on those campaigns, just maybe one highlight result that we have. So this is the size distribution of the cloud droplets in different kind of air masses. And I highlight 2 of them. I highlight the Arctic air mass, and I highlight the southern air mass, so continental air mass. So when the Arctic air mass you have here is very clean, about 20 cloud droplets per cubic centimeter, and you have the grown to a little bit larger sizes, more than 10 micrometers easily, being the effective diameter of the droplets. But when you have the continental air masses, when you have a little bit more stuff coming in from the lower latitudes, then you also have smaller sized particles, smaller sized cloud droplets, less than 10 micrometers in size. And now I still turn into one corner, because if you remember, I showed that we have this visibility sensor since the very early stages of what we had in Pallas. So the question is, of course, that there has been climate change, and there has been climate change in Arctic areas, happens 4 times faster than anywhere else. So do we see any effect at Pallas? And the answer is yes. So this visibility sensor reading can be basically converted into extinction coefficient measurements. And then what we've done is we've taken a conventional cut of saying that less than 1,000 meters in visibility means that you are in cloud. And then we are seeing the
cloud properties that has the extinction coefficient changed. And there you can see a slight slope. Maybe it's not so visible there, but looking at the numbers, there's a statistically significant decrease of 16% in cloud extinction. My last slide, basically. What about nano? Because this was also one of the questions that we wanted to see the new particle formation. And this is now just one case example that we have. What you have in this picture is a timeline. So basically there is 3 days of data is here on the x-axis, and then what you have is interstitial size distribution. Then you have cloud droplet size distribution. Then you have rain droplet size distribution. Let's start with this middle guy, because here we can see new particle formation quite clearly, right? And you can see that there is basically no rain, a little bit of something, but basically no cloud, and these particles are growing. And there's another event then coming. But then what happens is that we have a cloud coming in, but actually we should say that it's not the cloud maybe coming in, but we have the particles disappearing here. You can see that there is a bit of a hole. If you look at the previous day's data from here, you can see the hole even more prominent. And these are the activated particles, right? They are in the interstitial DMBS data, size distribution data. So these are the guys that made into the cloud droplets, but not the size distribution measurement. And they have grown into these cloud droplets that you see here. So in the micrometer size range. And actually what you then even see is the rain droplets coming in. So you can see the cloud droplets raining down, which means that in this one figure, as an example, you see the full life cycle of an aerosol particle starting from the gas phase condensation and coming down as rain. My conclusions, I won't go through them because I probably said it already, but the take-home message is that if we see in an area, Palastunturi, where the sort of changes in aerosols have been modest in the last 20 years, and if we take this sort of same process level phenomena to India, you can understand that these kind of issues are prominent here and they are happening in the atmosphere. Thank you.
Yeah, thank you, Dr. Antti. Any question? Yes, please.
Thank you for the nice talk. I have a question related to the Global Atmospheric Watch site. So, is that how this is being decided? Like the data is being taken into IPCC report, so that's super important. How that? Can you comment on that?
How do you mean? What is your question related to?
So my question is, do you have any idea how this? So, like out of those 28 sites, how that is being? Is there any criteria for that Global Atmospheric Watch site? Because there.
Yes, for the Global Atmospheric Watch site, there are criteria given by the WMO that if you fulfill and you submit your application, you may become a Global Atmospheric Watch station. Then if we come into these, let's see, these kind of studies,
yeah.
Then, well, this was a coordinated effort from Europe, basically, that we did, and it includes more than just the Global Atmospheric Watch station.
Okay.
They gathered data from anywhere they could get hands on. So also, for example, there are some stations in India that are belonging here. I cannot now found it, but at least the measurements from Mukteswar were part of, maybe not this one, because 2017 there were.
Yeah, I think I saw that was in mountain region.
Yeah.
I can just supplement that. Yeah. They do have a strict, as Dr. Varshney mentioned, that they have strict policy to have a time series of continuous measurement for the 10 years. That's their baseline. And we do have couple of locations in India, and of course Mukteshwar at the high altitude, FMI and Delhi made the measurements, but it was around 9 years. So with the lack of 1 year, it is not really clear.
I see. Okay. Thank you.
For the nice talk. I have a question in this and next slide. Hey, it's just whatever you were showing, yes. So here you are showing this forest mixed, pristine, rural and urban.
Yep.
But if you see the absorption, means your mixed has lower absorption than the pristine side.
No, it can happen. It can happen.
So means I could not follow this. Why is it so?
Well, there are some sites that are, let's say, for example, Jungfraujoch. This is a mountain site. So in that sense, it is there as a mixed, because it can experience both kind of conditions. As you can see there in the mixed site, it has very large variability in the rate. But mountain sites typically have lower concentrations because they're in the free troposphere often. So.
Even lower than the pristine sites, whatever it
yes.
is.
Yes.
Okay, so last question from Dr. Sarang.
So means I'm still more. I thought this is still more complex than simplified thing.
Oh, sorry.
So I have a simple theoretical question. Like, so we are seeing that CCN is activation is decreasing, and in the last slide, I think you hinted about new particle formation, forming CCN and then clouds. So means simple question, like which we have discussing since yesterday also, like this new particle formation, how much or what is the percentage that we know CCN can increase, but up to number cloud droplet number, how much percentage contribution you believe that this NPFs can reach at a climatic scale, not instantaneous?
Yeah.
That's what coming to my mind. You can comment just.
It's an excellent question and worth for a follow-up study for sure. At this moment we are still submitting this long-term CCN, but for sure the next step would be to quantify how much of that is from new particle formation. Thanks for the comment.
Okay, thank you again. Dr. Antti, nice presentation. So we'll have now the 3 lightning talks. Yeah.
Okay, thank you, Professor Day, for chairing the session. Let's first congratulate all the poster selectee. Out of those, only 3 will get chance for give a presentation. I'm sorry I forgot to do that earlier. So we'll go ahead with M. Deva Prasad. Yeah. Yeah, so you have 5 minutes exactly.
Okay. First of all, thank you, organizing committee, for selecting my abstract, and the judges for giving me option to give a post and talk here. So I am a PhD student from PRL. I am working with Professor Neeraj Rastogi, and this is a part of my PhD. I am basically working on carbonaceous aerosol to understand the sources, what are the sources of carbonaceous aerosol and the processes that are happening to its formation. So I during 2020 and winter to summer, like November 2020 to June 2021, I collected PM 2.5 samples from Ahmedabad and to understand the carbonaceous aerosol characteristics. So what the main focus I'm doing is I'm using carbon isotopes. That is, carbon has three isotopes, 12C, 13C, and 14C. In that, this 14C, it is radiogenic. So using 14C, we can tell how much of the carbonaceous aerosol is like coming from fossil sources and non-fossil sources. So I'm using 14C to estimate the contribution of that, and 13C, delta 13C, the determination. This is mostly used in like a geochemistry, geochronology and all to understand the processes affecting. So in carbonaceous aerosol also we can use the processes affecting to the carbonaceous aerosol. So this is the time series of both concentration of PM 2.5 and this axis, which is F by O. F by O means percentage of carbonaceous aerosol coming from biomass burning or biogenic sources. So if you see here, like around 65% of the carbonaceous aerosol during winter, post-monsoon and winter is from biomass or biogenic sources. And when it is coming to the summer, it is reducing to around 45% in Ahmedabad. Here in Ahmedabad, like PM 2.5 concentration is like 100 to 94, like 82 and 35 during like a post-monsoon, winter and spring and summer. Most of the time it is like more than 60 microgram per meter cube. That is like an average national ambient air quality standard. And in a post-monsoon, winter and summer, this is mainly like, what carbonaceous aerosol contributing more, and in summer mostly water soluble ionic species, mostly sulfates are contributing more in PM 2.5. And this is a correlation plot. This radiocarbon derived F by O, I correlated with some other biomass burning traces, that is potassium and BC 370 by 880 ratio. It's not much clear here. So we are getting good correlation, and this slope we compared with our previous study, that is we did the radiocarbon measurement and this potassium and BC 370 measurements in Patiala. That was like a biomass burning time and mostly pyroticity burning. That there mostly the carbonaceous aerosol are primary. But in Ahmedabad, this is mostly secondary. So the slope is nearly 6 times lower in Ahmedabad. That's it, that in Ahmedabad, rather than primary, most are secondary sources. So to understand that, I plotted both the F by O, radiocarbon F by O, and delta 13C. 13C tells the processes that undergone. So I see here, like in this, like if you see here, these are mostly winter samples. Winter samples have mostly 65% of biomass derived carbonaceous aerosol, which have a very varying delta 13C value. This is like a minus 26 to around a minus 25. That means like whatever carbonaceous aerosol reaching in Ahmedabad, they are mostly oxidized. So if you see in this, like here, this during winter the air masses are mostly transported from this IGP to Ahmedabad, and it is going to the Arabian Sea. So when I check the back trajectory, most of the carbonaceous aerosol coming from this, here you can see the high AOD also coming transported from here. So that is causing this aging of the carbonaceous aerosol in summer. So that is supported by this WSOCB OC ratio also, this color, and this it's a circle size shows the F44 fraction. F44 fraction that we got from the offline AMS analysis. So okay, offline AMS analysis, and so and similarly in summer we have depleted delta 13C around minus 27, and because here fossil fraction is like biomass concentration 45 to 55%. So there also we are getting significant WSOCB OC concentration and a lower F44 fraction. That means like in summer, like secondary organ corrosive formation, that is also dominating. That is shown here. So summer is like Ahmedabad is a highly polluted environment, and carbonaceous aerosol mostly contributing in winter, post monsoon and spring, and summer it is mostly like water soluble ionic species. And this correlation in the absence of radiocarbon measurement, this potassium and BC 370 by 880 ratio, those people are already using, that we are supporting with our study. And in Ahmedabad also, like this oxidized aerosol and primary aerosol, like in Ahmedabad there is a variable sources of carbonaceous aerosol. These are the summary. Thank you.
Next,
Okay, so yeah, good afternoon. First of all, thank you all the selection committee and conveners for selecting my poster. So my name is Arun. I'm coming from IIT Madras, and I have been doing a research on understanding how aerosol loading is having an impact on the fog layer. So each year over the IGPU, the news headlines goes up saying that there is huge disruptions in the day-to-day lives. And this is mainly caused by the fog layer that forms because of the regional meteorology. Now, there is a general consensus that the aerosol loading is also increasing at this point, but to what extent does this fog occurrence is changing, or to what extent does the aerosol influences this fog occurrences have not been attempted before. So here, what we do is, if you take a typical fog layer that you see from MODIS, and you take a cross section along this line, what the calypso sees is that there is a clear demarcation between the fog layer and an aerosol loading lying right above it. So from these profiles, what I do is that I isolate the fog layer by simply giving a distinct identification factor that the base of this fog is touching the surface. And using that criteria, what we get is that most of the samples of the cloud samples that I got by giving this criteria was that the top height was between 0.2 to 0.8 kilometers. Within this, this fog layer is also accompanied by this aerosol loading laying above, and I just I find out the AOD as well. To understand how this AOD affects the top height, what we do is we simply see a regression, we plot a regression plot. Okay, 1 second. Okay, so yeah, what we find is that the top height is increasing by about 40 to 42% as the aerosol loading above the fog is also increasing. In general, what happens is that when there is a high amount of aerosols lying above the fog, the top extent increases from 0.4 to 0.6. The percentage of occurrences increases, while shallow fog does not. They tend to reduce. So to understand why this kind of things are happening is that we did a set of WRF-Chem simulations. First of all, we were able to couple the chemistry for the first time with WRF, and were able to simulate fog for the first time. And this shows the 3-day averaged fog top height, which is very well matching with the observed quantities, and did a set of sensitivity experiments to understand the changes in the fog top height as the aerosol loading changes. What we find is that there is a clear acceptance with the observation. We find that there is a top height increasing by 0.1 to 0.15 kilometers as the aerosol loading has increased. Now, these are actually preliminary results, and we are in preparation of a new manuscript that includes all the information of what model we have chosen and how the what parameterization combinations that we have done. And that's all. Thank you.
Okay. So good afternoon all. My name is Subrata Mukherjee. So I am working at IITM under Dr. G. Pandithurai. So my title of my presentation is like estimation of aerosol volatility and associated chemical characteristics, change in associated chemical characteristics over an high altitude forested site at Mahabaleshwar in Western Ghats, India. So like why this volatility is important, because volatility is one of the like important physical parameters that determines whether that organics and inorganic species will be in gaseous phase or in the aerosol phase. And we know that organics and sulfates are the most contributor in terms of submicron aerosol range, because submicron aerosols are very important because it contributes to aerosol in terms of numbers more, and we know that numbers are more important because it will eventually contribute to a CCN and hence cloud formations. So because we need to know this volatility, because this volatility will add more uncertainties in predicting ambient aerosols. If we want to model, so it will add more uncertainties and biases into the model if we don't know the volatility. So with that background, I have posed two objectives. So I wanted to find the volatility of different chemical species in submicron aerosol range, and I tried to see more insights of these chemical species, mostly in organics, because it is contributing more than 60%. So in order to do that, actually what I have done, I have set up one experiment like combining thermal denuder system. So which thermal denuder system is a system we can set some defined temperature at high temperature, and I have coupled this thermal denuder system with high resolution time of flight aerosol mass spectrometer and with the SMPS. So HAT of AMS is giving chemical compositions, and this SMPS will give us size distribution. So I have two lines like with a switching valve of 10 minutes. So one will be like directly sampling ambient airs, one will be through the denuded air, and for denuded air I have kept the temperature at 150 degree just to see the how much volatility volatile species are there. Okay, so in terms of results, if we see actually for organics, the extent of volatility is around 54%, and the maximum volatility I have seen for inorganic species, mostly nitrate, it is about like 18%, followed by ammonium, it is about like 60%, and the lowest volatility was seen for sulfate, because sulfate being the least volatile ones, it will tend to remain in the aerosol phase. So in terms of percentage of contributions, so organics reduced from 7% to 41%, and the sulfate enhanced from 33% to 47%. So in the course of denuded samples. So we also try to see whether whatever measurements we are doing, ambient and volatility, whether it's comparable within our atmospheric range, whatever is reported in literature. So we try to plot this fraction of 44 by 43 and try to see whether it is in the defined range or not. And we found out that it is in the defined range. And we have also tried to see whatever molecular markers are there, like hydrocarbons, we know that it is more volatile ones as compared to oxygenated ones. So, but what we found out basically, the hydrocarbons are having similar volatilities as of oxygenated ones. So we tried to dig into further more. For that, actually, what we did positive matrix factorization. It is a technique, statistical technique to identify different sources, and we found out almost 4 sources, including HOA, BBOA, semi-volatile ones, and low volatile oxygenated organic aerosols. So HOA and BBOA being the more hydrocarbon-like ones, it should have more volatility as compared to other two, like SBOA or LBOA. But interestingly, what we found out basically, we found out SBOAs are more getting evaporated in the course of denuding as compared to HOA and BBOA. So we try to make one hypothesis out of it, because the experiment I have set up in winter season. So the air mass is mostly coming from the land origins. So it will be mostly laden with the emissions in course of its transport towards our observation site. So there will be lot of SBOA generation, and eventually it will be coated onto the pre-existing aerosols. So that's why we may be getting this kind of SBOA are getting more evaporated as compared to a BBOA or HOA. So in that course, actually, I want to emphasize that the processing of atmospheric processings of these organic aerosols into the form of SVOA can modulate these aerosol properties, and it can in turn affect CCN abilities also. So thank you.
Our next session is aerosol climate interaction. I request Professor Chandan Sarangi to chair the session.
So we have three invited talks in this session, and I would like to invite first Dr. Sachidanand Singh from NPL, Delhi, and following that we have Dr. Vijay Kumar Nair from VSSC Trivandrum, and then Dr. Ramakrishna Rami Setti, and we'll start, and one by one I will definitely invite, but first of all, Dr. Sachidanand Singh. Yes.
Okay. So, good afternoon, and let me thank Dr. Kanavade and Dr. Uda for giving this opportunity to speak in this NANO Symposium 2023. So, I will try to loosely follow this outline, starting with the introduction and finally to conclusion. So as we all know that the atmospheric aerosols are minute particles, solid or liquid, suspended in atmosphere. They change Earth's energy balance, trigger climate change, affect clouds and surface reflectivity, so on and so forth. They can be primary and secondary, natural, anthropogenic, and depending upon various sources, there is a huge contribution of it per year. Although this is old data, but still it's a huge number to contribute in the atmosphere. And the residence time, as you are aware, in the troposphere is around 5 to 7 days. And if you take mean wind speed around 16 to 17 kilometers per hour, so roughly they travel a distance of about 2,000 to 3,000 kilometers in the atmosphere. And that is why they make impact not only from the area of their origin, but also at a very long distance. In the stratosphere, the residence time is something from a few months to a few years, and that is why they affect very much there. Now, the contribution of these can be assessed from the point of view that if we compare it from 1850 levels, then just between 2005 to 2015, in 10 years, the anthropogenic aerosols have increased the scattering and absorption by something around 14 to 30%, and the cloud droplet numbers have increased to something from 5 to 17%. And these obviously will exert the atmospheric forcing, radiative forcing, and they are supposed to be offsetting the radiative forcing by greenhouse gases, something in the range of 20 to 50%. Now again, just for the sake of completion, this describes the whole process, how the aerosols modify the Earth's radiation budget, and they directly scatter and absorb by scattering and absorption, which is the direct process. But indirectly, they change the cloud microphysics and also change the droplet in the clouds, which is called the aerosol cloud interaction. And they also affect the reflectivity of the surface. Now, this aerosol cloud interaction, we have already seen in the previous earlier lecture by Dr. Pandidurai and all, that it is very easy to see the Tommy effect, which is that when we increase the number concentration by CCN, then the droplet radius goes down, and that is the Tommy effect, which is very obvious in the normal water clouds, you can say, or liquid clouds, but it is also there in the in case of ice clouds, where although this phenomena is not very one can be very sure, but they are still there. Anyway, where is the point? Yeah. Like in the ice cloud also, the Tommy effect is there, but it is not to that extent which it is in the water cloud or liquid clouds. So if we see the various IPCC reports, then this is the because in the starting from the second assessment report, the estimation of aerosol radiation interaction and aerosol cloud interaction global picture is given, but up to fourth assessment report, the effective radiative forcing were not being taken into account. But after fourth and fifth ARF, because now there is more focus on understanding the process, so there is a improvement in the uncertainty and also the level of forcing. Now, this is how the aerosol instantaneous radiative forcing and the other forcings are defined. The instantaneous forcing is nothing but here the atmospheric temperatures are fixed everywhere, as you can see from this plot 1. Then there is a stratospheric adjusted radiative forcing, SARF, which allows the stratospheric temperature to adjust. Similarly, the other process is when the atmospheric temperature is adjusted everywhere with surface temperature remaining fixed, as in this case. But in the particularly in year 5 and year 6, here the adjustment in the temperature change at the surface is also taken into account, and that is how the forcing is estimated. But for most of the purposes, the aerosol constituents, the atmospheric adjustment is so little that in this case the radiative forcing or particularly the instantaneous radiative forcing is calculated at the top of the atmosphere. And here the tropopause can be substituted. So the in this case there is no need of stratospheric adjustment. And the instantaneous radiative forcing is in that case simply defined as the net change in flux at any level in the atmosphere. That is, we have to only consider the flux change taking down minus up into account. And here is a recent study kind of in which the global distribution of aerosol radiative forcing was estimated. And why I have taken this is because this time frame is around 2001 to 2017, and which matches with our studies. And you can see that the global average atmospheric warming over the land is almost double the global average warming taken into the global perspective. So, which it is from 4 watt to almost 9 watt per meter square. And then there are hot spots like Africa, Southeast Asia, China, and including the Indo-Gangetic Plain. And also the top of the atmosphere and surface, it has a warming trend, linear warming trend, but in the atmosphere there is slightly cooling trend which has been observed during this period. Now coming to India, over the same time frame, almost 2000 to 2016 that we have studied. Of course, there is a total AOD which is consistently showing an increase on per year or per decadal range. And then the increasing trend you can see is in AOD is mainly because of the spherical particles which are increasing over the time. And also if you see the trends in the particle size, then it is the increase in total AOD is mainly because of the spherical and urban, basically industrial generated pollutants, which are smaller in size, and they are increasing over this time frame. So it is because of these we are having increase in the aerosol concentration. The similar trend is also when we take only the IGP into perspective. So here you can see that the highest increase in AOD is found in the lower IGP region, where of course the industrialization is increasing over the time, and the anthropogenic activities are more. Then there is a decreasing AOD trend in the northwestern region and some of the part of the central south, and which is mainly because the dust storm activities during this period has actually decreased. So that is why there is a decrease in the western region, western part. There is a decreasing trend. And then also you can see that there is a trend in the cloud optical depth, which is also varying from the west to east, and it is changing from minus 0.5 to plus 0.6 in terms of cloud optical depth into the entire region. And obviously this will have effect on the radiation. So the short wave as well as part radiation both are seen to have effect of the order of minus 5 to 5 watt per meter square. So these are some individual stations at which again the increasing trend is there. Also this is compared with the aerosol properties from the aeronet stations which are lying in the IGP. And the interesting thing is that there is a linear increase in the various aerosol parameters like cloud, like fine mode fraction, angstrom exponent, then the absorbing aerosol. So you can see that these stations are actually aligned from west to east, and they are increasing here, slight increasing trend. Again, angstrom exponent, absorption aerosol optical depth, and this is the refractive index, which is imaginary part of the refractive index. So all this indicates that there is a systematically increase from west to east IGP in the absorbing aerosols, and their concentration is increasing. But overall, if you see the entire region, the fine mode fraction is still below 0.5 in the overall region for at all the stations, which predominantly shows that there are coarse particles which are dominating in the IGP region. Now, there are various types of aerosols which are available in this IGP, or at least they can be categorized in terms of mostly dust. It can be mostly black carbon, and then the mixed phase of BC and dust. So in the western side, which are, say, Karachi and Jaipur-like stations, mostly dust and mixed BC and dust kind of aerosols dominate. In the eastern region, like Kanpur and others, which are heavily industrialized, there we'll find the mostly black carbon and mixed, again, BC and dust kind of aerosols. So for example, in the Gandhi College, which is at the most eastern part of the region, you'll hardly find the dust-dominated aerosols over there. So the absorbing aerosols increase in also the season-wise, pre-monsoon period. These absorbing aerosols are more compared to the other winter season. If you look at the vertical profile of the aerosols in the IGP region, then if you see, if you study the color ratio and the depolarization ratio, so the color ratio will give you the size of the aerosols, depolarization, again, the shape of the aerosol. So if you study it closely, then in 1 to 4 kilometer range, you can see that the large particles with high color ratio and non-spherical particles with high depolarization ratio overall dominate in the 1 to 4 kilometer region in the IGP. Then if we study the what are the types of various clouds and what is the cloud vertical structure in the endogangetic plane, then over this long period of time, we find all kinds of clouds are found in this region. Almost every kind of clouds, but the high-level clouds, particularly the cirrostratus and deep convective clouds, they dominate in the IGP region. The cloud vertical structure is very much different in the monsoon season compared to the other seasons in the IGP, and they are also different if you compare them from the urban agglomerates and the normal average IGP region. So in the urban areas, the cloud structure is far more different than the other IGP regions. And the average depth of single layer aerosols, single layer clouds over the IGP is actually higher. It is around 2.5 to 5 kilometers. But in the urban areas, it is at lower level, 1.8 to around 2.7 kilometers. So that is how the different cloud types and their vertical structures can be seen in the endogangetic plane. This is again about the vertical structure of different clouds in the region. Now, if we see that how these aerosol cloud interaction, what impact it is having in the entire endogangetic plane during the same period almost. So here we have studied the aerosol optical depth due to small particles, which is small means less than 0.35 micron, and the large particles which are greater than 0.7 microns. So how they are interacting with the clouds. So different cloud parameters were studied against these two types of AODs. So the cloud fraction, then cloud optical thickness and other parameters were studied. So the cloud fraction increases with increasing AOD in general, But then there is negative correlation between aerosol optical depth and cloud optical thickness, and which is against the first indirect principle, indirect effect that we know as a Tommy effect. So this we call it as an anti-Tommy effect. Also, the cloud effective radius in the liquid phase only we have studied, no ice phase. So here it is negatively correlated with the small size aerosols, which is basically the Tommy effect we are aware of. But there are the processes, there are where we see positive correlation with the aerosol optical depth, particularly with the larger particles, and which is sort of the anti-Tommy effect that can be seen here. If different clouds are studied against the same parameters, same small and large aerosols, and they are not very different. So irrespective of the cloud types, the larger particle aerosol optical depth are negatively correlated with the cloud effective radius in the liquid phase compared to large. So the similar anti-Tommy effect is everywhere reflected. Okay, so this already explained earlier. The elevated aerosol layers in the IGP region, they are affecting they are causing the tropospheric cooling. And also these aerosol-induced tropospheric cooling, it increases with the increase in cloud coverage. And the aerosol cloud interaction further contributes to the lowering of the tropospheric cooling. So it is a kind of cycle which is set in, and again the aerosol-induced lower tropospheric cooling will affect the cloud distribution and cloud dynamics. So it becomes feedback which keeps on generating and changing the cloud parameters. Then coming to the aerosol indirect effect, which was also studied in the IGP region. So here we studied aerosol indirect effect in different cloud thickness with different liquid water phase, liquid water content. And for different liquid water path, you can see that the average aerosol indirect effect over all liquid water path is high for compared to the smaller particles. And the highest positive aerosol indirect effect is observed for the small particles, which you can say these small particles are causing more aerosol indirect effect compared to the large particles. And the aerosol indirect effect is for very thin clouds, that is the low liquid water path, it is negatively correlated with the negatively correlated in case of the thin clouds. Then coming to the aerosol cloud radiation interaction at IGP, we try to find out the cloud forcing. And the cloud radiative forcing for short wave, long wave, and net forcing using this formula, which is a standard one. This is the ongoing work which is going on. And you can see that if you study this during monsoon and summer, in summer you can see this frequency of distribution and the fit, they are at zero level, so which is indicating that there is almost cancellation of short wave, long wave radiative forcing. But it is not so in case of monsoon, and where it is at minus 10 watt per meter square. Similarly, at surface also the behavior is entirely different in summer and monsoon. In monsoon it is very much skewed towards left, and even in atmosphere there is a change in cloud radiative forcing. So the cloud radiative forcing, the difference between the pre-monsoon and post-monsoon, maybe here you can see the pre-monsoon and post-monsoon differences in the top of the atmosphere, different types of radiative forcing, short wave, long wave, and net radiative forcing is very much different. And so much so that the difference in the long wave radiative forcing here, you can say it becomes almost negligible. So that is all about the different aspects of cloud radiation and aerosol interaction, which we have seen in the endogenic plane, and this is the summary of what we have done. I've already spoken almost all of these, so maybe you can have a look on that. So that's all. Thank you. Yeah, these are my students and collaborators. so and funding agencies. So
Thank you.
thanks.
Thank you, Dr. Sim. Any questions? Yeah.
Yeah, thank you. Very good lecture. Just I want to curious to know, how do different cloud types, like from low cloud to high cloud, like stratus, alto stratus, cirrus, so respond to changes in aerosol loading and composition, and how does the effect of earth radiation budget?
See, the aerosol, when they enter the clouds, and it depends upon the what height, if it is lying above the cloud, if the aerosol layer is lying above the cloud, it will have, say, you can imagine it as a dark surface over a bright surface. So in that case, the effect will be maximum, the reflectivity. But if the aerosol layer is lying below, which is itself a dark surface, and the cloud surface is which is the bright surface, which is above that. So it really depends upon the difference in the bright and dark surface combination. If the surface is almost of the same brightness, then the effect on radiative forcing will be almost negligible. In that case, you won't see any change. So whenever there is a contrast, there will be a change in radiative forcing. So that is how it will be.
Any other question? One quick one we can take. Yes.
Sir, like absorbing aerosols, we mostly refer to black carbon. So how about brown carbons, which are also absorbing ones? How to account for that, like radiative forcing?
Yeah, black carbon is maximum absorbing, but there are, say, for example, in Indo-Gangetic plain, if we have dust which is also rich in iron and all, they are also absorbing. So, and then the brown carbon and black carbon, the difference is that they act at different wavelengths, they are absorbing. Black carbon absorbs all the radiation which is falling on it. Brown carbon is not so absorbing compared to that. So obviously their effect when they are mixing with the, say, clouds, then the effects will be entirely different in that case. So the forcing will also be different.
Yeah. Again, thank you, Dr. Singh, for this interesting talk. And with this, I would like to also invite our next speaker, Dr. Vijay Kumar Nair from VSSC. And I believe he will talk more about other absorbing material also in his talk.
Yeah, thank you, Chandan, and I will also join with all the invited speakers to thank Vijay for organizing such a nice conference here. So from where Satyananda Singh sir stopped, we will move a little bit north. We will talk about what is the effect of aerosols over the Himalayan region. So here I will be mostly talking about the snow-covered part of the Himalaya, where how aerosols are going to affect the climate, so how, whether it is relevant. So very broadly I will discuss about that one. So we know that Himalaya is a lot of significance in our regional climate. Probably this has a barrier effect on monsoon, and also it has a thermodynamic feedback on the monsoon, and it provides a lot of fresh water for the billions of people living in the Himalayan, living in the South Asian region. A lot of rivers arise from that one. This is a main freshwater reservoir. So the health of the glaciers over the Himalaya is a major concern. A lot of scientific discussions are happening on that aspect. Whether a micron-sized particle, whether it can contribute something to such a large scale system is a major scientific problem. So we know that Himalaya recently, these are all things to put the things in perspective, what I'm going to talk about. This shows that Himalaya is facing a lot of extreme events, and it's a hot biodiversity point, and it is very vulnerable to the climate change. And recently we have seen a lot of cloud burst and all those things. Whether we can directly attribute this to climate change is a different question, but these are very important as far as the country, India as a country is concerned. So the recent report from compiled by IATM, Sabin's chapter talk about the climate change over the Himalayan region. It clearly shows that the Himalaya has more warming trend than that of the Indian region. So Himalaya is warming much faster. So 1 degree or 2 degree change in the Himalayan region, whether it is going to affect the glaciers over that region is a major concern. So you can see that in any scenario, if you take, we are expecting much more warming in the 2100. Other than that, there is one more important thing. When you look at the vertical distribution of the temperature trend over the Himalayan region, what you see that at higher altitude, it warms more. It's called elevation dependent warming, EDW. That's a major concern. So EDW has a lot of importance over Himalayan region, especially because most of our glaciers are mountain glaciers. So temperature, if it is increasing at a faster rate over the high altitude Himalayas, it can kill a lot of glacier or snow over that region. So all these things make the study over the Himalayan region and its fast melting very relevant. So we will just look at what are the sources and the sinks of aerosols over the Himalaya. We know that there is a lot of hot spots sitting near to the Himalayan region. Lot of anthropogenic aerosols are emitted from the Indo-Gangetic Plain and South Asia. They goes up to the Himalayan region, and there is a dust transport which is coming from the Thar Desert or Middle East or the much western part of that one. These particles can get transported here. With the dry and wet deposition, this particle can deposit on the snow surface. So snow is very white, no doubt about that one. So when we look at the snow which is impacted with the aerosol, it looks something like this way. And in the extreme cases, you can see these are the pictures over the Arctic region. This forcing, the aerosol deposition over the snow surface, is considered as one of the major forcing mechanism over the Arctic region, but we don't know much about over the Indian Himalayan region. So this is the one. So if you look at the spectral albedo, interestingly, the albedo reduction happens mostly in the visible region. So we know that maximum radiation is coming in this region, so it should have a larger radiative forcing. To address this program, we started somewhere in 2011 or 2010, we started this program. So initially it was field expedition to Himalayan glaciers to understand that how much is the BC over that region. So we cannot simply start the program. So we went to the Himalayan glaciers, lot of expedition to the glaciers. We directly went there and measured how much is the black carbon over that region. The another problem is whether the black carbon from the South Asian region, the Indo-Gangetic Plain goes to the Himalaya. So what we did is we took aircraft and we measured the vertical distribution over the IGP region and found that during pre-monsoon time it can go very up in the atmosphere. So these particles can reach the Himalayan region. So after that we started regional climate modeling. So I will be more focusing on this aspect, just touching upon the some of the observations over the Himalayan region. So you can see that these are the observations made from different glaciers. Expedition to glaciers, some of the people may be aware, especially Chandan is aware, it's very, very tough job. So you have to travel at least, you have to do trekking for at least 2-3 days to reach the glacier. Then do some measurements there, 2 or 3 days, then come back. It's a very hectic job. So we did little bit of that one. Don't go for these high values, just to look at the mean value. We are talking about the climate perspective, so just look at the mean value. It will be somewhere around 200 to 100 nanograms of particle in a meter cube of air. This is a pretty big number. If you compare with the Arctic or Antarctic values, earlier it was mentioned, these values are very, very high because we are close to the source regions. And if you see the vertical distribution, it is decreasing with altitude, expected, because the aerosols are mostly at the valley region. So with altitude it is decreasing, and it is peaking during the pre-monsoon time because of the large scale convection. Aerosols are going up in the atmosphere, and if you see the vertical profile, calypso profile, if you see, you can see that there is a lot of aerosols which is lying in the mid-troposphere or upper tropospheric region. Then we did profiling in the snowpack itself. This is a snowpack profiles of aerosols. You can find that even at 1 meter below the surface, you will find lot of black carbon aerosol. It is getting accumulated. It is compared to the atmosphere. In the snow, the aerosol depositing on the snow is, with the time it is accumulating. So what we did is, sorry for this poor quality in the figure. So what we did is we used a regional climate model. It is an Italian model. It has an online aerosol scheme. It has a chemistry model. It has an online aerosol scheme that is connected to a land surface scheme. In the land surface scheme, we have a provision for the deposition of aerosol that is going to affect the albedo of the snow, and it is connected to the radiation. So we call it as a SAE. SAE means snow albedo effect. We can call it as a snow darkening also. Snow is getting darkened, so we call it as a snow albedo effect. And same way you can have a direct effect of aerosol, DRE. Sachin Singh was talking about DRE quite a lot now. So this is called a DRE. DRE means direct effect. These aerosols are in the atmosphere. It is a DRE. When it is at the snow, it is called SAE. So These are the two effects we anticipate. So what I do is I won't spend much time on my result side. This is the one slide where I compile all the results together. So I will spend some time on this one. First, aerosols are getting deposited on the snow surface. Then it changes the albedo. It decreases the albedo significantly in the visible region. Because of that, it leads to some warming. Warming is positive, meaning that it warms the snowpack. When it warms the snowpack, temperature increases. When temperature increases, it reduces the snowpack. We know that the temperature and the snow surface, the snow cover fraction, SCF is snow cover fraction, they are directly linked, because if it increases the temperature, SCF decreases. If SCF decreases, it increases the temperature. It's a positive feedback mechanism. So it goes feedback to the system, so it enhances the initial signal. Because of the increase in temperature at a high altitude, we know that it can change our monsoon pattern. It can change the not monsoon pattern. It can change the rainfall pattern over this region. So same way, this excess melting will change the runoff. So we will have more runoff over the Himalayan region. So the rainfall is also connected to the runoff. So this feedback to the albedo. Because when you have more rainfall, it is coming as a snow over that region. So your albedo will increase. So it gives some sort of a negative response to that one. So this aerosol darkening, surface darkening will change the direct effect of aerosol. The snow darkening due to aerosol deposition has implications on the atmospheric, the way atmospheric aerosols interact with the radiation. So that's a very tricky part. Since snow is melt very fast because of the aerosol, it exposes the land. So that leads to the dust emission. It acts as a new dust source over the Himalayan region. Since it is a new dust is coming into the atmosphere, it has implications on the DRF. And this excess dust can again deposit on the system, and this feedback will continue. This is another forcing feedback mechanism. And finally, this DRF is cooling the surface, and the snow albedo effect is warming the surface. It can compensate the DRE effect. So all these complex processes we can address using a regional climate model only. So there is a lot of positive and negative feedback mechanisms are coming. So what I will do is I will go by one. So finally, I will spend one slide on the elevation dependent warming also. So if you look at the deposition of aerosols over this region, this shows the emission minus deposition. We can see that over the whole Indian region, emission dominates. The deposition dominates over the Himalayan region. Over ocean also, we don't have sources here. So deposition is dominant feature over all these regions. If you look at the concentration of black carbon and dust over the Himalayan region, they are pretty big number. One is in microgram per kilogram, another is in milligram per kilogram. So since BC is very, very effective than the dust, their forcing will be comparable. That even you can see that in the Chandan's paper also. And if you look at the albedo change, there is a significant albedo reduction happening because of the aerosol induced deposition. So albedo change leads to a large amount of warming. If you look at the forcing values, they are 20-30 watts per meter square. These are pretty big numbers compared to the amount of aerosol available over this region. If you calculate the DRE forcing, it will come around to minus 10 watts per meter square at the surface. So the deposition of aerosols is almost 2 to 3 times larger than what aerosols is there in the atmosphere. So it leads to a temperature change. This is the one we are more interested. The temperature change is of the order of 1 Kelvin to 2 Kelvin. So it's a very, very big number. Aerosol deposition leads to 2 Kelvin warming over the Himalayan region. It decreases the snow cover fraction pretty over this region, and not only the fraction, the last box, it shows the number of days in which snow is available. In 365 days, how many days each pixel is snow covered? You can see that almost 20 to 30 days are missing because of the aerosol deposition over the Himalayan region. One application, but we can look at all the climate models. If you take, there is a cold bias over this region. Any IPCC model or any model you take, you will always find a bias over the Himalayan region, especially the Western Himalayas. That bias can be reduced by including aerosols into the simulation. So when I do with and without aerosol, you can see that the bias significantly reduces over the Himalayan region because of the aerosol deposition. So I will just discuss about the hydrological effect aerosols on either rainfall and runoff. Yeah, aerosol leads to warming over the Himalayan region. This is topography is shown. You can see that there is a significant warming over this region, but this is highly localized. So it doesn't have much implication, but you can see there is an enhancement along the Himalayan foothills, and other regions don't worry much. You can see there is an enhanced precipitation over the Himalayan region during March, April, May. these enhanced simulation that can add to the snow melt also, river runoff also. You can see that same way when aerosol warms the Himalayan region, snow melt increases significantly, and also the snow cycle moves forward. So meaning that suppose if snow melts during July-August period, because in the control run or without aerosol run, with aerosol it goes 30 days back, meaning June 1st itself the snow melt mostly over the Himalayan foothill regions. So the snow cycle is getting affected, as well as the amount of snow is getting melted is also getting affected because of this aerosols deposition. And this is the work we published in WRR, Water Resource Research. And what we have showed here is over the western Himalayas, because of aerosol, there is two things are happening. One is the total amount of snow melt is increasing in the presence of aerosol, and also, as I mentioned earlier, the snow cycle shift towards more pre-monsoon side. So that indicates that the glacier, which is the glacier without snow protection, is exposed to the solar radiation, and it will change the energetics over that region. You can imagine like one region is covered with the snow. Once you remove that one, it exposed to the solar radiation, and your all surface energy balance changes because of this one. And if you look at the extreme rain, extreme snow melt occurrences, that is 99 percentile, the number of cases after the 99 percentile, if you see control run, it shows almost 1,500 events for whole pixel during the entire simulation. I just put the number here. And it doubles. The take-home message is over the western Himalayas, the extreme snowfall events increases almost 2 times because of the aerosol events. So extreme snow melt is increasing because of this one. So this we have seen also over the, this is valid for the Indus Basin, which goes from western Himalaya through Pakistan to Arabian Sea. So here we have the implication. So last one, how these aerosols affect the DRF. How much time I have? 4 minutes. Okay. So how aerosols affect the DRE. So this is very different. So here what I am going to talk here is aerosols are deposited on the surface. This surface deposition, how is going to affect the aerosols in the atmosphere. So that's what I am going to discuss. And we all know that the way the atmospheric aerosols interact with the radiation is mostly dependent by your surface albedo. Albedo is a big animal as far as the direct radiative forcing is concerned. So if aerosol going to decrease the snow albedo, it will change the direct radiative effect of aerosols. And you can see that this is the equation which connect the surface albedo and radiative forcing, and you can see that when the surface albedo is very low. So simply what I mean to say here is, suppose if you do a radiative transfer calculation over above snow region, a small number of particles, maybe a few nanograms of BC in the atmosphere will make your top of the atmosphere warming. So over a snow surface, you don't need much absorbing particles to get warming over the top of the atmosphere. Whereas over the ocean, if you pump tons of black carbon over that region, you will not be able to make top of the atmosphere warming over the ocean, because ocean albedo is much lower than the black carbon albedo. So there is almost impossible to make the top of the atmosphere warming over ocean, but it is pretty easy to change the sign of the radiative forcing over the snow surface. The sign of the radiative forcing over snow surface is very easy. So that's what we investigated. What we found is that without aerosol forcing, you can see that this is over the western Himalayas. The top of the forcing is positive, meaning it is warming over the Himalayan region. It is always positive over this region. When I included the snow darkening effect, this red one, you can see that in the June-July period, it changes. The positive forcing changes to negative, meaning that warming changed to cooling over the Himalayan region just because of the snow darkening effect alone. So as I mentioned earlier, when we have snow albedo effect, that leads to more warming, then snow melt happens, it exposes the non-vegetated land. The entire snow is gone away. So Himalaya is, those who are visited Himalaya, we know that it's a very loosey sand. So it acts like a dust source, and this increased dust source again deposit on the snow. This goes as a positive feedback mechanism. So that we investigated, and we found that this excess dust source is mostly sitting over this region. So if aerosols remove the snow cover over the Himalayan region, it will add as an additional dust source over this region. So an additional dust is coming into the atmosphere, and this additional dust is again affecting the direct radiative forcing. So that is somewhere around -4 watts per meter square. Out of 30 I was mentioning earlier, -4 watts per meter square is compensated by the snow albedo effects of aerosol itself. So this is already published in JGR. You can just refer to that one. And finally, this is one work which we are currently doing. So it is elevation dependent warming. I will show one figure. In that one, what you can see is, as I mentioned earlier, when BC is decreasing with the altitude, I mentioned that there is nothing interesting. It is expected because sources are at the surface. When you go up in the atmosphere, your BC will decrease. There is nothing wrong in that one. But if you look at the total radiative forcing, the SAE due to total aerosol, you can see that at the higher altitude, the aerosol forcing is increasing. When your concentration is decreasing with altitude, how can your forcing increases with altitude? This is mostly because of the snow albedo, snow microphysics, because radiative forcing due to aerosol is not only depend upon the loading alone, it depends upon the snow depth, snow density, snow grain size and all. So that is why we get this kind of a nice pattern. Your warming increases with altitude. The watts per meter square means it's nothing but a temperature, it's Kelvin. So you can see that when you increase when you go up in the atmosphere, when you go up in the Himalayan region, your forcing increases with the altitude. And interestingly, if you see the direct radiative effect, the aerosols which is present in the atmosphere, that shows that it gives almost a -25 watts per cooling at a 2 kilometer altitude. 2 kilometer, I think Kullu or Dehradun, that altitude comes around this one. And from there, if you go up, mean around 5.5 kilometer, the cooling decreases. Meaning both are same. Here it is warming increases, here it is cooling decreases. Whether it is direct effect or SAE, both have same effect on the temperature. So finally we calculated how it is going to affect the temperature over this region. We found that a pretty big number. So I am not emphasizing more on that number maybe we have to check. So I thank all of you, and these are the publications. You can just have some look. And this was my PhD student. She did all this work and she completed. This is my senior and division head. He was supposed to present this talk here. And I also thank Sushant. He is from ICTP, did PhD with the Saknikde, and he is now in Stockholm. And these are the people contributed. Thank you very much.
Thank you, Dr. Nair.
Hi Vijay, nice talk.
Yeah, thank you.
I have a couple of questions.
Yeah.
So first, simple questions. So you showed that you have measured dust and black carbon over snow, right?
Black carbon we measured using a kilometer.
Black carbon in air and in snow also. So how did you measure that?
Black carbon using a kilometer.
Okay.
Snow using transition meter.
Okay. How many sites you have covered when you were covering Himalaya?
Initially we went to Sadhovat, then Kolhoi, then total glaciers will be somewhere around 30 to 40. Yeah.
30 to 40.
Yeah.
Okay. So one thing what you were talking about the dust, that if snow melts and dust is going back.
Yeah.
So don't you expect that once dust has fallen on snow, then they will come together, they will agglomerate and become bigger particles. So it will not go in the same way as when it is coming from, say, it is coming from some desert or something. That kind of dust, and what if snow is gone, this dust is coming back. So it will be quite different.
No. Actually, dust comes, it gets deposited on that one. When snow melt starts, the melted water will carry some of the dust along with that one. Some will remain there. Then once this entire snow is removed, then barren land is exposed. So from there, depending upon the wind speed, again emissions start coming.
What I was saying, this whatever is coming again from the snow, after snow melt, and whatever was coming initially, that virgin dust, whatever was coming earlier, I don't expect them to be similar.
One is coming from West Asian region, deposited, melted away by the snow. This is from the central Tibetan region. It's a freshly, from that region it is emitting. It's a new dust is emitting. Other one is gone with the water. We have a runoff happening because of the snow melt. With the melted water, it has gone. So
you are saying there is a loose dust?
Yeah, loose dust.
Which get
Wherever
exposed
we
by
have
the
high wind speed, it will start emitting from that point.
And one last question is, you were showing the vertical profile of black carbon from different sides, and then you showed Henley was the lowest, and then you go further up, it was increasing. Why? SU, yeah, it was higher than the
Henley value. So when we go to the very low concentration, systems will have
that
spike.
looks significant because means your scale was in microgram per meter cube,
Yeah,
and
NCOP
they were in nanogram. Means
yeah,
you can see that in microgram scale. That means
I agree. Because Western Himalayas, the Hanley was in Western Himalaya, this is more like a free region. But when NCOP that is comes in a valley region, so there will be confinement coming. So always that number is higher than our value, though it is high in the altitudes. It because of the how our site is located. Hanley is on the top of one mountain. There is no confinement. It's a clean air. It is seeing. It is at 4.5 kilometers. NCOP is in a valley domain. So there is some confinement is happening in the valley, so that could be one reason. I am not very sure, I can look into it.
I have another explanation for the same question. Generally, like it's also distance from IGP. So Hanley is very far. It has to cross through 3 ranges, and NPR is just after the Great Indian Range, Himalayan range. So in my experiments also I saw the farther we go, it's the first range gets maximum. The first range gets maximum deposition, and then till Hanley it doesn't.
Yeah, thank you. Very nice lecture. Just I am curious to know, when we are talking about our Himalaya aerosol deposition and composition, whether we consider the ITCZ, intertropical convergence zone. So we know in summer ITCZ move towards the foothills of Himalaya. During winter it's come down south of the our Indian region. So how does it affect, whether you are considering this ITCZ impact on deposition and composition of aerosols or Himalaya? Just I want to curious to know.
No, the whole presentation I focused only on pre-monsoon time because that time is the transition time. So ITCZ is still in our ocean only. So that may not contribute to this one. Pre-monsoon, March, April, May only I was talking about, the full discussion.
Okay.
I have a small question. So you also showed snowfall increment because of SAE.
Precipitation. In model we don't have a snowfall directly, but since the surface temperature is still below 0, we presume that it could be.
And it's during monsoon or pre-monsoon?
Pre-monsoon.
Or winter
Monsoon
season?
time we don't look at that one because that time dynamics is different and it is a large scale phenomenon, large scale dominated one, and the concentration decreases over the Indian region. So we focus mostly on the pre-monsoon way because pre-monsoon time we have a large amount of solar radiation and aerosol concentration is high. Naturally it is melting, so it acts like a catalyst. This aerosol acts like a catalyst to the snow melting, so it enhances the melting. That's all.
Thank you very much.
One
I have one
question. So like you showed that like transport of primary emissions to if Himalayas, it will impact negatively like positively towards radiative forcing. So what about like new particle formations over those regions? Because it will have negative impact and it may compensate whatever positive impact you are showing through radiative force or modeling studies.
Yeah, Himalaya is known for new particle formation, and people call this as the main source. There is a lot of new particle events are already reported, as Chauvin is also reported. A lot of new particle formation is happening. That new particles are adding to the total aerosols, scattering aerosols available over this region, and this is the radiative forcing due to the total aerosols available in the atmosphere. DRE. So forcing is somewhere around 0.2 or 0.1. This is about the primary aerosols, black carbon and dust deposited onto the surface. That's a big number. So this sulfate, when it is getting deposited to the snow surface, nothing happens because sulfate has 0.9 albedo or 0.96 albedo. Snow is also having 0.96 albedo, no change. But organics can have still a significant effect. I have not included organics in this simulation. So organics could be a potential contributor.
I think we can take this discussion.
MBF is not included in the model. These are climate models. We go with very minimum aerosol content or aerosol chemistry or atmospheric chemistry. Otherwise, it kill our whole time. So
Very sorry to be the spoil sport, but I have to keep time also. So thank you very much, Dr. Nair. And with this, I am also happy to invite our next speaker, Dr. Ramkrishna Ramisetti from TSI Instruments India, Bangalore. And he will talk about nanoparticle measurement techniques.
Hello all, very good afternoon. First of all, thanks a lot to Vijay to inviting me here and being part of this wonderful session. Actually, this topic is very close to my heart. When I was doing my postdoc and PhD, I was working on this new particle formation and nanoparticle studies from both physical and chemical characterization. But in last 4.5 years, I have been with the TSI. But time to time, I am engaging with some of the professors and scientists who are working in this field. So I will brief you on some of the measurement techniques which are useful for the nanoparticles, or which we call it as ultrafine particles, for both atmospheric and air quality studies. So outline of my talk is, I will just brief you about TSI instruments and atmospheric aerosols and tools for the aerosol characterization, and TSI solution for the SENS standard, which is recently came up in the Europe. And also I will show you some of the global trends in the aerosol studies. So TSI is a US based company. It is into particle instrumentation or aerosol instrumentation since last 60 years. We have been developing continuously the new equipment, collaboration with the University of Minnesota and other institutions. And majorly we have been dealing with, in this particular division, we have been dealing with 3 major applications. One is atmospheric aerosol studies, and the other one is filtration applications, and the other one is engine exhaust emissions. In all these applications, we have been providing solutions from 1 nanometer up to 20 microns. So there is no single instrument that can measure from entire aerosol range from 1 nanometer to few millimeters. But we have equipment which are dedicated for the different objective of the scientists or professors depending on their application. So I don't want to tell more about this graph, but I can brief you on this. The aerosols are very important to which are the origin and evolution of the aerosols is very interesting or important to understand the effect on the scattering and absorption of the solar radiation and the cloud condensation nuclei, and other important thing is the health effects on the human health effects. Okay, for all these 3, we have been studying these aerosols, and most importantly, when you will look at in recent days and recent studies, they are showing that these nanoparticles, especially the ultrafine particles, can go very deep into lungs, and they can penetrate with the blood cells, and they can go anywhere in the body. Okay. So in this topic, I'm only concentrating in this presentation. I'm only concentrating on the measurement techniques for the ultrafine particles. I'm not going into PM 2.5, PM10, because many of the people are already using a lot of different equipment for the LOCA sensors to high-end equipment. So this picture is from the very good book for the atmospheric aerosol measurements, principles and techniques by the David Louis and Pui. So in this picture, we have 3 basic parameters, that is mass, number and size of the aerosols. For each parameter, we have a direct sensing method and indirect sensing method, and also for different sizes, and also by different light scattering methods, and also different resolutions. We have various different methods to measure the particles from the in the atmosphere or wherever we have the sources. Okay. For example, if you look at the direct sources, quartz crystal microbalance or vibrating mass sensors or beta attenuation method, and indirect methods like light scattering methods. What we have with the nowadays, we have lot of LOCA sensors, and also for the number concentrations, we have for ultrafine particles, we have condensation particle counters or electrometer methods, and similarly for the bigger particles, we have optical methods, light scattering methods, and also the aerodynamic diameter, which is one of the best way to measure the larger particle size distributions. And similarly for the different high resolutions, for example, when you look at the size distribution of the particles, they can be now from 1 nanometer to few micron particles. So
it is always good to have more high resolution data. So there are equipment like SMPS or LP, there are instruments which can measure size segregated aerosols. And also there are other type of equipment for the larger particles. So I just put few slides for the ultrafine particle measurements of mass, number and size distributions. I'm not going into detail about this chemistry. So for real-time number measurements of the ultrafine particles, we have instrument called condensation particle counters, which we in short form CPCs, and electrometer techniques, and also light scattering methods. The disadvantage of the light scattering method is because of the we cannot measure very easily the nanoparticles with the light scattering methods, because the light scattering scattering intensity will be very less, and photometer cannot detect the nanoparticles. So we use condensation particle counters or electrometer techniques, and also some people use, if concentration is very less, some people use filter paper methods or microscopic method to count the particles. So this is the condensation particle counter. Here you can see the picture of the condensation particle counter, and here we have three major parts: saturator, condenser and optics. Here we have an inlet, and the particles will be the nanoparticles will be pulled into the instrument, and those particles will be here we have a liquid, that is, we call it as a here a saturated liquid, or either we use butanol or water. That butanol vapor will be condensed on the particle, so that the particle will grow further, and which can be easily detected by the optics. That's why we call it as a condensation particle counter. So this technique is very well recognized and gold standard method for the nanoparticle counting. Okay, and here I mentioned few things already. So there are different CPCs which can measure from 1 nanometer up to 1 micron or 2 microns. So this is based on the single particle counting, and it measure in real time. Within few milliseconds, the instrument can detect the effect of the for example, if there is a engine exhaust emissions, you can immediately see the effect of the engine emissions. And there are different type of equipment, CPCs, which can measure from low concentration to high concentrations. Even engine exhaust concentrations also it can measure. And even it can measure a single particle. If there is only one particle, it can measure easily. So there is another method which is used to measure the particle counting. This is electrometer method. It's just with the Faraday cup, it measures the charge on the particle and basically a current. So this is another technique, but it is a very high sensitive instrument. Mostly this instrument is used to calibrate the CPCs. Very few people use to measure the particle counting from the ambient. And the other physical parameter is particle size. We call it as a particle size distribution. Many people have stressed about the importance of the particle size distribution in the new particle formation studies. And we have real-time methods like electrical mobility scanning methods, or ultra-fast electrometer methods, or some of the optical methods, and QCM impactors. I'll brief you on this. So this is first method is scanning mobility particle sizer, which can measure from 1 nanometer to 1 micron with the different DMAs. And the other method is a fast mobility particle sizer. This is with the electrometer method. This is scanning mobility particle sizer is with the combination of DMA and CPC. And in this, here as mentioned as scanning, it takes 1 minute to 5 minutes to scan from 1 nanometer to 1 micron. So it's a slow process, whereas this method is very fast. Even you can measure 0.1 second data with high accuracy. So this method is used to do the measurements from the combustion systems like engine emissions or from ship emissions. People have been using for such a kind of applications. And this is the scanning mobility particle sizer. It is a combination of two parts. The first part is called as a differential classifier with a differential mobility analyzer, and second part is CPC, condensation particle counter. So now, first of all, when aerosol pulls inside the instrument, it goes to the neutralizer, which gives a uniform charge distribution to the particles, and only one charge particle will come at a time when we apply to the when we apply electrical field to the rod, central rod, and only one size particle comes out, and that particle number will be counted by the CPC. So in one instance, that means one spectrum will give both size distribution and number concentration of the total in the environment. So if the spectrum looks like this, size versus number. And so you see the importance of the scanning mobility particles or nanoparticle sizing. This is one of the nice pictures. When you measure the mass of the particles, you cannot see the effect of the small changes. When you measure either number or size, you can see the effect of the, this is actually when we started the engine, you can see the effect of the diesel exhaust from the tailpipe. So you can nicely see the changes in the total number of particles, whereas you cannot see that in the mass, because the mass of the particles is very, very less, and you cannot easily measure that mass. And this is what I mentioned, the fast particle sizing. And the last part of the physical parameter is mass. So as I mentioned before, this is the size particle counts versus size, and this is mass versus size. You see here, the total number of particles will be very high in this first portion below 100 nanometers, whereas those mass contribution is very, very negligible. So measuring mass of the nanoparticles is very, very difficult. So for this, we have an instrument called quartz crystal microbalance with Maudy impactors. Maudy impactors are the cascade impactors. We combined two equipment like quartz crystal microbalance and Maudy. So that is a fusion of two equipment which takes care of the relative humidity of the particles and also temperature. The first portion is the conditioning of the aerosols, and then it goes to the cascade impactors. The quartz crystal, when the particles are fallen onto the quartz crystal, the change in the frequency of the natural frequency of the quartz crystal is proportional to the mass of the particles. So in that way, we measure directly the mass of the particles. So this is a direct mass measurement method. There is no assumptions here, and it is free from the artifacts from the relative humidity and temperature. So it can measure even 45 nanometers from 50 nanograms up to 2.5 microns in 6 different size channels. And also the cleaning of quartz crystal microbalance is very easy. You can complete that within a few minutes. And that particular sample can be used for the chemical analysis. And there is an offline method, which is a cascade impactors, which can measure from 10 nanometer up to 10 micron. This is a rotating disc Maudy impactor. People use it for there are different type of Maudy impactors based on the number of size channels and also the accuracy. So you can go for different sizes. Starts from 10 nanometer up to 10 microns or 18 microns. And in recent days, in last 2 or 3 years, there are changes in the aerosol studies. I have been observing personally on this particular SENS standard. People have been talking about SENS standard and Actris network, which is one of the biggest networks in Europe. And Dr. Andy also mentioned about Actris network, which is nicely formulated all the methods for the particle measurements from 10 nanometer to, from 1 nanometer to 1 nanometer to up to several microns. So for each, they have clearly mentioned how to sample, how to measure, and how to deal with the data. All these they have clearly formulated. This link is very nice to read. If you have time, please go through that. And they have mentioned for which kind of instrument you have to use for the sampling and conditioning and for counting and sizing. And TSA is providing a complete solution for this SENS standard, including a sampling system to the counting and sizing. So if you are interested, please contact me. And the other equipment is aerodynamic particle sizer. In Actris standard, For the larger particles, people always use optical particle counters. In optical particle counting, you have a lot of assumptions. You assume the particle shape as a spherical, you assume density as a 1. So with those assumptions, in the ambient, if you measure in the ambient, that the measurements will not be accurate. So this aerodynamic particle sizer will give you more accurate data, because we have two lasers here. The distance between two lasers is known, and when we measure the particle time of flight, that means the time taken from one laser to other laser, that is independent of the density of the particles and shape factor of the particle. That is, we call it as the aerodynamic path of the particles. So we measure aerodynamic diameter with this equipment, and this instrument can measure from 0.5 microns to 20 microns. In active standard, there are two instruments from the 10 nanometer to 10 microns. One is scanning mobility particle sizer for the smaller particles, and for bigger particles, the technique is aerodynamic method, not the optical light scattering method. Okay, and this is the combination. And we have also some nanoparticle generation techniques, generation instruments for the smaller particles, a simple aerosol generator, which is widely used for in the laboratories. And we have also other equipment from 10 nanometer up to 200 microns. And these are some global trends which I have been observing. One I have talked already. This is aerosol access network. And in Europe, there is one more network which is called as a Eurochamp. They call it as for chamber studies, they have a nice network. Yeah. And the mobile monitoring of the aerosols, and sensor-based networks, and periodical testing inspection of the nanoparticles. These are some global trends. And one of the interesting things is, I can tell you here, China has started these superstations in 2013. They have built hundreds of superstations with all these ultrafine particle networks. We do not have such a kind of network in India. So probably we can learn, and we can do something for the nanoparticle studies as well, in addition to the PM2.5 and PM10. Okay. So these are some of the instruments which we have. If you have any questions, I will be happy to answer.
Thank you very much, Dr. Ram Sethi. Any questions?
So, if you have any doubts or questions, or if you need any information regarding our instruments, please contact me. This is my email ID.
Yeah, miss. I wanted to ask how to make instruments cheaper.
Yeah, it's good thing actually, but yeah, what I observe is some people have been trying. But for trying also, for example, if you make any new instrument, to calibrate that, you need a good equipment. For that also, we do not have sometimes funding, or there are few people who are asking me such things. But yeah, it should come from the universities or research institutions.
Yes, I believe it.
I know that these instruments are not expensive when you just count the part by part price. But when the companies always have their own formula for costs, right?
Yes.
From R&D days, from this beginning of the R&D to the production, they have different formulas. But frankly speaking, as per my knowledge, I should not talk on this when it is in the YouTube.
I agree your point. Like collaboration has to come up between academia
and personally, I am helping a lot of my customers. Whenever they want something, I am giving my instruments for free of cost for several months. I have been doing since last 4.5 years. And whenever there is equipment lying in my lab, I am giving it free of cost for certain time.
So that's absolutely fantastic. Thank you very much, Dr. Ramakrishna. Thank you for this. And I hand it over to.
Thank you.
Okay, thank you, Chandan.
Since yesterday, we talked about the process level starting from 1 nanometer, and now we are gradually increasing through the understanding different pathways, and now at the final stage where we need to understand the receptor also. In the previous session, we understood about the climate, and now the turn is of health issues. So we have three very nice talks in this session. Professor Ravindra Khaiwal from Chandigarh, Professor Sagnik Dey from Delhi, and Professor Santu Ghosh from Bangalore. So without delay, I invite Professor Ravindra for the first talk of the session.
Thank you, Dr. Buddha. Am I audible? Yeah. Is it working?
Yes, yes.
Yeah. So I just wanted to ensure that you all are awake. The coffee and tea were really nice. Hope you will not mind if I stand here and discuss with you so that I can check who is sleeping and who is listening me, like I can check on the back. So we breathe 22,000 times a day. Inhale 16 kilograms of air. 16. And our lungs are filtering out. I wrote a review actually in 2001. It was about toxicity. So some were saying, oh, it's the size, it's the number, it's the physical property, Ferrine theory, Osborne theory, those were talking about, no, it's the chemical toxicity. Someone saying, no, it's the physical shape. It's not spherical as we think about. So all these things really bring focus on the health. That how our body, when we all are exposed, is not affecting equally to all. So before that, why I am here is that I will show you, because we have a site in Chandigarh, and we invite you for collaboration. So I'm running this through site which is Chandigarh.
Have air quality monitoring set aside, can be seeing 3 PM for verified monitor, and this is how whether the whole system is sensor for setting up.
So you can see we have collaborators from Japan, they are working, and these sites are for UX.
Sanjeev,
they are not for
you can see here, and Atmos,
for me, actually,
purple layer taking you back,
that's why I came here
and monitoring side, we are going to our other sensor out there. So this is the
these are the sites, and
site.
you can see they
For rural,
at near the rural site also we have
other emissions basically we are monitoring.
So how clean is the environment?
It's based in
From
Kerala.
rural to urban. The problem is, I came from Punjab, and now we are problematic. Why? Because we are producing rice, wheat. We are the food bowl of the country, but we are blamed for the pollution now. In 1970, when there was a scarcity of the food, we became the part of Green Revolution, and now we are part of the pollution. But you know, in the Ukraine war, who could feed? It was only this region which could feed, the most productive region, and this is why we need to think about before blaming. And this is the situation, how it look like. Then we try to understand the emissions, look at not only now in 2050, and these probably could match your interest, PM 2.5, means how they will increase, and how these you can say, lightweight volatile organic compound also increase. So your chemistry, your physics, you can work it out looking at our work. And you can improvise, means how these will react in near future. Again, we also looked at how the emissions are there, from which district, and if they are emitting, means why there is more burning there. Again, you can see those districts in Punjab area basically, or in means which are close to the Pakistani area. So why these districts are burning more? Which rice variety they are using? Is it basmati, which we prefer, or it is other? So what mechanization has changed? These are the issues which are leading to these kind of emission, and these emissions are available for your analysis, or if you want to use them, so we are open for this. Not only this, basically, you were talking about, because we link from satellite data to the ground-based monitoring also, why you see certain pollutants which are coming from the belt of, you can say, towards the Pakistani Himalaya side. And then we have this sink side. So what is contributing and how it is impacting, including the long-range transport we presented there. And then we also looked at the rural area side, how the pollution is varying there. Is it the black carbon which is dominating, or other pollutants which are dominating? And here you can see that through the tracer analysis, we also try to understand how much is the crop residue burning contributing to that total emission. The problem is, when we talk about rural area, we think only about the crop residue burning season. So we thought, oh, is it the only scenario when the pollution is high? So we looked at then harvesting, residue burning, tillage, sowing, and during the pesticide spray. And you will see that all season they play a chemistry and there is a increased emissions. Either you talk before harvesting, during harvesting, and post harvesting. So these are the work which are available, and this is how their emissions basically varied for various species. And then we also looked at fire count data and tried to understand how they are affecting the chemistry. Another interesting point is that when we talk about the air pollution, you will be surprised to note that AOD trend is changing much faster at rural location. Means they are the emerging hub. And when we saw India as a rural economy, we need to understand who will be paying the cost of the health. These are the rural population, and we remain focused around there most of the time. So this is the work which highlights that it is not only basically this AOD change is faster in cities, but it is much faster in rural area. Then this is again, if I ask people where would you like to go, they will say at a rural site and say to relax. But look at the emissions. They were almost 1.5 times than the Chandigarh city. So this is where we sometimes have an impression, but which might not be true. So we also work on sensor monitoring side with Dr. Day. We have placed some with Japanese colleague, with other colleague from USA and also from UK. So is this air pollution, is this only which we are talking, or there could be other sources? Yes, there are other sources, but if we look at, it is the indoor, where we are sitting now, what is forming there. And you will be surprised, there are 4 factors which will be affecting your health in that scenario. We were looking at the chemistry, but with chemistry, as highlighted by the chair, it is the how we behave. Means the social aspect, behavioral aspect, they will also affect. Means occupant behavior, outdoor climate, air exchange rate, and weather condition. And these pollutants you can also look at, and also some in the nanoparticles, like we hear during the COVID-19. Apart from indoor air pollution, I term this as separately as household air pollution. We know that in India, even more than 70% population is based on this solid biomass fuel. So, when you go to them and ask what is the health impact, they will say only respiratory issue, this is study just published actually, or eye irritation. But if you go through the data and stat, you will see that total pollution is killing more than 10 million population. And if you look at indoor and outdoor air pollution, they are the #1 risk factor for our health. And then if you go further, you will see that against all this systemic means cardiovascular disease, they are taking the burden of the death and disease. So we need to understand when we see the young deaths, they might be associated with air pollution. And 2011, Ella died, and 2021 it was said that she died because of the air pollution. Only 1 death till date because of the air pollution. That is global evidence. How many deaths? 1 death proven. So I ask you, is there any data? The government says there is no data because most of the studies, we, including myself or other colleagues basically, are working on correlation, not causation, or long-term evidences as we have from Pop and Dockery or other, you can say, cohort studies. But when we talk about indoor air pollution, as I said, because our rural, my talk will be focused on rural, Professor Padmavati, in 64 years back basically proved that yes, those who use solid biomass fuel, they are exposed and they have poor pulmonary. It is a disease, cardiovascular disease, like in smokers. So they are exposed, and we don't have any rules and regulation still for indoor air pollution or indoor air, except WHO guideline for indoor air pollution. So how it is differ basically? You know that mostly it is through lungs, but it can also be through other way. Again, our occupation, how much we are exposed, means which activity we are doing, India is the only country where people feel proud that my house is just close to the road. Of course, if you are living close, you are exposed to high concentration of the pollutant. Traffic pattern, percent of other pollutant, which I learned here actually how that chemistry play. And again, I was listening the source to exposure, but no, it's from source. It is then emission, then concentration. Then concentration, you are exposed. Exposure at target order. And then where, which pathway it is affecting, and your health status along with other parameters basically like age of the receptor, state of the health, duration of the exposure, concentration of the pollutant, and nature of the pollutant. The outcome will be defined. So there are various factors. There are various disease models which we can talk sometime. I can explain you from communicable to non-communicable disease how this focus. So we try to understand, and then we try to look at how much that at a rural location could be associated with the air pollution. So this is the same area which I showed you the slide, and here you can see on an average 250 excess death we could attribute it to the higher ambient air pollution at a rural site. So this is the first study from the India showing that yes, air pollution is related. Now, do you think this is fine? Look at the hospital admission data. When you say the air pollution is high, and when I try to relate it also, you will see that number of visitors are less. So means when people, we say what we learned from other studies, increased hospital visit. But I remind you, this is a government hospital data. So civil hospital data. So you need to also explore these things. If you are doing a health risk assessment study, and if you only rely on a certain data. So what I am showing, these are the high, means high air pollution episode, and less people are going to the hospital. So there is no issue. The government is right. Basically, you have to go through this article and you will identify that it might be that these are sorters. They might be going to someone more local equac. And this happens quite frequently, and we try to report those. Apart from this, actually, our behavior has changed. From last 2 days, you know that we are sitting indoor, and on an average also, we are spending now more time in indoor. So 76%. So this is time when we are thinking, we need to understand how will be the air quality impacting us. So at our rural location again, having the rural movement, we try to understand means what will be the air pollution exposure. Again, at rural location, you cannot find one type of kitchen. Like you have various physical environments. Someone was studying in Himalaya, someone has sink in Bay of Bengal or somewhere in coastal side and isolated side. Look at the type of the kitchen and then how the air pollution could impact. We were talking about indoor air quality standard, and here I am talking about PM 2.5 concentration. Look at where it is 2.5 microgram, somewhere here. So how much we are exposed. I heard a lot about black carbon, and when I talk about black carbon, you will be surprised to know that the concentration was more than 25 microgram. Only the black carbon means here you are looking the concentration somewhere in 2000 microgram range. So think about how much, and again we did our study looking at 2 hour to 6 hour exposure. So this kitchen, ethylometer, black carbon measurement, and where from 6 to 35 microgram. This is only the black carbon. If the time will permit, I will show you the kitchen. The tar is, you can say from the wall you can see the tar. And then look at the impact. Anyway, the minimum, maximum, and average. So overall, if we look at the concentration was relatively very high. We thought, okay, we have black carbon. Let us relate it with the benzoypyrene. So we try to establish a kind of a how much cancer we could attribute, because I look at the risk factor, and then I identified that if I consider black carbon as benzoypyrene, how many additional cancer, because this is the nearest I could find out. And then try to relate this crude death rate along with the population-based cancer registry. I hope you are aware that PGI Chandigarh is among the pioneer in leading the population-based cancer registry, through which you can verify your data also. Otherwise, most of these hospital-based cancer registry, which do not give you the better picture of the health risk. So this is the standardized cancer death as per our study, and this study published in Environmental International, and you can see. But here I will also bring an interesting finding. When I try to look at this excess death, yes, they are related, but and they are matching, because overall death burden, it is 2% only, which we will give it to the cancer. So somehow these burdens are in the acceptable range as a public health professional. Where in a one death at 1 lakh population, if you cannot provide any solution, is acceptable. Like chlorine we give in the water, and that is also related with the cancer. So we need to further investigate, and my colleague is sitting here. Means what is this oxidative potential, or what is there, which we need to really understand, or where we are missing, because this data is thoroughly examined and presented here. And we did another study recently. Is this clean fuel, is it really improving the health of the woman, or it is depleting, or if other women are using, what is happening? So what we did is clean fuel and smoking women. We selected 3 locations in 3 states, having more than 3,000 households and women representative. Our data, because we are also modeling and we will predict. So model has been developed and showing a good result. Interesting finding here. Means, of course, they vary from Uttar Pradesh, Punjab to Haryana to other place. But look at here. This is type of cooking fuel. Means those who are using this solid biomass fuel, they have higher risk or odds ratio basically of self-reported health outcome. Means their respiratory element is compromised. Another thing which you will see that we look at means which caste they belong. So the poorest of the poor, the socio-economical status was also found to be associated with the health outcome. Means we call them backward caste or whatever it is. So this shows that yes, there is an association. Another thing, in different states, looking at the basically type of the biomass fuel, we notice that age is also a factor. So in Punjab, you could see that they are reporting early. The health outcome is somewhere in 30 to 40 year of age group, whereas in Haryana or other, it could be the 40 to 50 year of age group. So this shows that yes, means if we provide the clean fuel, their life could be better. And that is why the government initiated several program, and you are seeing that we have reached to the now this PMUI, and then there is a Solar Alliance also, which the first day the speaker were also talking about this sustainability, the sustainable development goal. So these are the impact which we looked at, and this is how we have reached to this barrier where this energy transition is happening, and if it's continue, we will be able to minimize this health and disease burden because of this, and we propose this how it could be ensured using this Keval model and then various programs. And if we give, means if we implement our policy, it's not always the dark side. Here you can see that the article is showing that if you implement your policy and planning at the ground level, you could have the positive outcome. So that and disease burden, which was reported somewhere here, is now reduced. So the positive policies work. Last, so if we do this, basically we can have a positive impact, and we need to work towards more the vulnerable, those who are you can say unaccessible, so that we can minimize their impact. So considering this, basically I developed this health adaptation plan for Government of India. We were given this responsibility by National Center for Disease Control, and it was adopted by them, and I'm happy that I developed this, and which is being adopted by Government of India. Along with this, these two booklets like health sector preparedness for air pollution, then what and how a medical professional can play their role to understand, means, and look at and relate air pollution with the health. So these are the booklet which you are also seeing, and they are part of the national program. So this is somewhere you feel proud, basically you develop something and become a national, part of the national program. So it's a small contribution from our side. And then another booklet, to educate common man what is air pollution. You can look at the content. So our environmental minister and the state minister at that time, they have released or forwarded it basically, if you will go through. And then how people were asking so many questions. So then we developed this for the ministry also. And then I hope you are aware that we are the communicator through comics. So 42% population in India is children, means below 18. Some, let's say, so if you want to communicate, you can at least have 35% of your population to talk with them. So when COVID came, I developed this booklet, and along with our partner, we developed means how to minimize air pollution around the school. And these two comics were released by Government of India. And the latest booklet I developed on climate change. You name your language and you will find that booklet probably, if you can read your language, you can find it here. So they are available in more than 22 Indian languages, and international translation is in progress. So through these communication basically, we are not creating awareness, but we are breaking them to them for certain action, and these actions are known as lifestyle for the environment, which is a Government of India initiative, Life for Life. Means lifestyle, how through modification in our daily life we care. So where the government is taking several initiatives, like I said, Solar Alliance to green energy, we as an individual can also contribute towards healthy planet. Thank you.
Thank you, Professor Ravindra. Yes, question time now.
Thank you for such a vast topic to cover, and I have a comment. So you mentioned about the tower in rural areas. So women cooking, and you can see the. I think you're talking about the black soot, or what exactly you're mentioning about that?
Basically, that is tar.
Yeah.
And tar is nothing but black carbon, which is deposited on their wall.
So I have seen that in my house in Delhi as well. So that's why I wanted to
say that. Means we talk too much about black carbon. We are going to Himalaya also to measure that. But look at, means there you see only in small particle. But look at in the long term how much it is being deposited at their houses. Means so how much exposure could be there? You could simply look at their houses. You can imagine. But still somehow the cancer risks somehow were not there. But when I am saying cancer risk, they are again part of this total mortality burden is only 2 out of this 2%. So I'm not denying that cardiovascular disease burden might be more.
Okay, and can I hear? Yeah. There was also you. I couldn't get what is the odd ratio. Maybe I missed something. On x-axis.
If you have healthy population and compared to that odd of disease, compared to that population basically in the person exposed to. So that means if odd ratio is 1, means there is no chances of having disease. But if it is posed more than that, it means there are odd of having that disease compared to non are that much basically. So 1.2 means you can say that roughly if there are 100 people, so there will be chances that 2 people will get that disease, something like that.
Okay. Thank you.
Okay. Thank you, Professor. Okay, our next speaker, Professor Sagnigde, and he's talking about how we are looking beyond PM Mars.
Okay, thank you. Yeah, so I want to express my thanks to BJ for inviting me. It's really great learning, listening to all these important talks. And Dr. Khaiwal has already provided a very good overview of the air pollution and health scenario in the country, covering multiple topics. So my talk is focusing mostly on the argument that we should start looking beyond PM mass-based indicators when it comes to the health impacts. And I acknowledge the contributions from my research group, Dr. Santu, with whom I'm collaborating, and many other colleagues. So just two examples. We all know that WHO has various interim targets as well as the air quality guideline, and I'm mainly talking about today on PM 2.5. And if you look at all the important interim targets, all the way down to the air quality guideline at annual scale, which is 5 microgram per cubic meter, these are all PM mass-based thresholds. If you talk about our own national standard for PM 2.5 at annual scale, it is 40 microgram per meter cube. WHO interim targets and air quality guidelines are mostly based on the cohort studies done across the world. When the Central Pollution Control Board defined the national standard way back in 2009, there was no study actually published on PM 2.5. Papa study which Dr. Santu was involved, that it was going on. Perhaps the first report came out in 2009 or 2010 or 2008, yeah. So almost the same time. Oh, 10, yeah. So this number has no scientific backing. Why the national standards was set at 40 microgram, but now, as we speak today, CPCB is in the process of revising the national standard. And then obviously you have the different 24-hour standards. Then the other important point is that we talk about the global burden of disease. I was part of it from the India arm, where exposure, rather long-term exposure impact on non-communicable diseases are quantified. And if you see the methodology there, what they do is basically they calculate the excess mortality or morbidity attributable to different diseases. So for example, so far the relative risks are available for COPD, ischemic heart disease, stroke, LRI, lower respiratory infection, type 2 diabetes, and preterm birth. So these are the 6 diseases which are part of the GBD because there are enough cohort studies to define the dose response functions. Now I must say that there are many other diseases for which air pollution impact has been identified globally, including in India, but enough cohort studies are not available to really develop the integrated exposure response function. So that is why they are not yet part of the GBD. And how do we calculate the excess mortality attributable to air pollution? So you calculate the attributable fraction, which is basically a function of the relative risk. So any given exposure, you can calculate the risk. If you have these functions, then you can calculate the attributable fraction, you multiply by that baseline mortality and the population, and that gives you how much of the total burden of that particular disease you can attribute to air pollution. If you have to do this for smoking, same methodology, all you have to do is actually you need to know what is the attributable fraction for that particular disease to smoking. So the point I'm trying to make again here is that all these things have very important assumptions. The first assumption is that the epidemiological risk only varies with PM exposure and not with compositions. So what is assumed is that the relative risk at any given exposure does not change if the composition changes. So we are assuming uniform toxicity. And secondly, for long-term exposure, particularly what we assume is that if we have long doses of low exposure versus a situation where you have relatively low dose and then suddenly you have high spikes of exposure. So there is no difference. So these are the two basic assumptions. But this is the main assumption where I want to draw your attention. Question is that whether this assumption is correct, and also that what is the air quality guideline. As I mentioned, WHO has set 5 microgram per cubic meter annual PM 2.5 level. Is it really possible to achieve? Very recently a study has been published by Siddhant, and what they have done is a modeling study. So they have switched off all the anthropogenic emissions globally no anthropogenic emissions whatsoever globally, and then this is what the PM 2.5 annual values, and you can clearly see that most of the countries, the PM 2.5 value is above 5 microgram per cubic meter. Entire India is above 5. So it's very clear that whatever we do, we can never reach WHO air quality guideline of 5. You have that much natural PM 2.5 present always in the air. So really the question is that then shall we really try to achieve 5, or we set more realistic target, keeping in mind that uniform toxicity assumption is not true. That's what the research is suggesting. So what is the way forward? So way forward, obviously you have to answer the question whether PM composition matters. And how to answer the question in terms of health, Dr. Kaival has already mentioned, so you can do different types of studies to generate indigenous evidence. You can think of doing time series studies to see the impact of acute exposure. You can think of also doing cross-sectional study, first to establish association, and then for causality, you have to go to cohort studies. Now, when I started this work a decade back, I was sort of told that where the health data will come from. But now I realize that there is a lot of health data available. The real challenge is actually the representative exposure data availability. Now why I feel this is a challenge, because you think of any of these studies, it requires consistent, long-term, a very robust exposure data. Because if you're talking about cross-sectional study, you need data for the entire country, or at least in a very large regional scale. You may be measuring at 1 or 2 locations, and then think of doing again, some time series studies, but that will not really give you the impact assessment for the long-term exposure. So there are many challenges, and because India has a very inadequate, I would say, network for PM 2.5, even if I talk about today, we have around 400 continuous monitoring sites for PM 2.5 measurements. Most of these sites actually became operational after 2018. So if you go back in time, there are hardly any monitoring sites, and even today also we have no reference gate monitoring maintained by the government in the rural regions. Only few, as Dr. Kaival mentioned, are being maintained by different research groups. So what we did is that actually we developed the satellite-derived PM 2.5 database for the Central Pollution Control Board. So our data is at 1 kilometer spatial scale and 24-hour average values for the last 22-23 years. Now, one important point I want to mention, that when we derive PM 2.5 from satellite AOD, the most important thing is to fill the AOD sampling gap at Delhi scale. We all know that passive sensors, when they retrieve AOD, they cannot retrieve on the days when it is cloudy. And it means that if you simply miss those sampling clean days, your annual statistics will be biased towards polluted. And this is exactly what we have quantified, and in fact we have developed a machine learning algorithm to first fill the daily AOD gap. So this is actually unfilled AOD average over the last I think 7 years, and this is the field. So you can see that there is a clear bias. And then when you convert this to surface PM 2.5 unfilled data versus field data, interestingly what we have found is that because you are missing those better days in your sampling, your annual PM 2.5 exposure is overestimated by at least 20 to 30 microgram per cubic meter, and that's a very, very large number. So if your exposure is overestimated, then you can think of how much actually the downstream applications will be impacted, and this is the kind of performance of our daily product monthly and at annual scale. You can see that the error is pretty much lower. I'm just showing the recent results because on the morning I listened to many talks which shows that there has been increase in the aerosol loading over the Indian continent from early 2000 to 2016 and 17. I am showing the data from 2017 to 2020 to the last 6-7 years of data, 6 years. This is not AOD, this is PM 2.5. And this is actually the distribution of the population weighted exposure. What essentially you see that if I calculate what fraction of population is exceeding the national standard of 40, interestingly you can see that number has come down in most recent years. And if you look at the satellite data or even the ground-based measurements both from continuous sites and manual sites mentioned by the CPCB, you will see at annual scale in more recent years PM 2.5 level in most of the cities are decreased. If you don't believe me, just look at the data. Because we always think that pollution level keeps on increasing, but I must say that not just our data, very recently Ministry has also reviewed the NCAP activities, and most of the cities have shown an improvement in terms of air quality, both in terms of annual average as well as the number of clean days or good days. So the next challenge is that, okay, this is the total PM 2.5, but my original point was that how we can really talk about the composition and look beyond. So that's even more challenging. So what we do is that we take this PM 2.5 satellite data because we wanted to develop database for the entire country. However, satellite cannot give you the composition directly. So what we did is that we collaborated with people who ran the chemical transport model, and from the model we got the mass fraction of individual species. So we simply, and because actually the models have also uncertainty due to the uncertainty in emission inventory and other factors, we assume that the model derived mass fraction will at least be correct, if not the absolute value. So we then multiplied this mass fraction from the model of each species with the total PM 2.5 from satellite data, and then we get basically the individual species information. And this is just an example for, this is for 2015 and 16, so you can see that this is the typical black carbon exposure. This is the organic carbon, sulfate, dust, and sea salt, and then now we have more species. We tried to sort of compare our modeled exposure versus very few ground measurements, whatever data we could get, and we are still trying to get more and more data to improve, but at least for black carbon, organic carbon, and sulfate from literature, overall our correlation coefficient is 0.8. We hope that obviously it can definitely be improved with more data filtering in. But since we have this data, then we did series of different analysis. So this is one example of acute exposure analysis with PM 2.5. So first what I'm showing here is that in literature we find in many cities with PM10 data, people have looked into what is the impact of increase in PM10 on all-cause mortality. Very interesting thing, if you see that some of the cities which are polluted, I was just discussing with Dr. Santu, that when it comes to acute exposure, if the city is already polluted, then the sensitivity of the people's response to spikes in shorter term to the pollution level is much lower. Rather, what you see is that in the cleaner region, the impact is much more. Like, for example, Chennai or Simla is showing much higher impact than Delhi and other places. Now, if you compare with PM10, what is the situation with PM 2.5, for which studies are available from Delhi and from Varanasi. So Varanasi study, again, Dr. Santu is involved. So you can clearly see, first of all, in Delhi we have both PM10 results from PAPA study and PM 2.5. So PM 2.5 impact is much larger than PM10, so that is very clear. But then we also ask the question that whether there is differential association with PM species. And that's the next study that we did, and you can see here that we looked into multiple species and very clearly what is emerging. So for each of these species we looked for male and female. Same thing, all-cause mortality data. Essentially the take-home message from here is that there are differential associations. If you identify which species has stronger association and larger association, you will see mostly it is black carbon and the secondary particles like sulfate or ammonium sulfate, whatever form you take, ammonium nitrate and others. This is for the short term. Then we did some analysis with the in a cross-sectional study design, utilizing the data from the National Family Health Survey. Anemia is one of them. And the reason anemia is chosen is that India has one of the highest anemia burden as per the statistics. So after adjusting all the important confounders, what we found is that first, with total PM2.5, increase in 10 microgram per cubic meter exposure leads to almost 7% increase in anemia prevalence in the women. And then we also then looked into is there any differential association, and again you can see that between these 5 species, clearly sulfate and black carbon is showing higher impact than some of the other species. And then this kind of analysis has been repeated from some other health outcomes. So here is the most recent analysis that Dr. Shantu and my group have done together, where 3 different child health outcomes we have taken. One is the low birth weight, child anemia, and acute respiratory infection. And again, after adjusting for all the confounding factors, exposure assignment strategy is slightly different when it comes to the child. So for low birth weight, we have considered the exposure during the pregnancy, so that we can see the impact of exposure during pregnancy on the birth weight of the child when the child is born. For anemia and acute respiratory infection, the exposure is basically from the day the child is born till the survey was done and the results are available. So again, the main message here is that you see differential impact. For example, here again ammonia, the ammonium sulfate, nitrate, EC has little bit higher impact. And because we know that the species can be tagged to the sources, so when you did the analysis with different sources now, you see basically the similar result. So this points out clearly that there are differential impacts, or association rather I should say. So why is that? So if you look into the literature again, the biological pathways, unfortunately in India for composition there is no study so far. We need to definitely do that studies, but if you dig into the literature and see elsewhere, then there are many studies which have clearly shown how biological systems respond to such differences in the compositions. And this study is from Park et al., where they have shown that, so simply actually if the circle is larger, the toxicity level impact is much more, the response of the biological system. So clearly what they have identified is that, for example, diesel generators, shoot, coal combustion and all have much larger impact for different, biological responses. So it is very clear that different composition has different toxicity level. However, we are yet to reach consensus on which particles are more toxic across a wide spectrum of health impacts. But there is no denial of the fact that PM composition matters when it comes to health impacts. Now, even if you move ahead of PM or PM compositions, the next question comes that air pollution is always a deadly cocktail of various components. It's not just PM, you have various gases and others. So if that is the situation, then whatever association or causality you are establishing with PM, it may be modulated by other gaseous pollutants. So what is important from India is that we need to go in a multi-pollutant environment and start looking into this. Now for that again, what is required is exposure data for all other pollutants. And one such pollutant is NO2. So recently we sort of looked into the long-term changes in NO2 columnar concentrations and tried to understand where the NO2 columnar concentration is higher. And you can see that wherever you see big power plants or the big cities, you have high NO2 concentrations. And now using such kind of satellite data, you have developed a land use regression model to estimate the NO2 surface exposure at a very high resolution of 100 meter by 100 meter. This is done at annual scale for 2015 onwards. We did not go back to 2015, but if required we can go, and then we can see sort of that again it's a very quite good comparison with the ground measurements. But then if you just blow up the big cities, Delhi, Mumbai, Kolkata and Chennai, you can see that in those cities most of the regions are actually exceeding the national standard. And if you keep in mind the WHO air quality guideline of 10, which is for NO2, then a large part of the country is actually exceeding. So what is the way forward? My last slide. What I feel is that we need to create consistent, robust and long-term exposure database for PM species and other pollutants, so that the health studies can be done in a consistent manner across different timelines, because we also need to understand whether the health impacts are changing over a timeline, as various other factors also impact those, which Dr. Santu will talk about. And as Dr. Rastogi mentioned earlier, I think this is the key actually, that we must link to oxidative potential and understand the biological response. And if we cannot do that, then whatever policy we are framing is meaningless. And we need actually systematic epidemiological studies with as much as possible indigenous health data, because this is one of the key things always coming from the policymaker. Where is the evidence? I showed that there are evidences which cannot be ignored because these are all Indian data. Finally, we need to set realistic linear target. We cannot really, target dust. And if you talk about the national linear program, you will mostly see what we are doing is controlling dust. We forget about fine particles, diesel generation, and many other actually, which are the toxic sources. And finally, those mitigation efforts to be prioritized where we know that toxic particles are being emitted, and clearly there should be demonstrations that air pollution mitigation efforts are leading to health benefits. So with that, I end my presentation. Thanks for your attention.
Yeah, thank you, Professor Day, for this nice talk. And now the question time, please.
A very nice talk. I think both the statements are correct. For example, that AOD is increasing, we all know that, and several reports are telling. What the statement you are telling, PM 2.5 is decreasing. Please note that AOD is the integration from the top of the atmosphere. In the changing climate, the recent time, the trends has been changed. The free tropospheric aerosol concentration has been increased. So that will not come into the PM 2.5 what you are mentioning. I think both the statements are correct. Using RF network, SPL people, and from Gadenki observations also, we have shown that in the recent times, there is a decrease in trend in the BC, and also of course though it is a part of fraction of in the total aerosol, but there are decreasing trends in the surface, but increasing trends in the free troposphere. So that will reflect in the AOD. So we should keep in mind that these two are two different aspects.
No, absolutely. I mean, but my point here is that when it comes to air pollution, and particularly for exposure modeling, usually, when you try to convert AOD to surface PM 2.5, it was not done, adequately. And many data sets I have seen actually where PM 2.5 surface estimation is highly overestimated, because you don't really adjust to the particle distribution.
Yeah.
Yeah, there is one comment. Means actually in the final slide you are addressing that. So when you are showing the composition, means say sulfate, nitrate, ammonium, we know that they are the part of PM 2.5, and more or less means they're not too much variable. So that means if it is you get the relation with the PM 2.5, you will get with those component also. But actually, if we are looking for the species actually which are causing oxidative potential, that you have already said in that. So in that, black carbon may be interesting thing, because that is the means it represents the combustion, and from combustion many of the reactive oxidations also come. So among them, black carbon is the most realistic.
No, absolutely. I mean, so it is just a beginning. Even in organics also, there are studies globally, not from India, that soa is much more toxic than primary organics and all. So organics, when you say, it's also of different types, and then you need to really differentiate and then try to see actually there are studies not from India. So those are the challenges, and that's why you need to really work together to first develop exposure data for each of these different compositions.
Yeah. Yeah, Doctor.
Thanks for a very nice talk. Europe is currently revising their air quality guidelines. And in these guidelines, at the moment, the proposal is that they're going to add, first of all, black carbon as one of the substances to be measured, oxidative potential, and concentration of ultrafine particles. These are not going to be
regulated at this moment, because first what they want to do is when they want to collect the exposure data. So maybe that's something to consider, and then of course follow what's happening then in Europe in the future for that.
No, absolutely. I think very good point. I mean, probably in future things will be considered, but currently the CPCB is already in the process of revising it based on whatever knowledge we have. But yeah, absolutely it will.
Professor Day, I have a small comment and the question also. Giving a little bit background, Professor Smith, he started to work in 1990s in India, and he already started with a couple of things, but still, what's your take on how we stand on the estimating the toxicological curve? Because that's based upon the kind of sensitivity of the individual, one thing. Second, still he raised this point in 1990s that we need to have a cohort study because we are missing, and Professor Balakrishnan was part of those discussions. But still we are at the same pace. So what's your take forward in terms of establishing something related to cohort studies and having the toxicological curve, what Professor Rastogi also mentioned about the different compositions, and I'm looking forward to see in depth basically all these toxicological curve and how we can build into ICRP model all these things basically from the Indian perspective.
Yeah, I mean, again, absolutely agree. Whenever we discussed, those are the discussions. He used to say that we should move from source apportionment to exposure apportionment because that's where the impact is. Yeah, coming back to the point is that, yeah, I mean, if you look around the typical research going on in the health field, funding, long-term commitment to the funding is a big constraint for cohort studies. Still, there are, I think, a few cohorts which are either recently ended or still continuing. There are opportunities now if you have this sort of exposure data. You can sort of add air pollution as an as a risk factor and do retrospective analysis for the cohorts for which already the health data is available. I don't. So only probably one happened and some other cohorts are going on where directly they are actually assessing the exposure, but again, not from the toxicity perspective, it's just the total exposure to different pollutants. So the research community is trying to convince health ministry that these are important things, and in CDC I think they are kind of agreeing that we need to really move beyond this traditional standardized metrics and do more. I hope that in future we should start long-term.
And I believe the cancer registry data also if can be maintained, because still we are not established a kind of linking which is based upon the international scenarios. I think you are the key person to take it forward with Professor Balakrishnan. Yeah, thanks for a nice talk. Okay, now for this session we have the final talk from Professor Santu, and we believe that we will understand more epidemiology from him.
Middle pointer, right? Okay. Good afternoon, all. Thank you very much, Dr. Bijay, for inviting this session, this seminar. And from the morning I was listening. I was not fully awed because 12 years I was with Kalpana, and that has a multiple wings actually. So I love to listen, even that is beyond my expertise, because sometimes that gives motivation for my research. So that's why I loved even in few days before, suddenly accidentally I entered into AI community, and that whole sessions I listened and found some motivation. So anyway, already Ravindra and Sagnik set the platform, so I don't need to say about air pollution and health association and its pathways. Rather directly, I am going to acknowledge some studies that have been already published and available in the literature. Not all, but whatever I could collected through Google, are going to summarize here, and it's just an acknowledgement, not a depth exploration of those studies, how it was done, but definitely we'll summarize from what we learned from here. So if you look at the air pollution literature, even recently the air pollution has been a major public health concern for so many years. And that recently, last few years when Delhi seeing this high pollution, people had started considering air pollution is a problem to our life. But it was there. In 2018, they said that around 9 million premature deaths worldwide, with India accounting a significant proportion of these deaths due to this air pollution. And 2019, 1.67 million deaths in India are attributable to air pollution, accounting for 17.8% of the total deaths in India. That is also Lancet Planetary Health 2021. That paper was cited by Ravindra also. And a study collected data from 25 cities in India reported, even forget about others, in recent, there is a direct link of PM 2.5 and COVID mortality. And same, Lancet Planetary Health reported the lost output from premature deaths and morbidity attributable to air pollution around, say, $28.8 billion and $8 billion respectively in India 2019. So it's one of the important factor at present to our day-to-day life that need to be mitigated, but nobody knows where is the solution. So let's focus on air pollution health, and then which are the health problems that normally people get. So based on the literature, these are few, there are many. Even recently I was getting some articles, I guess from the same Chinese group, somebody is trying to see the old age fall with air pollution, somebody trying to associate with GI with air pollution, and many other. So people are exploring. But these are something very common, is the respiratory, cardiovascular, neurological, reproductive age, cancer, reproductive outcome, cancer, eye and skin, these are mainly the acute impact. So these are the main focus health area where air pollution can impact. And now we'll see where we are in terms of the evidence base. I don't focus much on below 2019 because this is one article that is published in 2019, is beautifully actually capture all the studies before 2018 and 2019. So there are 59 studies in 2015 when I was summarizing my PhD, it was around 46 or 43, I can recall. 46 could be. So after that, this many happened. So 59. So I'm not focusing on these studies. Those who are interested to get the evidence about air pollution health, you can read this study. But I will focus more on what is the recent evidence that we have, touching few that are important from this pool. So Lancet Planetary Health 2021 estimated that air pollution is responsible for 1.6 million premature deaths in India every year with respiratory illness. And a recent study, Selvi 2021, compared self-reported respiratory symptoms of school-going adolescents between Delhi and Kota, Mysore. I feel this study is very important, though it's not actual comparison or actual exposure response association between PM 2.5 or any air pollution in this, but in epidemiological literature, this is one of the important aspects when you have a counterfactual, you have the exposure, and you need to show that where counterfactual no effect, while you have exposure, you have a effect. But in an air pollution literature, it's really difficult to find a counterfactual. And that's why, we consider still now that cohort is the gold standard for air pollution epidemiology, not randomized control trial, which in general is a gold standard to prove any causality. Because randomized control trial would be merely possible in this particular literature, this particular field of study. Because, everybody exposed to air pollution. You cannot reduce air pollution even below 5, whatever way you try being in India. So you cannot find a true counterfactual here. So these study particularly compared two cities. One is very low another is very high, two extreme of our country, because southern cities are much more cleaner. Even Mysore is one of the non-metro cities, so naturally they are much cleaner compared to Bangalore. So when it is compared, they found that asthma, respiratory symptoms, allergic rhinitis, eczema were much higher in proportion in Delhi than Mysore. That's why I'm telling I feel that is a very important evidence, because when you have a 2, it is almost, if we assume that's near counterfactual and another is really highly exposed, and you find a clear difference, that itself proof a bit about the causality. And when talk about lung, the Ranjini et al. 2022, they published a study that is called APCANS in here in Andhra Pradesh. And so this is not Andhra Pradesh now, sorry. It was. They reported that there was a decline in actually lung function. I'm not going in details. The details numbers are there. Those who are interested can read. They reported that there is a decline of lung function that is measured in terms of FPV1 and FVC. Actually, the forced expiratory volume in the first second. And this is kind of marker, that lung marker that help to understand the outcome or lung function. So that found to be declined by higher PM2.5 exposure. This is one of the important evidence, and it was a cohort. Then talk about COPD and air pollution. The Suryakant et al. 2022 reported the impact of use of biomass fuel on COPD among non-smoker, because that was a case control study and they excluded all non-smoker. Shows a higher, proportion in, higher odds of COPD, those who are actually biomass cooking fuel than non-biomass cooking fuel. And the odds ratio was reported by 4.25. Somebody was asking about odd ratio, right? It was nothing but the ratio of two odds. For your understanding, I would say if you can consider a risk. Risk means, you have a two group, and one group is this many cases and one group is this many cases. So if you get the proportion, the exposed group must have a higher proportion and unexposed group must have a lower proportion. So how do you get the excess risk? The proportion is the risk, but how do you get the excess risk? Two ways you can get. One is in an additive sense, and another it could be multiplicative sense. Additive sense means you can just subtract two risk and you can measure the excess risk, or you can take the ratio and you can get the risk in multiplicative term. So odd ratio is equivalent to relative risk, you can consider. And then even this is another study that it is not a study, it's a almost the prospective paper where they mention that given the alarming increase in prevalence of COPD among non-smoker in recent past, a potential role of air pollution, particularly particulate matter in COPD developed, has gained much attention of the scientists, because before that people used to take COPD in smoker. The smoking, it's considered to be COPD. Even if 65 years old is chain smoker, if you go to a physician, they would first write COPD without any investigation, because you are a chain smoker. So that is it. I have seen several times. So, but now the number of the COPD among non-smokers are increasing. That itself indicating the air pollution could be, a major risk. That a Karg used to say, the household air pollution is equivalent to that many cigarette smoking. Then ARI is a recent study, Balasubramaniam et al. 2022. They published based on the NFHS data with the global estimate of PM 2.5, and they also found the increase in, say almost 0.6% rate ARI cases increased by 0.6% per microgram increase of PM 2.5. And what they did here, they actually standardized the ARI prevalence by the prevalence per square kilometer. And then this is the global estimate PM 2.5, and if you see, you would see the clear trend between these two. So though it is a correlation, but actually giving some evidence that it is a causal based on the evidence that we get from the global database. I mean, it would be foolish to consider we are a different species than those who are living in Europe and America. So I would suggest, do not run behind collecting evidence, that rather try to quantify the evidence for a better policy making. There is another study where Sagnik was involved. It was not fully Indian, 35 countries, and you see how close the estimate is. The estimate is almost similar. So that India was one of the study, and they reported per 10 microgram increase in PM 2.5 was associated with odds of having ARI, that is almost 6% increase in odds per 10 microgram per meter cube increase. So here it was 0.6 per 1. If you multiply by 10, you will get 6. So both studies giving almost same estimate. I mean, there are very few evidence of cardiovascular illness, but there are sufficient global evidence nowadays, even in the cohorts, by a cohort study. So almost globally we can consider that this is a causal, but in India evidence are very, very few. The one study, same APCON actually, they had some, cardiovascular marker, which is the CIMT, that is the carotene intimate media thickness, which is the marker of erythroclerosis. It is not a good marker. However, it could be considered as a marker, but not as a diagnostic sense. But for a correlational sense, you can think as a, to understand the association between air pollution and CIMT. But it is not a correlation is not so good so far that I observe. But however, this is one of the evidence that they reported positive, the association of CIMT with PM 2.5. And that was, they did lot of things, they did land use regression and many other way they estimated the PM 2.54, yeah. Hypertension and air pollution, there are two studies that I found. One is the PHFI Prabhakaran and another is the Kalpana's, the Hapin cohort. They also showed that there is an association between increase of blood pressure and air pollution. Very limited information about cognitive health and air pollution in India. However, there are two studies that I found that also showed the higher risk of cognitive health, cognitive decline with increase of air pollution. One is the Krishnamurthy et al. 2028, and another the Lassie study, the famous Lassie cohort, that is the longitudinal aging study in India. Then child development and air pollution, there are few studies that, there are a couple of studies with NFHS4 itself, and this study also showed that the child satellite-based PM 2.5 actually, that is also the global estimate, I think. The reported increased average concentration of fine particulate matter by standard deviation account almost 5 and 2.4%, increase in stunting and severe stunting rates. The reproduction health with birth weight, this is another study that actually there are two studies that I found. Islam Mohant 2021 showed a significant association. Almost, they showed an 80 gram higher weight among clean fuel versus non-clean fuel. And Goel and Canling 2021, they found a nonlinear association. They found at different level of exposure, the effect is actually increasing. Then this is, Kalpana and I was involved, this study estimated almost 4 gram decline of birth weight part 10 microgram increase of PM 2.5. It is a cohort, so this is much more robust evidence. However, this is one randomized control trial by Kalpana and other partners. It shows actually there is no benefit giving LPG to the pregnant mother. Look at the journal where it is published. However, they reported that they found a positive association with actual PM 2.5 concentration. When continuous exposure response was associated, they found the association. But actual benefit was nothing. Let's focus few minutes on some time series study, starting from Papa study that was Chennai and Delhi. Then few other study, including what Sagnik also reported, the Ahmedabad study, one of my junior took my health. There are 5 cities showed impact, and as Sagnik already covered that where the exposure is less, effect is much higher, so I am not touching upon. Then 2 recent study, where parallelly we did, I and Sagnik did one and PHFI did, that also showed almost similar effect. Only the numbers will vary because the exposure levels are different that they consider. They consider interquartile range, we consider 10 microgram per meter cube. So that's the only difference. Sagnik already talked about this study where we explore further details with the PM species. Then another one, that the evidence of anemia and air pollution, that before that there was little evidence, was not so robust, yet the causality is not established. However, we can consider this is the association. It's long way to go to establish this association. This is for under 5. This was for WRA, women of reproductive age, that he already spoke. And this is the final one that he was talking about, that we also explore the 3 different children health outcomes with the PM species and the fraction shared by different sources. In conclusion, the local evidence of air pollution and health effects in India is improving over time, but yet to focus on many other factors like cancer, like neurological disorder, like coronary artery disease. The premature CAD is one of the emerging concerns in our country. Metabolic disorder, the PHFI is doing the study, but I didn't find, they have not published, I guess. But metabolic disorder and the cardiometabolic risk factor and air pollution, that is what they are doing. They published the methodological paper, but I have not seen the actual results. And recent priorities should be quantify the association that I told, that where the evidence is there globally. We just need to quantify for, plan our, policy correctly for the implementation. And considering variation of these acute effects that Sagnik shown, that itself is telling we should decentralize our study across the geography to understand the entire spectrum of the air pollution health effects. And finally, the inflammatory pathway, which is mediated by the oxidative stress, is a most explained physiological pathway for air pollution and health effects, where antioxidant may play a very vital role. So we really need to explore this particular link till we can cut down our air pollution below 5 microgram per meter cube, where nearly impossible in next 50 years, I guess. Thank you very much. I took more time.
Yeah. Thank you, Professor Santo. Now the questions, please.
Good?
Okay.
Yes, please.
Mechanism is when you are seeing the kind of linkages between PM 2.5 and different
no study yet, that the problem is the health science people should come up. Okay, and this mechanism, it should be a physiological mechanism need to be established. I feel it is not only the physiological mechanism of PM 2.5, we should focus more in depth with actual species, your oxidative potential, all together need to be explored. I think, you correctly pointed out that it's long before that was discussed, but nothing progressed actually. So that need to be actually established. We are mainly focusing on epidemiological studies. Epidemiological studies cannot give us a proper mitigation strategy. We have to understand the physiological mechanism, and unless that happens, it's really difficult. That is needed. Yeah, these are require more trained people. There are very limited people who are interested in environmental, epidemiology itself. And then even the physicians has to come up. Right. And the problem for environmental epidemiology is a bit complicated.
That is correct. Yeah.
Okay, the whole mechanism is complicated.
Yeah.
So people are not much interested to enter into this complex life. So that, unless that happens, we really cannot solve whole the problem. It would be only the problem would be solved superficially. Yes. At the end, the problem would be as is.
Yeah.
Yeah.
I'm quick to add that. So for this anemia work, actually, they have given a hypothesis on this physiological pathway, and that can be tested in a cohort setting. Yes. If you have those biomarkers and all. So that is what is required actually.
But there are some groups who are actually trying, even my own group, Kalpana's group, they are also trying. But many groups has to come up with this. I being a environmental scientist or Sagnik being a exposure scientist cannot solve this problem. It is beyond our cup of tea. We only can help. But a core health science people should come up. Because the physiological mechanism is beyond our thought. We don't know.
Professor Andu, a small comment.
Yes.
In addition to PM composition, how do you see in Indian perspective the size distribution and having this LDSA kind of studies so that you can estimate the lung deposition?
Yeah, of course, that will help. But, if you are looking for actual species, why do you need to bother about the size? Because this is an alternative. We are trying to explore the actual composition.
Size may matter because
if you see, sorry, yeah, please.
If you are talking about certain transmitters. Depending on when you are in air, size will decide how deep it can reach.
But that is PM. But when you come to the molecule,
that molecule is a part of that PM, right?
Can I just add on quickly?
Yeah.
Because our respiratory system, it depends upon the impaction, and what the processes are taking place in atmosphere. I'm just adding, please listen. Quickly, because the respiratory tract it's basically works on impaction, deposition. Couple of phenomena are there, and the size distribution, it varies. If you have less than PM1, that get deposited more, and in between it bounce back. So that depends upon how the toxic, in addition to size, the composition again is very important, because nowadays we have the analytical skills so that down to PM1 we can make the composition also. So I think combination of these two in addition to dose curve analysis will give a kind of very much understanding about the exposure.
Agree.
Yeah, so in IIT Delhi actually two of my colleagues actually did one small experiment where they found that particles smaller than 0.25. So they call PM 0.25, it's 5 times more toxic than PM 2.5. So right now it's not actually, nobody is actually giving much importance, but probably yes, because size in a way also is related to species toxicity and all. We need to explore that.
Yeah, I'm not ignoring that part.
You consider respiratory tract as an ambient environment.
I'm not ignoring that, but we can.
Smaller the particle,
thank you.
Yeah. Reach. So I think we should be concerned composition of the smaller particle, probably. The larger particle may not reach deep.
Thank you, all the speakers. Please applause for all the 3 speakers. Thank you.
Yeah, thank you, Rakesh, for chairing the session. And I thank one and all the speakers, delegates, everybody, for keeping to the time. We finished 5 minutes early. That's great. So as you see in the program, we don't have a formal valedictory function. What we have is a closing session. The way we planned is we'll have a maybe kind of a round table. No, it's not round table, but yeah, open discussion for outcomes and the way forward. We have prepared a short document, and now I will request Dr. Antti to chair that particular session, and then followed by we'll have a best poster prize prize distribution. Professor Ghanshyam Krishna, he has to attend a meeting, so he won't be joining us. So we'll not have a remarks by Professor Ghanshyam Krishna. We'll directly go for vote of thanks then. Yeah. Over to you, Antti.
How long do you want this to?
We can have as long as we want to. I think half an hour, 20 minutes, absolutely fine. Yeah.
Okay, so now we've heard very many talks, good and excellent talks, and the organizers have here listed some of the, let's say, notifications that they have made during the talks, what are the important points, and what we were asked actually in the very first session was that we should come up with some kind of a way forward, and why do we do these studies, and what should be the objective of them, and how do we go about in the future so that we can maximize the results of this symposium, so that it's not only, as it was said, whining and dining, but actually there are some concrete results. And now in this session, we will go through these notifications that were made during the last 2 days, a little bit. And then there's open discussion from you. So what do you see the points that are important that we should have in our final sort of white paper of recommendations for the way forward? And what should basically be the concrete steps as well? And I think that the organizers then, after the symposium, will pull this white paper together for everybody to circulate. Okay, so how do you want to show this? There are 3 pages now of different ways of doing that.
I don't think we can squeeze into 3 pages.
No, we can't.
We can go through point by point maybe. No, we can't.
Okay, let's do it such way that I will follow the document at the same time, and I will take your comments, and then if the comment is already there, then I will emphasize or make some mark that this is especially important, and if there are new comments, then we will add it to the document.
You have most of them are here now.
Okay, so floor is now open. What do you see that was maybe the most important finding or of this symposium? And
May I ask who is the designated target for this document? Is it the ministry?
Yes. Oh, yes. Minister.
Yeah, because I mean, I can see this is relevant for 3-4 different ministries. So I'm just trying to think actually how to
We don't
make
have
that kind of
specific,
coordination.
yeah, specific ministry in mind, but it's also open with the senior colleagues here to suggest what could be the best effective way.
Yeah, so I think the best effective way would be, so DST, MOES, MOEFCC, Health Ministry, 4 ministries definitely, and then think tanks like NITI Aayog and PS office. Probably it will be best is that if these points can be sort of summarize and link to the ongoing programs of those ministries. Because otherwise then it looks like these are required. For example, MOFCC has already programmed, National Clean Air Program. So under that which will be important. EST is also having a program on climate change, of which aerosol climate interaction is very important. Similarly, that all the points regarding to nanoparticle formation and all perhaps also could go there. MOES is also, again in MOES has different programs. So my point is that this can be grouped and then linked to the ongoing programs, and if we feel that focused network program is required to be created to address some of these issues, that also can be suggested.
I think that's a very good suggestion. We should do that. Right?
Yeah, we can differentiate and then we can try to link with that. Yeah.
So at least it will work, if not all ministries, but maybe at one of the ministries.
Yeah.
So that will also help.
And then maybe we can approach different ministries and also
And then say that this is the program you are already having, and this is what is required to be added from.
Sure.
The way I see it is that we have findings that we have made during this symposium. We have open questions that we have found that need to be addressed. And then, let's say, we as a community are trying to come up with recommendations of what should be done. Sagnik.
Also one more point. Sorry. The DST, Department of Science and Technology, is coming up with a research vision document. So this is 2030 and beyond. What are the immediate action item? And under that, focusing on the climate. So you can share this with them also. And I know that you are also part of that. So you know that there are different sections already identified within that what area India should invest in. And that document will be followed by all the ministries once it is finalized.
So more comments or notices now from the audience. Please wait for the mic.
So you said, going through those points, and if I really resemble so I think there was something about nitrogen. I definitely would say that highlight that. Exactly. So that's definitely very important.
Good.
Sorry, one more point is coming to
Yeah. Don't
so
hesitate.
what I'm seeing here is missing is that I personally think in India we don't have adequate capacity even. Very few groups actually are capable of doing this kind of advanced measurements and all. So capacity building in aerosol measurements should also be a very important point. It's not just the science, but science cannot be done with enough groups actually capable of doing those measurements. Okay,
but so not just the aerosol science, or maybe the atmospheric measurement. Yeah.
So the objective of this symposium was mainly on the secondary aerosols formation and growth. So even though the NPF studies have been going on for last 15 years or so, even in the advanced countries, but still we have not quantified what is the contribution of this kind of secondary aerosols to CCN and how it alters the cloud and precipitation microphysics. So that is still not very much quantified, especially in India it's not much So as an outcome of this symposium, are we like planning some collaborative major campaign in any selective location wherein all groups can bring in all these facilities at one place and address that? So yeah, otherwise sporadically several groups are working independently here and there, but there is no so as a recommendation of this, we can put up a major proposal, and so it can come up like, because there are complaints also. People are not coming with the big proposals. So small proposals are going from different institutions. So it could be a international collaboration proposal. We had good speakers today, like Manish from PNNL and all. So can we plan something big in India? So that could be one recommendation from this.
Please.
I apologize if my comments are not really aligned with the aerosol, but I see there was a regional emission can constrain local air quality. I see that. So are we are we just talking about the PM 2.5 here, or just air quality means, or because there are emission inventories in India needs to be updated. It's we are really so I'm not sure if that's the scope of the.
Yeah.
Yeah, with the carbonation aerosol program, but still actually the update of emission inventory is for 2019, and now we are in 23. So already there is a 4-year kind of.
That's true. Now scope is also real-time emission inventories and having high-time resolution.
For these kind of studies, I think it has to be modeling based, right? For measurement based would be difficult.
Yeah,
that's measurements. Okay, but then you have to have multiple data sites, not just one or two sites. Yeah, exactly. Yeah.
I mean, for emission inventory, you need to have the emission ratios, emission factors. So for that, you need measurement, right?
Yes.
So.
And definitely more than just PM 2.5. Yeah.
First of all, thank you so much for the organizers for this wonderful session. And we all are talking about like the formation of aerosols and the hazards of these particles. So everyone knows these are not very much good for our health, and we should also go forward for the solution of removal of those particles from the air, as well as from indoor as well as from outdoor. So I think these would be like a better suggestion. Thank you.
Exactly.
Yeah, means one thing I felt in these 2 days not discussed more is about lab scale experiments. So when Dr. Panditurai is suggesting bringing or putting proposals, yesterday Dr. Lubna showed the kind of experiment they are doing, like they are showing 6 AMS club together in one place. So and as a modeler, I generally feel that my regional scale sophisticated model also doesn't have proper chemical equations, right? So those kind of experiments coupled with modeling studies can actually go from microclimate to regional and cover most of the questions we are trying to address.
One recommendation for measurement. I would suggest, now whenever we are taking the measurements, we should do size segregated chemical composition, because when we are doing PM10 or PM 2.5, a few big particle will take over the mass of all is one particle. If we have size segregated, then we know that, okay, this size, that particular source is important. So size segregated chemical composition, that is what we should consider.
Chandan mentioned, chamber experiments is something that you need a lot of resources. If I have to just look at sulfuric acid aerosol formation, I need SO2 analyzer, I need S2 sim, and so on. And that itself is too expensive. But chamber experiment basically meant to be control, you're doing something in control environment. Rather than replicating it, maybe we have a cloud chamber in Europe, maybe we can come up with some kind of parameterization, and then we can incorporate into our regional models, what you have been doing, right? So probably that will be the best solution rather than creating chamber and then simulating what already people are doing. So again here, international collaboration or maybe integrating the information, which is available in the literature also. It's not that we have to have collaboration for some of the things.
I didn't quite catch you. Did you say that utilize the existing chambers and
yes.
not to build?
Yeah. Okay. Because it's a control environment, whether I do it or you do it, we are going to get the same result. Yeah, I know how much of SO2 I am putting in, and OH, I know how much of S2 it's going to be there. Atmosphere is like cocktail, you don't have any control. But in chamber, you can control one particular VOC, isoprene, monoterpene, ozone, and look at what is happening. Yeah. So for that we need in situ measurements. So we'll get some idea how much isoprene we have in the air, and in Europe there might be difference. Chamber, exactly. We need to just know the rates and their quantification from the chamber studies. That whether I do it or they do it, it's the same thing. Yeah. Correct. That's true. I mean, once you have a measurements will tell you this much is there, that much is there, but you will not have any mechanistic understanding. You have to rely on models and probably some kind of experiments to know the physical mechanism that is, or governing processes that is happening in the atmosphere. But of course, you need measurement, and along with probably chamber studies, and basically you need everything in order to come up with a superior process level understanding. There is no shortcut, yeah, especially. Yes. 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 Yeah. That's what Dr. Panditu has suggested. So, yeah, we should do that. We should bring at one place and then do it, whether it's campaign based or continuous. I think we should do it. That's a really great proposal. Logistically easy, yeah. Considering the resources, yes. Yes, let's hope that we'll have funding opportunities to cover logistic support, and that should help, I think. Okay. Right. Thank you. Any other suggestions?
Yes, more
recommendations? Yeah. I'll take over to you.
Please go ahead. Yeah.
following that comment, having that everybody together and doing the measurement, but to solve or to really understand the problem, we also need to bring other scientists like, epidemiologists. So we need to bring health experts. Same, I think agriculture is such a, important topic. So we definitely needs to collaborate with people from different fields. That's what I don't know. I don't mean to just really expand that, but yeah.
Let's take everything in, and like I said, that the organizers will go through it and come up with the suggestion paper then for everybody at the moment. Any more comments? I have one very practical question for anybody to answer. How to ensure that the collaboration happens, that it's not only discussion now? Who will host the next Nano 24?
Yeah, I have a small query.
Please go ahead.
So, in policy perspective view, what are the regional and global impacts of aerosol-related forcing on ecosystem as well as air quality and public health, and how we can address these impacts in climate policy and how we can take decision making?
I will try to remember your comment now. What are the impacts of climate change or air pollution? What did you say? Can you repeat that maybe?
So, what are the regional and global impacts of aerosol-related forcing on ecosystem and air quality as well as public health, and how we can address these impacts in climate policy and how we can take decision?
Good. So does anybody have then answer to my question that how do we ensure that the collaboration happens that we have now been discussing? Because typically it happens so that, we go home now. But at the minimum, I think that this kind of regular meetings could be there.
And also, at least if there are collaborations established at university, institute level, like we have with recently, so
yes,
that will facilitate more student and faculty exchange and those things.
So we already have MOUs from my IIT Madras and Helsinki and Delhi also. So this could be probably the one way to ensure that it happens.
Yeah.
Maybe we could set up some working group which meets periodically. Once in a while, like once in a year or two.
Yes.
To work on this collaborative proposal.
Yes.
Or even submitting it to different ministries.
Yes.
By grouping into all these action items to different ministries.
Yes.
We have Indo-Swiss collaboration, Indo-French. There will
There
always
many EU call also is there.
There
Most recently there is a EU
Yes.
call on horizon, both climate and health.
Yes.
So those can be explored.
Yes. One of our colleagues got almost 4 crore under Indo-Swiss. Huge money. I think it is, there are probably opportunities. As you said, nobody is submitting the project, right? So probably how to.
Yeah, the prior MOUs help you when
Yes,
the time comes
absolutely.
for the proposal.
It just increases the chances.
And even now many IITs are going actually beyond MOUs, and then they have started dual PhD program.
Yeah.
Like we have
Yes,
IIT,
with plan.
IIT Bombay has with Monash and others.
I will share with you recently there is a form in that also.
So you have the answer?
I think I have already some ideas. Okay. Anything else from anybody? Or have we emptied the bank for now, after 2 long days? Okay, let's conclude. Thank you so much for a good brainstorming.
Thank you, everyone. Thank you, Auntie. Okay, now yes, of course. We have a poster presentation prize distribution now, which is supported by SGN controls. So I'll just run this in background while I'm doing my stuff. So we had total 18 posters. I mean, there were 18 submitted and 2, 3 withdrawn for genuine reasons. They had a UGC NET examination or something, so they had to withdraw. So total, I think there were 16 yesterday and today. We had a jury panel for evaluation of poster, and there were 2 rounds. Round 1, jury mainly looked at the scientific novelty, and in round 2, they were looking at the presentation skills and stuff like that. So out of 16, we shortlisted 5, best 5 posters, and out of that, 3 presented here this morning. I've already shown you the list. So we have the results, so I'll now call from last, of course. So we have 2 consolation prizes that you already know, Pallavi Padwal and Oishi Chakravarti. So yeah, can we have Pallavi and Oishi? And may I request Professor Krishna to please present the awards to the awardees. Where is our photographer? Yeah, that is video. That is video. 1 second, Vaishi. Yeah. Can we? Yeah, we will have a photo. Oishi Chakravarti? Yes, all of them. She is our student, sir. She is now at ISC Bangalore. Yeah. And number 3 goes to M. Deva Prasad. Yeah. Sorry, I don't have that.
So you are from which institution?
PRL Ahmedabad. You're a student of Neeraj. Okay, now I get it. Oh, I did not know that. Thanks. Good. So he gets a memento plus certificate and a little cash prize. The second goes to Arun Nair from IIT Madras. And I guess if you have guessed who is the first. And of course, the first goes to Subrata Mukherjee from IITM Pune. So we have a special gift for him. That's a 3-channel diffusion dryer. I don't know if I have a video here.
He is from IIT?
IITM Pune.
ISR Pune.
No,
IITM Pune, Indian Institute of Tropical Meteorology, Pune. Yeah.
Air quality monitoring station.
Yeah, yeah.
I think first prize will have some additional.
So three parallel channels of maximum efficiency. This is the dryer, which features 3 separate channels, each surrounded with silica gel beds, allowing to process more aerosol samples. And yeah, you can see the little animation and their analysis there. So the poster awards were supported by Edge and Controls. Okay, congratulations all the awardees, and congratulations to others also. You will get next time. So don't worry. Not here, somewhere else. Right, so with that, we are towards end of this session now. So I'll do the formal vote of thanks, unless if anyone wants to add anything before I do that. Okay, I guess assume no. Right, so on behalf of organizing committee, and of course my co-convener, Dr. Rakesh Sura, I'm really pleased and honored to be standing here to convey my gratitude and regards to dignitaries, delegates, the participants present here, the faculty members, our university supporting staff, and other members who have helped by, directly or indirectly. So let me first and foremost, it gives me immense pleasure to extend my heartfelt thanks to our chief guest, Shri Varshney ji, who for gracing the occasion and for spending one entire day with us. I would like to also thank our guest of honor, our beloved Vice Chancellor, Professor Bijay Rao, for accepting our invitation and addressing the gathering and making sure that he reaches for the inaugural session on time. Yeah, even he was out of country a day before. And of course, with his really motivational kind of words and his enthusiastic support to the university and to our center has always been very encouraging. I also thank our esteemed guest, Dr. Mikka Tironen. He is a Counselor of Science and Education in Embassy of Finland in New Delhi, for gracing the occasion with his presence. I'm thankful to the Dean, School of Physics, for being there and for unflinching support extended to our center. Of course, I take this moment to acknowledge and thank our head of the department, Professor K.S. Krishna, for his dedication and guidance that you have provided and for backing up us with, in our efforts with this symposium and even other activities at the center. I thank all delegates, particularly who have come all the way and joined, and of course, some of them joined virtually from US, UK, and Europe, giving your time and agreeing to share your knowledge with us. It was an honor for our center and university to have had such a prominent speakers delivering a lecture in their respective research fields. Particularly, I would like to thank each one of you for strictly following the allocated time for the talk and making my life much easier. You were the, I can't say you were, actually you are the heart of this symposium, right? And you will be always. So I said you because this is not the meeting which going to end after this, as Auntie also pointed out. We are going to have more deliberations, probably white paper, and in future also collaborative projects and things like that. So yeah, thank you so much for all the delegates, all the speakers. I also would like to thank and congratulate student participants for coming all the way to attend the symposium and present your ideas. And as jury told me, the posters were very competitive. They had a hard time. And we had almost 1 hour, 40 minutes, and I'm happy that they utilized the entire time evaluating your posters. And I don't hope, rather I'm sure that you have found this symposium fruitful, and definitely you have learned something and gained something from this symposium. I congratulate the students who have received the Best Poster Award, and I'm confident that it will motivate you in your future endeavors. I thank our sponsors, Institution of Eminence, University of Hyderabad, TSI Instrument India Private Limited, Indian Institute of Tropical Meteorology, Pune, Ministry of Earth Sciences, MG Analysis System, Pune, SGN Controls, TESCON, without whom this event would not have been possible. Particularly, I want to thank Institution of Eminence, director, who has been, considerate about the needs of our expenditure. So, yeah, thank you so much. A sincere appreciation to university and administration for providing all the support that we needed, different kinds of permission at the security, and even today we had some kind of a protest, but yeah, we had a great time last 2 days. I sincerely thank the Finnish Meteorological Institute, Finland, for being a co-partner in facilitating the global peer speakers of the subject, framing and supporting the host University of Hyderabad in organizing this particular symposium. And sincere thanks to my faculty colleagues and of course office staff. They are the support system, for their kind support and encouragement as always over the last 7 years. I'll be completing 7 years on 31st March. So with that, yeah, thank you so much. Last but never the least, I cannot overlook the tireless efforts of our technical and organizing committee. I'm so grateful for organizing committee members, Dr. Srijit, Dr. Stella, Dr. Charan, Matthew, Varaprasad, Vaishali, Duraimaran, Anibisha, am I missing anyone? Paul, who was not well, and I have asked him to, take rest, but he was just hanging around. So I'm really grateful to you guys for your dedication, the efforts that you put over the last 2 months, especially last 4 or 5 days. And also, of course, I'm so grateful for my co-convener and our organizing committee members, Professor Chakravarti and Dr. Devalina Mani Tiwari, for their support over the last 1.5 or 2 months. Since the wheels began rolling 2 months ago, when the symposium was put into action, the technical committee members, have been working diligently, and I really appreciate, and our research scholars. They are not just our support system in the scientific field, but also in some of the other technical fields also. So thank you so much, one and all. Thank you all once again, and for making this event a grand success. Thank you. Thank you so much.